What if the universe had ignited just a fraction hotter at its birth? That seemingly minuscule difference could have rewritten everything, altering the formation of galaxies, reshaping the chemistry of existence, and even determining whether life, as we know it, could ever emerge. At the heart of this cosmic what-if lies a hidden blueprint, an underlying force that governs how stars burn, how planets evolve, and how the very fabric of reality is stitched together. But what if these fundamental forces had taken a different path? Would time feel the same? Would dark matter behave differently? Would intelligent life rise from the cosmic dust? Or would something entirely unrecognizable take its place? At the very dawn of the universe, during what we call the Big Bang, temperatures were unimaginably high, far beyond what we can easily grasp. Picture the heat of a billion suns compressed into an infinitesimally small space. In such an environment, matter and energy behaved in extreme, almost incomprehensible ways. If we could imagine just a tiny increase in temperature, let's say a fraction of a percent, the ramifications could be immense. This seemingly trivial change within the context of the early universe could have sparked dramatic shifts in the course of cosmic history. For instance, the formation of fundamental particles like quarks and electrons might have unfolded differently. Quarks, the elementary building blocks of matter, might have combined in new ways to form protons and neutrons, altering the balance between matter and antimatter. This could have had profound consequences by potentially determining the very structure of the universe. As the cosmos expanded and cooled, that small shift in temperature could influence the creation of atomic nuclei during a period known as nucleosynthesis. A rise in temperature, even by a modest amount, might result in an abundance of certain elements, like helium, or perhaps even heavier elements. This, in turn, would have influenced the composition of stars later in the universe's timeline. But the changes wouldn't stop there. The rapid expansion of the early universe, called cosmic inflation, could also have been affected. A slight increase in temperature might enhance this expansion or trigger instabilities that ripple through space-time. These instabilities could alter the very way the universe expanded, potentially changing the rate at which galaxies formed or reshaping the large-scale cosmic structures we observe today. A tiny shift, imperceptible on a human scale, could have triggered a cascade of cosmic events, reshaping the universe's evolution from the earliest moments. Even in the earliest moments of the universe, shortly after the Big Bang, the environment was a seething cauldron of heat and energy. Picture an intensely energetic soup with every particle in violent motion, constantly bouncing around due to the immense heat. During this period, energy was not evenly spread out, but was packed into incredibly dense pockets. As temperatures soared beyond anything we can truly fathom, the universe was in a constant state of flux. The energy levels were so high that stable particles couldn't even form. There was no solid matter in this chaotic realm, just pairs of particles and their counterparts, such as electrons and positrons, constantly appearing and annihilating each other in flashes. However, as the universe began to cool, energy began to disperse, much like a balloon expanding. The cooling process marked a critical turning point in the universe's history. Once, when temperatures were still extreme, particles couldn't combine to form stable entities. But as the universe continued to expand and cool, the energy dropped just low enough for more stable particles, such as protons and neutrons, to emerge. These fundamental building blocks of matter began to coalesce, eventually forming the simplest of atoms, hydrogen and helium. It was at this juncture that instability began to give way to order, and the chaotic primordial soup began to settle into the universe as we know it. The distribution of energy played an equally pivotal role. Rather than being uniform, it was filled with slight fluctuations in density. These variations, though subtle, were the seeds for the creation of galaxies. Regions of higher density attracted more matter, while voids expanded where the density was lower. These early fluctuations would eventually form the sprawling cosmic structures we see today: massive galaxies, clusters of galaxies, and voids in between. Yet even this seemingly small fluctuation, this tiny shift in temperature, could cause a chain reaction at the level of subatomic particles. When matter is heated, its particles, including atoms and their components, gain energy and begin moving with more vigor. Imagine a group of people in a room. As the temperature rises, they begin to move around more, becoming more active and less still. The same is true for particles. As they gain energy, they collide more frequently, with greater force. These collisions may lead to new reactions, potentially altering their arrangement or state. If the temperature rise is substantial enough, it could cause electrons to be ejected from atoms, resulting in the formation of ions. This change would alter the balance of charges within the material, potentially influencing its chemical properties. Such changes, triggered by seemingly tiny shifts in temperature, could start a cascade of events. New ions could form, accelerating chemical reactions that had previously been dormant. In gases, this heightened energy could increase the frequency of particle collisions, fostering the creation of new compounds or the breaking of existing bonds. This delicate dance of temperature and energy could have far-reaching implications. A small rise in temperature, imperceptible to us but cosmic in scope, could have triggered a series of events that might have completely reshaped the evolution of the universe. It could have influenced everything from the very formation of matter to the complex chemistry that underpins the stars, planets, and even life itself. Imagine then that the universe's fate could have been altered by something as subtle as the temperature difference of just a fraction of a percent at its birth. It would not just have affected the immediate formation of matter, but also the grander structure of the universe, its galaxies, stars, and even the potential for life. Every shift, no matter how tiny, could have had consequences we may never fully understand. In the realm of particle physics, even a minuscule increase in temperature within a high-energy environment could set off profound changes, including the creation of entirely new particles. This phenomenon is rooted in the fundamental principle of mass-energy equivalence, famously encapsulated in Einstein's equation, E equals mc squared. It's akin to the subtle tremor of an earthquake fault line that unexpectedly triggers a much larger seismic event. This seemingly minor shift in energy has the potential to lead to far-reaching consequences, initiating a chain of reactions that culminates in the formation of new entities within the subatomic world. Just as a small disturbance in a fault line can create powerful aftershocks, a slight temperature increase among subatomic particles serves as a catalyst, igniting enhanced movement and triggering more frequent collisions. These collisions, in turn, unleash a cascade of reactions, possibly resulting in the creation of entirely new substances or the transformation of existing particles. From this initial nudge of energy, new particles may emerge, fundamentally altering the composition and behavior of matter in the high-energy environment. The concept of cosmic inflation is closely tied to this dynamic. It refers to the extremely rapid expansion of the universe in the moments following the Big Bang, when the cosmos stretched at an astonishing rate. If we introduce a hotter environment into this scenario, the very dynamics of this expansion could change in significant ways. A hotter universe, packed with more energy, would accelerate particle interactions. With more energy in play, collisions between particles would become more frequent and intense, potentially influencing the rate at which the universe continues to expand. This heightened energy could also alter the behavior of the fundamental forces that govern the cosmos. Forces like gravity and electromagnetism could behave differently in a hotter environment, potentially favoring new phases of matter or even influencing the fields that drive inflation itself. The result could be a universe that expands more erratically, with different regions experiencing inflation at varying rates. This unpredictability in the expansion could create a universe with a vastly different set of physical laws, influencing the eventual formation of galaxies, stars, and perhaps even life. A hotter early universe would not only affect the rate of inflation, but it would also influence the very constants of nature, those fundamental numbers that govern the interactions of particles and forces. These constants, akin to the rules of a game, play a crucial role in determining how matter behaves. If these rules had shifted even slightly, the game of the cosmos would unfold in entirely different ways. The higher the temperature during the Big Bang, the faster particles would have moved, and the more energetically they would have interacted. In this intensely energetic environment, particles that would normally be rare might have become much more common. Consider the analogy of stirring a pot of soup. When the temperature rises, the ingredients mix differently, and new combinations emerge. In the same way, the higher temperatures could have altered the balance of forces within the universe, shifting how atoms formed and how stars ignited. If the early universe had been even slightly hotter, the entire structure of the cosmos, down to the very formation of life, could have been dramatically different. This idea is particularly critical when we consider the process of primordial nucleosynthesis, which took place in the first few minutes after the Big Bang. During this period, the universe was so hot and dense that protons and neutrons collided and fused to create the simplest elements, such as hydrogen, helium, and traces of lithium. If the temperature had been higher, there would have been more energy available for these nuclear reactions, potentially leading to the formation of more helium and a different mix of elements. On the other hand, if the temperature had been lower, nuclear reactions would have been less frequent or might not have occurred at all, leaving the universe with far fewer light elements. This imbalance in element formation would have profound implications for the universe's evolution, particularly in the formation of stars and galaxies. Stars are born from clouds of gas collapsing under their own gravity, and a hotter universe could accelerate this collapse. The result? Stars would form more rapidly, possibly growing larger than they would have in a cooler universe. Larger stars burn hotter and more quickly, living shorter lives but exploding in supernovae with immense force. This would affect not only the types of stars that form, but also the elements they produce. A higher energy environment could also influence how stars interact with their surroundings. More energetic stars would expel material into space at a faster rate, enriching the interstellar medium with heavier elements at an accelerated pace. This, in turn, would have profound consequences for future generations of stars and planets. Instead of the gradual process of star formation and stellar evolution that we observe today, a hotter early universe might produce a landscape where stars form in rapid succession, each one more massive and short-lived than the next. This would reshape the chemical pathways for star and planet formation, influencing the nature of the planets that would eventually form around these stars. The behavior of stars and their life cycles is closely linked to the temperature of the early universe. At high temperatures, energy levels were higher and particle interactions were faster. This created conditions where more massive structures could form rapidly, from atoms to galaxies. However, what if the universe had cooled more slowly than it actually did? In that case, lighter elements like hydrogen and helium, the fundamental building blocks of stars, might have formed less readily. A slower cooling rate could have allowed more time for complex structures to evolve, leading to a more diverse array of galaxies. Ultimately, the temperature of the early universe played a pivotal role in shaping the cosmos. A hotter universe could have produced stars that are more massive and born at different intervals, leading to a universe filled with different types of stars, galaxies, and planets. The interplay between energy, temperature, and the fundamental forces of nature was critical in determining how our universe evolved from a hot, dense point to the vast and varied expanse we observe today. And just as a small temperature fluctuation can have profound effects on the subatomic world, the temperature of the early universe set the stage for everything that followed, influencing the very formation of matter, energy, and the laws that govern them. Conversely, if the universe had cooled too quickly after the Big Bang, only a limited number of smaller galaxies might have emerged. The essential conditions necessary for the formation of larger galaxies would not have been met. Temperature plays a pivotal role in the way matter clusters under the influence of gravity. At higher temperatures, the energy and motion of particles increase, which could accelerate the formation of denser regions. These dense areas, under the right conditions, might create galaxies more rapidly. As galaxies are born, their interactions with each other are also shaped by the prevailing temperature conditions. A hotter universe, at an earlier stage, might give rise to dense clusters of galaxies. In contrast, a cooler early universe would lead to a more uniform distribution of galaxies, each possessing distinct characteristics. Ultimately, the temperature fluctuations during the universe's infancy are intimately connected to the types and abundance of galaxies formed. Warmer conditions could foster a diverse and numerous array of galaxies, while cooler environments might limit the complexity and size of the galactic structures that arise. Understanding these dynamics helps us unlock the mysteries of how our universe has evolved over billions of years. When we expand our thinking to consider altered processes of star formation, we begin to explore a range of phenomena that are both unique and unfamiliar. Typically, stars form from clouds of gas and dust that collapse under their own gravity. However, if the conditions influencing this process change, perhaps due to turbulence from a nearby supernova or the gravitational influence of other massive stars, the outcomes could be vastly different. One such possibility is the formation of stars far larger than those we observe today. Under certain conditions, gas clouds might funnel together more efficiently, creating stars that are much larger and more massive than the ones currently seen in our galaxy. These massive stars burn hotter and faster than their smaller counterparts, which leads to a much more dramatic life cycle. When these massive stars reach the end of their life, they explode in powerful supernovae, releasing immense amounts of light and energy. The energy from these events can have profound effects on the surrounding regions, potentially igniting new waves of star formation, or even leading to the creation of exotic objects like neutron stars or black holes. Another fascinating outcome could be the formation of binary or even triple star systems. In typical star-forming scenarios, stars generally form independently, isolated from one another. However, under altered environmental conditions, stars may form in clusters. When stars are born close to one another, their gravitational forces can bind them into pairs or even triplets. These systems can create complex and dynamic interactions, including dramatic flares, energy exchanges, and occasionally even catastrophic collisions that lead to spectacular cosmic displays. One of the more unusual phenomena that could emerge from these altered conditions is the formation of failed stars, often referred to as brown dwarfs. These objects are larger than planets but fail to ignite nuclear fusion at their cores. If star formation is interrupted, or if the available material for star formation is insufficient, brown dwarfs may form in greater numbers. These enigmatic objects emit energy and heat like stars, yet they do not shine as brightly. Their existence challenges our understanding of what constitutes a star, and broadens our view of the variety of celestial bodies that can exist in the universe. Furthermore, altered conditions for star formation could lead to stars with unusual chemical compositions. Stars typically produce heavier elements through nuclear fusion, but if they form under different conditions, such as with varying materials or environmental factors, they might yield novel elements or isotopes. This could enrich the surrounding space with new chemical compositions, ultimately influencing the formation of planets and, potentially, the emergence of life. The consequences of these changes extend beyond individual stars. The very structure of galaxies could be altered. If star formation rates or processes were to change dramatically, the shape and evolution of entire galaxies could shift. The interplay between dark matter, gas, and stellar mass would create a dynamic feedback loop, resulting in entirely new types of galactic structures, ones we might never have imagined. As we alter the way stars form, we not only create new and unusual celestial bodies, but we also reimagine the very fabric of our universe. The formation of galaxies in its most basic form is a delicate and complex dance between two major components: baryonic matter, which makes up the stars, planets, and all known forms of life, and dark matter, which is a mysterious substance that does not emit light but is detectable only through its gravitational effects. As galaxies began to form in the early universe, fluctuations in temperature played a crucial role in shaping the interactions between these two types of matter. In the immediate aftermath of the Big Bang, the universe was extremely hot, and matter existed in a gas-like state. As the universe expanded and began to cool, baryonic matter started to clump together due to gravity. However, the presence of dark matter was just as essential in this process. Dark matter forms an invisible framework throughout the cosmos, creating a web-like structure that prevents ordinary matter from drifting too far apart. As temperatures decreased, baryonic matter began to lose energy, allowing it to collapse into denser regions where stars and galaxies could eventually form. Dark matter, through its gravitational effects, helped pull baryonic matter toward these areas, creating the building blocks for the galaxies we see today. The balance between baryonic matter and dark matter was influenced by how efficiently baryonic matter could cool down and clump together. If the temperature had been just right to favor the clumping of dark matter, it would have grown larger and had a more dominant role in determining where galaxies formed. Conversely, if baryonic matter had cooled too quickly, it might not have interacted effectively with dark matter, leading to a less structured universe with fewer galaxies. This delicate balance between cooling baryonic matter and the constant presence of dark matter remains fundamental in explaining the distribution of galaxies throughout space. It helps us understand how galaxies are not randomly scattered across the universe, but are woven into a grand cosmic tapestry, influenced by both visible and invisible forces. If the universe had experienced higher temperatures in its early stages, the formation of planets and their chemical compositions would have looked entirely different from what we observe today. A hotter environment would have meant that elements and compounds existed in different states compared to our current universe. Gases that are currently found as solids or liquids would have remained in a vapor state. This would have had a profound effect on how elements eventually came together to form planets. In this hotter universe, the process of aggregation would have favored the lighter elements, which are more volatile at high temperatures. This might have led to an abundance of gaseous planets, with fewer rocky solid ones than we see in our current universe. The universe we live in today is the result of a finely balanced series of events, from the way galaxies form to how planets emerge and evolve, and it continues to evolve in ways we are only beginning to understand. In the vastness of the universe, the conditions of its various environments shape not only the formation of celestial bodies, but also the very processes that might give rise to life. As the cosmos cools and evolves, the compounds that form and condense will vary dramatically, favoring those that can withstand the extreme heat of early stages in cosmic history. The universe, with its ongoing energy dynamics, offers a constantly shifting landscape of possibilities, where even the basic laws of physics appear to bend under the influence of colossal forces. When temperatures in the cosmos finally cool, the types of compounds that could condense would no longer resemble those that form in the present-day universe. Instead, the universe would favor compounds capable of withstanding the extreme heat of these early stages. Carbon, in various unique forms, would be one of the key elements, while exotic minerals might crystallize in conditions far hotter than anything seen on Earth. Furthermore, the distribution of heavier elements, those forged in the explosive deaths of stars, would also shift dramatically. If the conditions were hotter, it could lead to more energetic stellar events, potentially changing the way elements fused. This process might give rise to an entirely different array of heavy elements, some of which might only exist in the most extreme conditions, created within the swirling nebulae that would eventually coalesce into new planets. Additionally, the increase in cosmic energy could have profound impacts on the chemical reactions occurring throughout the universe. In high-energy environments, reactions would occur far more rapidly than in colder ones, which would allow complex molecules to form at an accelerated pace. This could dramatically alter the pathway of prebiotic chemistry, potentially leading to the creation of life forms or biochemical systems that are profoundly different from those on Earth. In a hotter, more energetic universe, the chemical building blocks of life might emerge in ways previously unimagined. This new universe, with its energetic intensity, would likely spawn a completely different array of planets, each with distinct compositions, unique mineral signatures, and chemical processes driving their development. As we peer into the extremes of the universe, places like neutron stars or supernovae present environments so intense that they can give birth to entirely new and exotic elements. Neutron stars, for instance, are created when a massive star collapses under its own gravity, creating a body where protons and electrons merge to form neutrons. The resulting dense matter is almost entirely composed of neutrons, and under these extreme conditions, the laws of physics behave in ways that challenge our understanding. Matter within these environments could take forms completely foreign to us, such as strange quark matter. In this state, quarks, elementary particles that usually form the building blocks of protons and neutrons, are freed from their conventional bonds and behave in ways that defy normal atomic structure. These unusual forms of matter could exhibit incredible properties, being both highly dense and stable, yet capable of unleashing vast amounts of energy. In addition to the peculiarities found in neutron stars, the early universe itself provides a stunning example of how extreme conditions shape the elements we encounter today. In the moments just after the Big Bang, the temperatures were so high that simple hydrogen and helium atoms fused together to form heavier elements. This process, known as nucleosynthesis, allowed the creation of elements that no longer exist in significant quantities today. These new elements might combine in ways that are not possible under Earth-like conditions, potentially leading to materials with extraordinary strength, unusual electrical properties, or novel magnetic behavior. The behavior of these exotic elements could also revolutionize our understanding of matter, possibly leading to the development of new technologies based on materials that conduct electricity better than known metals or display properties that are entirely new to science. One of the more fascinating aspects of the discovery of exotic matter is its potential applications. If scientists can learn to manipulate or replicate these elements in a laboratory setting, the possibilities are endless. Advanced technologies could emerge, powered by materials that behave in ways we have yet to fully comprehend. The potential for new energy sources, faster computing systems, or even novel forms of storage could be just the beginning. As our exploration of the universe continues, new elements and states of matter challenge our conventional thinking, pushing the boundaries of physics and material science to new frontiers. At the heart of all these chemical transformations lies one of the most profound questions in science: the emergence of life itself. Life, as we know it, is deeply dependent on specific chemical reactions, those that involve the elements carbon, hydrogen, oxygen, and nitrogen. These four elements combine to form molecules like amino acids and nucleic acids, which are the fundamental building blocks of proteins and genetic material. In different parts of the universe, however, chemical reactions take place under conditions far more extreme than those found on Earth. These reactions could lead to the formation of compounds that serve as the foundation for life, though they may differ significantly from what we recognize as life today. Consider, for example, the icy moons of gas giants or the subsurface oceans of distant exoplanets. These environments may lack the warmth of a nearby star, but still harbor enough energy to drive complex chemical reactions. In such places, organic molecules could form in the dark and cold, driven by energy sources such as tidal heating, radiation from distant stars, or geothermal activity from within the planet itself. These environments, though vastly different from Earth's surface, may still possess the potential to foster the emergence of life's precursors. Moreover, the discovery of extremophiles on Earth, organisms that thrive in environments such as deep-sea vents, acidic lakes, or superheated springs, has expanded our thinking on the nature of life. These organisms survive in conditions that were once thought to be uninhabitable, suggesting that life could arise in environments radically different from those on our home planet. In fact, this has broadened the search for life beyond Earth, prompting scientists to consider a wider variety of environments in which life might exist. For life to emerge, a key factor is the presence of liquid water, an essential solvent for chemical reactions. Water, along with varying temperatures and pressures, provides the right conditions for molecules to come together and form the complex structures necessary for life. This opens up new pathways for the evolution of life, paths that may look completely different from our own. From the depths of gas giants to the frozen moons on the outer edges of our solar system, the universe teems with environments that could harbor forms of life we have yet to imagine. The universe continues to surprise and challenge us, constantly shifting the parameters of what we know about the fundamental forces that shape existence. As we venture further into the cosmos, one thing becomes clear. The chemical and physical processes occurring on distant worlds may not just lead to the formation of planets and stars, but may also set the stage for life to emerge in forms far beyond what we can even envision. The search for biosignatures, the chemical markers of life, has become a crucial component of our quest to understand the universe. As we look beyond our own planet to distant worlds, the discovery of specific gases in a planet's atmosphere, such as oxygen or methane, can suggest the presence of ongoing biological processes. These gases are often associated with life, as on Earth, they are primarily produced by living organisms. The detection of such molecules on distant planets could indicate that life might not just exist, but thrive in environments far removed from our own. The potential for life to emerge independently on other worlds, guided by chemical processes distinct from those on Earth, opens up exciting possibilities about the diversity of life forms across the cosmos. This ongoing exploration of life in the universe challenges our fundamental understanding of what life is and what it needs to exist. It also fuels the broader search for answers to the profound question, are we alone in the universe? Every planet or moon has its own unique set of characteristics, from its atmospheric composition and temperature extremes to its gravity and radiation levels. These factors could shape the evolution of life forms in ways that are radically different from anything we know. Let's consider what that might look like on distant worlds. Take, for instance, the temperature of celestial bodies. On some planets, the heat might be unbearable, while others could be trapped in an eternal freeze. Life on a hot planet might evolve mechanisms to regulate internal temperatures, similar to how some organisms on Earth avoid overheating. In contrast, life forms in frigid environments could develop thick insulating layers or even produce substances that act as antifreeze, allowing them to survive in sub-zero conditions. In such environments, survival would depend on the organism's ability to adapt and thrive in extreme cold. Atmospheric pressure, too, plays a key role in the survival of life forms. On planets with dense atmospheres, creatures might evolve to be stockier, with shorter, more robust bodies that allow them to navigate through the thick air. Conversely, on planets with low atmospheric pressure, life forms might develop balloon-like structures to retain the gases they need for survival. Such adaptations would be critical for their existence in these unique environments. Gravity is another critical factor. Higher gravity would likely favor squat, muscular life forms, creatures built to withstand the immense weight pressing down on them. These organisms would need to be strong to support their bodies against the force of gravity. On a planet with lower gravity, however, life forms might grow taller or develop more fragile structures, as they would not be burdened by as much weight. Gravity's impact would shape the very form and function of life across different worlds. Radiation levels would also influence the evolution of life on distant planets. On planets with thin atmospheres or no protective magnetic fields, organisms might evolve biochemical processes that allow them to either shield themselves from harmful radiation or repair DNA damage caused by exposure. Protective shells or special pigments could become common traits in life forms living in these hostile environments, much like how some Earth organisms have evolved protective mechanisms against UV radiation. Moreover, the availability of specific nutrients would also influence how life develops. A planet rich in sulfur might support organisms that rely on sulfur-based chemistry rather than the carbon-based processes we are familiar with. Life on such a world could operate under a completely different set of biological rules. Instead of relying on oxygen and carbon, these creatures could use sulfur as their primary metabolic fuel, allowing them to thrive in environments that would be hostile to Earth-based life. In essence, if life were to emerge elsewhere in the universe, it would need to adapt to each planet's unique environmental pressures and conditions. These adaptations would likely result in life forms that are vastly different from anything we encounter on Earth, showcasing the incredible diversity that the cosmos has to offer. The night sky, as we see it, is shaped not only by the stars that twinkle above us, but also by the vast distances between those stars and our unique position in the universe. If the initial temperature of the universe had been different right after the Big Bang, the formation and distribution of stars, and by extension the constellations we see, would have been significantly altered. The temperature of the early universe plays a crucial role in how matter behaves. A hotter universe would mean that atomic particles would have more kinetic energy, moving faster and dispersing more widely. This would prevent gas clouds from collapsing into stable stars, leading to a universe with fewer stars. Conversely, if the universe had been cooler after the Big Bang, gas clouds could clump together more easily, potentially leading to an abundance of stars. The distribution of elements in the universe is also affected by temperature. A hotter early universe would favor the formation of lighter elements like hydrogen and helium, while a cooler universe could allow for more complex elements to form, leading to a greater variety of stars. These stars, in turn, would shape the constellations we see in the night sky. Some stars produce more heat and light than others, and this influences the patterns and shapes we associate with certain constellations. It's important to note that the constellations we recognize today are not permanent. As stars move and evolve over time, the patterns they form in the sky change. If the initial conditions of the universe had been different, the types and numbers of stars would also differ, which means the patterns in the sky would look nothing like the ones we currently observe. New constellations would emerge, and the celestial canvas we once looked to for guidance would be completely restructured. The universe would offer a completely different view, rich with new stories and meanings. A sky woven from entirely different threads. The large-scale structure of the universe, filaments and walls, shapes the distribution of galaxies. These cosmic structures form a web that stretches across space, providing a framework within which galaxies are situated. These structures are not static, however. As the universe continues to expand, filaments and walls change in surprising ways. The gravitational pull of dark matter, an invisible force that holds galaxies together, is responsible for the formation of these filaments. As galaxies interact with one another, colliding and merging, they create ripples in this vast cosmic web. These ripples, much like traffic on a busy highway, can alter the flow of galaxies and even lead to the formation of new structures. The expansion of the universe itself plays a key role in how these cosmic structures evolve. As the space between galaxies grows, the properties of the filaments and walls could change. These structures might grow denser or thinner, depending on how matter is distributed and how it responds to the forces at play. Over time, the universe's expansion will continue to reshape the landscape of the cosmos, influencing the very framework upon which galaxies are positioned. Ultimately, the universe is in a constant state of flux, with the interactions between galaxies, the expansion of space, and the influence of dark matter all contributing to the ever-changing nature of the cosmos. These cosmic structures are far from being fixed. They are dynamic, evolving, and shifting, offering an ever-changing backdrop to the ongoing story of the universe. Moreover, theories suggest that dark energy, another mysterious force propelling the expansion of the universe, could also play a pivotal role in reshaping the cosmic structures we observe. If dark energy fluctuates or behaves in unexpected ways over time, it might induce unpredictable changes in the formation and evolution of vast cosmic features, like filaments and walls. These intricate structures, which form the scaffolding of the universe, are far from static. The behavior of galaxies within these cosmic frameworks will likely lead to a constantly shifting landscape, one that reflects the dynamic and ever-changing nature of the universe itself. As we delve deeper into the cosmos, each new observation may reveal even more layers of complexity, inviting us to reconsider the very nature of the universe. Black holes, for instance, are fascinating celestial objects that evolve in the most intriguing ways. As stars burn through their nuclear fuel, they eventually reach a tipping point, causing them to collapse under the weight of their own gravity. This collapse can give birth to a black hole. Initially, black holes grow by drawing in material from their surroundings. This material spirals inward, forming a disk that heats up and emits powerful radiation, allowing the black hole to accumulate more mass over time. As the black hole's mass increases, it becomes even more massive, significantly altering its future evolution. However, the story doesn't end there. Smaller black holes, for example, can lose mass through a process known as Hawking radiation. This phenomenon occurs when particles are emitted from just outside the event horizon, the boundary beyond which nothing, neither matter nor light, can escape. Over time, this gradual loss of mass could cause smaller black holes to eventually evaporate entirely, potentially leaving no trace of their existence. This concept challenges our understanding of what happens at the core of these enigmatic objects. The singularity at the center of a black hole, where gravity is believed to be infinitely strong, poses even deeper challenges for current physics. It is within the singularity that the very fabric of space and time is thought to break down. However, researchers are now proposing various theories about how singularities might evolve. One such theory suggests that when black holes merge, their singularities might combine, altering their very nature. Other researchers speculate that the development of more sophisticated physics could reveal new structures within singularities. Rather than a point of infinite density, these structures might be far more complex, opening up new avenues for understanding how information behaves within black holes. This is especially significant in the ongoing study of quantum mechanics and relativity, as these two branches of physics have, for the most part, remained separate. The eventual merging of these concepts could revolutionize our understanding of black holes, their singularities, and by extension, the universe itself. As the universe continues to heat up and evolve, it may result in profound changes in the interplay between quantum mechanics and relativity. In a cooler universe, particles tend to move slower and behave according to the rules we are familiar with, rules that govern everyday experiences. However, the universe was far hotter during its early moments, immediately after the Big Bang. In this energetic environment, quantum mechanics governs the behavior of particles, and these particles can exist in multiple states simultaneously. Their properties seem strange and incomprehensible by everyday standards. Under intense heat, particles gain energy, move faster, and collide more vigorously, creating an environment where they constantly interact. This leads to the formation of new states of matter, such as plasma, a chaotic soup of free electrons and atomic nuclei. This transition from stable, low-energy particles to high-energy, interacting particles indicates that different rules may govern the universe at extreme temperatures. At the same time, relativity, which describes the behavior of objects on large scales and in strong gravitational fields, begins to play a more significant role. As temperature rises and particles gain energy, the gravitational forces at play may cause space-time to warp in ways that deviate from classical expectations. These alterations could result in scenarios where traditional gravitational limits no longer hold true, leading to a profound reshaping of our understanding of both matter and gravity. In a hotter universe, the relationship between energy and mass, as described by Einstein's theory of relativity, becomes even more crucial. As particles gain energy with rising temperatures, their effective mass increases, which could lead to shifts in the behavior of matter and the formation of cosmic structures. These changes might impact the way galaxies and black holes evolve, potentially altering their dynamics in ways we can't yet predict. Ultimately, the phase transitions that occur in such extreme environments may reveal entirely new interactions and phenomena, ones that have never been observed before. These revelations could significantly challenge our current understanding of the universe and push the boundaries of quantum mechanics and relativity. By developing new theories that better integrate these fundamental aspects of physics, we may eventually gain deeper insights into the rapidly changing nature of the universe. In the vastness of the cosmos, the conditions are so extreme that they give rise to environments and phenomena far beyond what we encounter on Earth. These conditions could spawn unique quantum states or even new types of particles that challenge our current models of physics. For instance, inside neutron stars, extremely dense remnants of dead stars, the matter behaves in ways we can barely comprehend. The density is so high that protons and electrons collapse into neutrons, forming a state of matter known as neutronium. This is a material unlike anything we encounter in our everyday world, highlighting the possibility that under extreme conditions, entirely new forms of matter could emerge. Similarly, in the environments surrounding black holes, or during the earliest moments of the universe, the laws of physics as we know them may not operate uniformly. Some scientists speculate that new particles could form in these extreme settings, leading to entirely new forms of matter and energy, ones that are currently foreign to our understanding of the universe. As we continue to explore these extremes, we inch ever closer to unveiling the mysteries of the universe's most fundamental workings. Moreover, within the vast and intricate realm of quantum mechanics, particles can exist in states so perplexing that they defy our conventional understanding. One such phenomenon, known as quantum entanglement, presents an astonishing scenario where particles become interconnected in a way that the state of one instantly influences the state of the other, no matter the distance between them. This phenomenon challenges the very concept of locality, suggesting that our reality operates on principles far beyond the scope of everyday experience. While we can only speculate on the unique quantum states and particles that might exist beyond the confines of Earth, the vastness of the universe undoubtedly holds the potential for phenomena that defy our deepest knowledge of matter and the laws that govern it. Such discoveries could propel us toward an entirely new era in physics, sparking fresh avenues of research and deeper understanding of the forces that shape the cosmos. As we turn our gaze to the earliest moments of the universe, shortly after the Big Bang, we encounter an environment where temperatures reached unimaginable extremes. In those first few seconds, the very fabric of reality was a chaotic and searing mass of energy. Under such intense heat, the laws of physics operated in ways drastically different from how we experience them today. To comprehend the impact of even the slightest increase in temperature on these laws, it helps to consider the fundamental forces that govern our universe. At high temperatures, particles gained extraordinary amounts of energy, enough to overcome the forces that normally keep them bound together. This scenario can be likened to a crowded dance floor, where the music begins to increase in volume. As the beats grow louder, everyone starts to move faster, unable to maintain their previous positions. In a similar fashion, the particles within the hot early universe began to move in such a way that new interactions and formations became possible, an environment where the usual laws of physics could no longer be taken for granted. One of the most significant outcomes of this heightened temperature was the potential for new states of matter to emerge. While we are familiar with the standard states, solid, liquid, gas, and plasma, the early universe, with its intense heat, may have fostered entirely different, exotic states of matter. A prime example of this is the quark-gluon plasma, a hot, dense soup of fundamental particles, which could have existed in the aftermath of the Big Bang. This state of matter, a primordial soup of quarks and gluons, was vastly different from anything we encounter today. In such an environment, the traditional forces, gravity, electromagnetism, and the strong and weak nuclear forces, would have behaved in unfamiliar ways, potentially exhibiting altered strengths or entirely new behaviors. The very laws that govern the interactions of matter might have fluctuated depending on the temperature and energy present, giving rise to completely new phenomena. Furthermore, theoretical physics posits that, under specific conditions, the physical constants, those immutable values that define the strength of forces like gravity or the electromagnetic force, might not be as constant as we assume. If temperature variations could push these constants outside their usual ranges, the entire dynamic of the universe could change. From the formation of stars to the collisions of galaxies, these altered constants could drastically reshape the cosmos. A small increase in temperature, it turns out, could have a profound impact, perhaps triggering the slow evolution of different physical conditions that lead to the creation of diverse cosmic structures. This scenario suggests that a seemingly insignificant change in temperature might serve as the catalyst for a process that not only redefines the nature of matter, but also reimagines the very nature of space and time itself. In this speculative view of the universe, the conditions that govern the formation and evolution of planets might also diverge dramatically from what we observe in our own cosmic neighborhood. In our universe, planets form within the gravitational influence of a star's surrounding disk of gas and dust, a process that occurs gradually over immense periods of time. As particles collide and coalesce, the conditions of temperature, pressure, and material composition play a crucial role in shaping the unique characteristics of each planet. However, in an alternate cosmic scenario where different types of stars or entirely different stellar configurations are at play, the processes that lead to planet formation could look vastly different. For example, if stars formed in irregular patterns or at different intervals, the gravitational forces acting upon the surrounding material would change, influencing how matter clumps together. This could lead to fewer planets forming overall, or to the rapid consolidation of material, resulting in larger, denser planets that may differ drastically from the ones we know. In such an environment, where the very elements that give rise to planetary systems may be altered or absent, the makeup of the planets themselves could be vastly different. Imagine a universe where the standard elements required for life as we know it, like carbon, oxygen, and nitrogen, are less abundant or entirely absent. The consequences of such a shift would be far-reaching, influencing everything from the composition of planets to the potential for life to emerge. Without these fundamental building blocks, the chemistry that forms the basis for life might not occur at all, or perhaps it would take an entirely different form, unlike anything we can currently imagine. This alternative cosmic scenario forces us to reconsider everything we know about planet formation, the development of life, and the evolution of the universe itself. As we continue to explore these vast, unknown frontiers, we may come to realize that the universe is not only stranger than we imagine, but stranger than we can even begin to comprehend. The study of such phenomena, both theoretical and observed, pushes the boundaries of our understanding and compels us to question the very nature of reality itself. The universe, it seems, may hold secrets that challenge the limits of our knowledge, waiting for us to unlock them and further our quest for truth. Moreover, geological processes such as volcanic activity, tectonic movement, and erosion would undergo dramatic transformations in this alternative cosmic scenario. A planet positioned closer to a hotter star might be subjected to fierce volcanic eruptions, with the searing heat perpetuating a landscape dominated by molten rock and eruptive activity. On the other hand, a planet located in the colder regions of its stellar system might remain in a frozen state for an extended period, perhaps even indefinitely. Such a world could develop icy surfaces with little to no geological changes over time, preserving a pristine, frozen landscape. The interaction between heat and the planet's geological activity would significantly impact the planet's appearance. A hotter planet, in particular, would likely experience more intense volcanic eruptions, which could continue shaping the surface for eons. These eruptions would release vast quantities of gases like carbon dioxide, water vapor, and sulfur, contributing to the planet's atmospheric composition. Over time, these gases could create a greenhouse effect, trapping heat and possibly allowing the planet to become even warmer and more volatile, perpetuating the cycle of geological upheaval. In contrast, a cooler planet might not have such active volcanic behavior, instead allowing more gradual processes like erosion or even the formation of vast ice sheets. Tectonic movements, if present at all, might be slower, and the surfaces might remain relatively undisturbed. Without intense geological forces at play, the landscapes of such a planet might appear static, with little to no significant transformation for millions of years. Even when change occurs, it could be subtle and almost imperceptible, resulting in vast stretches of frozen plains or ancient weathered mountains. Furthermore, the abundance and composition of gases and liquids, essential components of weather systems and erosion, would create vastly different atmospheres. For instance, a planet that lacks a dense atmosphere might develop a barren surface that remains virtually unchanged for millions of years. On the other hand, a planet with a thick, rich atmosphere could be continuously sculpted by the forces of wind, water, and temperature fluctuations. Over time, the surface could undergo radical transformations, with rivers carving deep valleys and winds eroding mountains into rolling hills. In this dynamic environment, the emergence of life would be influenced significantly by the planetary conditions. Some worlds might harbor thriving ecosystems, thanks to the ideal balance of temperature, water, and atmosphere. These planets could develop lush forests, diverse wildlife, and intricate food webs, benefiting from stable climates and abundant resources. In contrast, other planets could remain lifeless or develop entirely unique forms of life, adapted to the distinctive conditions of their environments. The path of evolution on these worlds could be shaped by factors such as extreme heat, perpetual darkness, or high radiation levels, leading to life forms unlike anything we might recognize on Earth. Thus, The formation and geological history of planets in such an alternative cosmic scenario would lead to a staggering variety of worlds. Each planet would be uniquely shaped not only by its formative processes, but also by the intricate interactions between the laws of physics and its surrounding environment. From fiery, molten worlds to frozen, lifeless planets, the possibilities would be as diverse as the stars themselves. Planetary atmospheres, too, could develop in fascinatingly unique ways, greatly influenced by the planet's initial heat conditions. When a planet forms, it gathers materials from the surrounding space, and the energy generated during this process can cause significant heating. This initial heat plays a crucial role in determining how gases accumulate and interact in the planet's atmosphere. For a planet that forms closer to its star, like Mercury in our solar system, the intense heat could lead to the formation of a thin atmosphere, primarily composed of lighter elements like hydrogen and helium. Over time, these elements might escape into space, leaving the planet with little to no atmosphere at all. In contrast, a planet farther from its star, such as Neptune, might retain heavier gases such as hydrogen and helium, resulting in a thick, dense atmosphere. The amount of heat present also influences how volatile compounds behave. Warmer conditions might favor the existence of gaseous forms of certain substances, while cooler conditions could allow liquids or even solids to remain stable. This, in turn, would impact the planet's surface features and its potential to support life. The initial heat of a planet also shapes its geological activity. A hotter planet is likely to be more geologically active, experiencing frequent volcanic eruptions that release gases into the atmosphere. These eruptions not only influence the atmosphere's composition, but also contribute to long-term climate patterns. Over time, these gases could alter the planet's climate by enhancing the greenhouse effect, leading to a hotter, more volatile environment. Thus, the initial heat of a planet sets the stage for the development of its atmosphere, geological activity, and overall habitability. This heat is not just a temporary factor. It shapes the ongoing interactions between a planet's surface and its atmosphere, influencing everything from cloud formation to volcanic activity. As the planet cools or heats over time, it creates a feedback loop that can either stabilize or radically alter its environmental conditions. Temperature plays an essential role in shaping the climates of planets. A shift in temperature can have a cascading effect on various aspects of a planet's climate system, including wind patterns, precipitation, and seasonal cycles. Imagine the surface of a planet as a blank canvas, where temperature is the artist. As the temperature increases, it provides more energy to the atmosphere, which can result in stronger winds, more intense storms, and altered precipitation patterns. Warmer temperatures often lead to an increase in water vapor in the atmosphere, which can create more humid conditions. This, in turn, can contribute to the formation of clouds, rain, and storms. On the other hand, a decrease in temperature can lead to the opposite effect. Cooler conditions might result in drier environments, with some regions experiencing severe droughts. In extreme cases, the water on the planet's surface could freeze, creating snow and ice where liquid water once flowed freely. These temperature shifts also influence the types of ecosystems that can thrive on a planet. Warmer climates, for example, might support lush forests, tropical rainforests, and diverse wildlife. Cooler conditions could lead to the development of tundras, deserts, or even frozen polar landscapes, each hosting unique flora and fauna adapted to the specific climate. In the end, the temperature of a planet doesn't just dictate its weather patterns, it influences the very nature of life that can exist there. Whether a planet is scorched by relentless heat or covered in ice, temperature is one of the key factors in determining the kind of world it will become. Temperature is an unseen force that has profound implications on the existence and evolution of life, influencing not just the ecosystems we are familiar with, but also the very foundations of the cosmos itself. Beyond Earth, the way temperature interacts with other elements, such as atmospheric composition and the proximity of a planet to a sun-like star, creates a complex web of conditions that can lead to radically different environments. The extreme temperatures of different worlds can shape environments that foster unimaginable forms of life. In the warmth of certain planets, creatures capable of flight might thrive. while resilient plant life could flourish in cold, harsh regions, a testament to life's adaptability to diverse climates. However, it's not just the temperature itself that matters. It's how temperature shifts interact with everything else. Each planet has its own unique set of conditions that can produce some of the most extreme and unpredictable climates in the universe. From the blistering winds of a desert world to the frozen expanse of an ice-covered planet, the interplay of these conditions is what fuels the incredible diversity of planetary environments. Grasping how temperature shifts influence the development of climates is key to understanding the broader picture of how a planet's conditions evolve and whether or how life might emerge in these extraordinary environments. Moreover, the concept of a hotter early universe expands our understanding of everything we know about the cosmos. It provides insight into the Big Bang, the moment when the universe began its vast expansion from a singular point filled with intense heat and energy. In those first moments, the universe was unimaginably dense and hot, conditions that eventually cooled to give birth to the galaxies, stars, and planets we observe today. The idea that the early universe could have been even hotter opens up the possibility of multiple universes, an interconnected multiverse. The hotter the initial conditions, the more likely it becomes that multiple varied universes could have formed in parallel, each with its own set of physical laws and unique characteristics. The theory of the multiverse suggests that there could be a multitude of universes, each shaped by tiny variations in the fundamental forces at play during the earliest moments of existence. If the early universe was indeed hotter, that could mean there were more opportunities for different types of universes to emerge, each with its own rules, laws, and dynamics. High temperatures might have facilitated a greater variety of energy states, leading to diverse cosmic regions, each with different trajectories, potentially resulting in universes where time and space unfold differently than in our own. This concept also ties into the idea of inflation, the rapid expansion of the universe after the Big Bang. Variations in inflationary processes could result in regions where the universe expanded differently, generating multiple universes with distinct properties. A hotter early universe could have accelerated this process, spawning a cosmic landscape filled with an infinite array of realities. This raises a profound question. Is our universe an anomaly, an outlier with unique properties? Or is it just one of countless other universes that emerged from that fiery early moment, each one charting its own unique course in the vast cosmic narrative? As temperatures rise, so too does the potential for the birth of new universes. Consider the fabric of space as a dynamic, malleable entity, stretching and bending under the influence of various forces. When temperatures increase within a specific region of space, the energy levels surge, creating the perfect environment for singularities, regions of incredibly high density and energy, to expand. In these singularities, the conditions may be ripe for the formation of new universes, much like bubbles emerging from boiling water. Each bubble would be unique, shaped by the specific conditions that brought it into being. In this conceptual framework, the interaction of temperature with the fundamental forces of nature could give rise to universes with different physical laws or properties. Just as the early moments of our universe gave rise to rapid expansion, higher temperatures in other regions could lead to similar processes, where the rapid cooling and subsequent formation of matter from energy could occur. However, the stability of these new universes would depend entirely on their initial conditions. Some might develop into stable systems, while others might collapse into chaos, never fully forming. Understanding how temperature influences this process is key to unlocking the mysteries of how universes are born and evolve. Additionally, temperature plays a crucial role in the interaction between distinct universes within the multiverse. If space and time are understood as a fabric that can warp and stretch, temperature changes could, in theory, create openings or connections between these separate bubbles or universes. Such interactions could allow for the transfer of energy or information between different realms, leading to a fascinating concept known as overlap. Though this idea is speculative and remains in the realm of theoretical physics, it opens up a tantalizing possibility. Universes may not be completely isolated from one another, and under the right conditions, They could touch, overlap, or influence one another in ways we don't yet understand. Yet, while this concept remains hypothetical, it challenges the very nature of existence as we know it, pushing our imagination and understanding of the cosmos to its limits. The idea of the multiverse, where multiple realities might coexist, each one governed by different sets of rules, raises questions about the fundamental nature of reality. It invites us to ask, what if there are infinite versions of ourselves, living out countless alternate lives in parallel worlds? Furthermore, the elusive concept of dark matter plays a pivotal role in shaping the universe, despite its invisibility. Dark matter is a mysterious substance that, although it does not emit light, exerts gravitational influence on visible matter, acting as the unseen scaffolding of galaxies and galaxy clusters. The early temperature of the universe had a profound impact on how dark matter interacted with the rest of the cosmos. If the early universe had been hotter, particles would have moved more energetically, creating more turbulence in the formation of cosmic structures like galaxies. This increased turbulence could have led to dark matter behaving in different ways, potentially altering how galaxies formed. In a hotter universe, higher energy levels might have accelerated the clustering of dark matter, pulling in ordinary matter to form galaxies more rapidly. Alternatively, if the universe had started cooler, the opposite effect might have occurred, with particles moving slower and dark matter clustering less efficiently. This difference could result in galaxies forming more slowly, or in entirely different structures emerging. The properties of dark matter would therefore depend on the initial conditions of the universe, shaping the distribution and formation of cosmic structures over billions of years. The influence of temperature on dark energy also warrants attention. Dark energy is the mysterious force responsible for accelerating the expansion of the universe. In a hotter universe, temperature shifts could alter how dark energy behaves, potentially affecting the rate at which the universe expands. If temperatures were higher, the increased energy might alter the dynamics of particles and the way dark energy interacts with matter. This could result in a universe where cosmic expansion is either slowed down or accelerated, with profound implications for the formation of structures like galaxies and clusters. In a warmer universe, dark energy might behave differently, potentially leading to different outcomes in the way galaxies form and cluster. This raises the possibility of a universe where the formation of large-scale structures is fundamentally altered. Perhaps fewer or smaller galaxies would emerge, influenced by the higher energy levels affecting gravitational forces. Thus, temperature not only shapes the formation of structures in our own universe, but it also hints at the profound ways in which the fundamental forces of the cosmos interact with each other, creating the vast and intricate web of existence that we continue to study and explore. The expansion rate of the universe is intricately tied to its temperature, and fluctuations in temperature might have profound effects on the behavior of the cosmos. As the temperature rises, we could witness increasingly energetic phenomena, possibly leading to shifts in the way the universe expands. This connection prompts scientists to consider how dark energy might interact with an energized universe. In such a scenario, the rate at which the universe expands could fluctuate, either accelerating further or decelerating depending on the interplay between dark energy and heat. If the balance between these forces shifts unfavorably, the expansion of the universe could experience a sudden slowdown, dramatically altering our perception of cosmic evolution. The potential for accelerated expansion in an increasingly heated universe opens a gateway to numerous theories and models, each demanding further investigation. These theories not only enhance our understanding of dark energy, but also prompt deeper reflection on the fundamental forces that govern the cosmos and shape its ultimate destiny. As the universe evolves, it undergoes transformative processes, with temperature fluctuations playing a pivotal role. Among the most intriguing consequences of these changes are the effects they could have on dark matter. Currently, dark matter is one of the most mysterious and elusive components of the universe. It doesn't emit, absorb, or reflect light, making it almost impossible to detect. Yet astronomers believe that dark matter constitutes a significant portion of the universe's total mass. When considering heat increases in the cosmos, especially during dramatic events such as galaxy cluster collisions or the intense energy released by supernova, we step into a realm of intriguing possibilities. These heating events could influence the behavior of subatomic particles, potentially unlocking new forms of dark matter. Higher temperatures could facilitate the creation of new particle types, ones that may not have existed in the cooler early universe. These particles might even be classified as dark matter, offering scientists novel clues that could help reveal the true nature of this mysterious substance. Moreover, as the universe cools after such events, it is possible that previously hidden characteristics of dark matter will come to light. The intricate relationship between heat and particle interactions holds the key to groundbreaking discoveries. While the exact nature of dark matter remains uncertain, the exploration of these high-energy phenomena may lead to the emergence of new forms of matter that could fill in some of the missing pieces in our understanding of the universe's fundamental composition. In a parallel universe, conditions might favor a whole different spectrum of cosmic events, occurring at a far more frequent rate than in our own. Imagine a universe where the life cycles of massive stars are dramatically altered, leading to a larger number of supernova, spectacular explosions marking the violent death of a star. In this alternate reality, these events could occur far more often, resulting in bursts of light so intense they would momentarily outshine entire galaxies. The increased frequency of supernovae would offer researchers unparalleled opportunities to study the explosive processes of stellar collapse and the energetic transformations that shape the very fabric of the universe. Additionally, in such a universe, the density of stars might be much higher, creating the perfect conditions for more frequent neutron-star mergers. These rare and cataclysmic events result in the production of heavy elements like gold and platinum, as well as the generation of gravitational waves, ripples in the fabric of space-time itself. The higher frequency of these mergers would present a unique chance to study the fundamental forces of nature, such as the strong nuclear force and the dynamics of matter under extreme conditions, shedding light on the creation of elements that populate the universe. Black holes could play a far more dynamic role in this alternate cosmos, too. The paths of stars, gas clouds, and other celestial objects might be shaped by gravitational forces that lead to more frequent collisions between black holes or even the formation of supermassive black holes. When these black holes merge, they release energy in the form of gravitational waves, disrupting the very structure of space-time. These collisions could offer unprecedented insight into the nature of black holes and their effect on the cosmic landscape. Furthermore, such black hole mergers might also contribute to the acceleration of galaxy formation, creating a rich and diverse array of cosmic structures that could provide deeper understanding of galactic evolution. Gamma-ray bursts, among the most energetic explosions in the universe, could also be more common in this alternate universe. These high-energy events, typically associated with the collapse of massive stars or the merging of neutron stars, release immense quantities of radiation in the form of gamma rays. If the conditions favor rapid star formation, gamma-ray bursts could become a routine feature of the cosmos, offering astronomers a glimpse into the most intense processes that power the universe's most energetic phenomena. The fabric of the universe itself might be altered by heat levels, too. Exotic cosmic structures such as filaments, vast strings of matter connecting galaxies, could take on more intricate and pronounced forms. Gravitational forces might give rise to large-scale structures of unprecedented complexity, reshaping how galaxies interact and evolve over time. These shifts could also affect how dark matter influences the formation and behavior of these cosmic structures, leading to new insights into the role of unseen matter in shaping the cosmos. In such a universe, cosmic events such as supernovae and gamma-ray bursts would not only be more frequent, but would also behave differently in response to their environmental conditions. A supernova, for instance, is an explosive event that occurs when a star exhausts its nuclear fuel, causing it to collapse under its own gravity. This catastrophic collapse releases an enormous amount of energy in the form of light, heat, and radiation. In a universe with higher temperatures, these events could be influenced by the surrounding gas and dust, potentially altering their interactions with the environment and affecting the light curves observed by astronomers. These changes could lead to the creation of more complex and varied phenomena, further deepening our understanding of the processes at play in these explosive events. Similarly, gamma-ray bursts, intense, high-energy explosions, are produced by cataclysmic events such as the merging of neutron stars or the collapse of massive stars. In a universe with altered heat levels, the environment surrounding these events could influence the direction and intensity of the gamma-ray jets that emerge, impacting the spectrum of radiation observed. These fluctuations in energy release would contribute to the dynamic nature of the cosmos, highlighting how temperature and pressure variations can reshape the observable phenomena associated with these cataclysmic events. As we explore the possibilities of such a universe, it becomes clear that extreme cosmic phenomena, like quasars and pulsars, could also evolve over vast timescales. Quasars, bright objects powered by supermassive black holes at the centers of distant galaxies, could become even more pronounced as the conditions for star formation change. Pulsars, rapidly rotating neutron stars that emit beams of radiation, might also undergo shifts in their behavior, providing new insights into the fundamental forces that govern the universe. For spacefaring species, navigating such an altered universe would present both immense challenges and unique opportunities. High levels of cosmic radiation, for example, would pose significant health risks to living beings aboard spacecraft, potentially damaging their biological systems and electronic equipment. To counter these dangers, species might develop advanced shielding technologies or biological adaptations that enable them to survive in this hazardous environment. Furthermore, the lower gravity of distant asteroids or moons might offer advantages in terms of physical labor, though prolonged exposure to such low-gravity environments could lead to muscle and bone density loss. As a result, these species would need to develop specialized habitats that mimic the gravitational conditions of their home planets to ensure their long-term health and survival. Ultimately, exploring these dynamic and unpredictable changes in the universe opens the door to new questions about the forces that shape the cosmos. As we continue to unravel the mysteries of dark matter, dark energy, and the universe's vast array of cosmic phenomena, we will gain deeper insights into the fundamental nature of existence itself. This journey not only reshapes our understanding of the universe, but also beckons humanity toward the edge of discovery, where new realms of knowledge await. Altered cosmic conditions possess the potential to create planets that are teeming with rich resources, granting spacefaring species unexpected advantages. These new worlds, shaped by the unique forces of the cosmos, could serve as vital assets for civilizations exploring the vast reaches of space. Consider, for instance, a planet abundant in water ice and possessing a stable atmosphere. Such a world could become a crucial way station, offering both refueling and resupplying services to ships embarking on long, arduous journeys across the stars. The ability to access these resources on demand would significantly lessen the need for spacecraft to carry the entirety of their supplies for an entire voyage, alleviating the burden of extensive storage and logistics. However, the expanse of space is not always so welcoming. Certain regions are marked by extreme phenomena, nebulae, wormholes, and other cosmic anomalies that introduce a high level of unpredictability. Nebulae, dense clouds of gas and dust, obscure the clarity of space, while wormholes, though potentially shortcuts through space, come with the risk of unstable energy fields that could disrupt even the most advanced systems. These chaotic environments create challenges for spacefarers, forcing them to constantly adapt their technologies and refine their navigation systems. In these unpredictable regions, traditional methods may fall short, and only the most innovative minds can find ways to thrive. The constant interplay of obstacles and opportunities in these altered cosmic environments shapes the evolution of spacefaring species. With each challenge faced, there is an opportunity for growth, for the development of new technologies and strategies that may lead to significant advancements in both engineering and biology. Each new hurdle conquered by these civilizations could propel them closer to mastering the vastness of the universe, unlocking secrets of energy, propulsion, and life itself. The potential for innovation and adaptation, spurred by the environment's demands, becomes the driving force behind technological breakthroughs, enabling species to overcome the vast distances and dangers of space. In the current scope of our understanding, the limitations of propulsion and energy sources are tied to the fundamental laws of physics. These laws govern everything from the speed of light to the forces of gravity and the nature of energy. But if we consider hypothetical scenarios, alternate realities, or the far distant future, our imagination begins to stretch the boundaries of what we know. Imagine for a moment a universe where the rules of physics are subtly altered, where gravity might be weaker or stronger, where particles behave in strange and unexpected ways. Such a universe could foster entirely new methods of propulsion, and with it, a revolution in space travel. For example, in a universe where gravity were weaker, the challenges of escaping a planet's gravitational pull would be diminished. Advanced spacefaring civilizations might develop propulsion systems that glide or float, leveraging the weak gravity to harness energy from celestial bodies more easily. These systems would require far less energy than those currently designed to overcome the strong gravitational forces we experience today. On the flip side, if gravity were stronger, civilizations might need to rethink their energy sources entirely, potentially relying on new forms of propulsion that manipulate gravity itself. The very fabric of the universe could also offer new avenues for exploration and innovation. Exotic materials, not found in our own reality, might exist in alternate universes. These materials could have strange properties. Perhaps they are able to conduct energy in ways that ordinary matter cannot. With such resources, spacefaring species could develop propulsion systems that harness the unique characteristics of these materials, creating engines that produce far more energy than we can currently conceive. Imagine a propulsion system that taps into these exotic particles, generating energy with an efficiency that defies everything we currently understand about energy and mechanics. Perhaps even more tantalizing is the idea of extracting energy directly from the very fabric of space-time itself. In such a scenario, a civilization might harness the energy generated by black holes, which possess incredibly powerful gravitational fields. These black holes, often seen as the cosmic endpoints where matter and light are swallowed up, could become a source of immense energy. Though this remains largely theoretical, the very concept excites scientists and engineers. What if we could use the powerful gravitational forces around a black hole to extract energy? This type of energy harvesting could potentially revolutionize the way we think about energy production, offering us access to limitless sources of power. While our current limitations are grounded in the established laws of physics, the possibilities opened by hypothetical or altered realities offer pathways to unimaginable breakthroughs. The exploration of such possibilities can redefine what is achievable in terms of travel, energy consumption, and even the nature of existence itself. As we broaden our understanding of how different physical conditions might shape the universe, we realize that the cosmos is far more vast and mysterious than we could ever have imagined, and the potential for discovery seems limitless. As humanity looks beyond the familiar to explore the unknown, our strategies and technologies must evolve accordingly. Instead of relying on traditional spacecraft built primarily for travel, future expeditions may place greater emphasis on adaptable vehicles, vessels capable of changing their form and function based on the environment they encounter. Such adaptability would make these ships more efficient, allowing them to respond in real time to varying gravitational fields, atmospheric conditions, and other unique factors found on distant worlds. By making these vessels more versatile, spacefaring civilizations could increase their chances of survival and success during missions to unfamiliar and potentially hostile environments. Moreover, the role of robotic explorers is set to become increasingly important. In the coming years, unmanned probes equipped with sophisticated artificial intelligence will take the lead in exploring distant corners of the universe. These robots will gather vital data, analyzing their surroundings and making decisions on the fly based on real-time information. This flexibility, coupled with the ability to learn and adapt, will make them invaluable assets. The importance of human safety will remain a priority, and robotic explorers will help mitigate risks by conducting preliminary surveys of potentially dangerous environments. As humanity ventures further into space, communication technology will need to advance at a rapid pace. The vast distances involved will create delays, sometimes taking months or even years for messages to travel from one end of the universe to another. To address this challenge, innovations like relay networks or dedicated communication satellites positioned strategically across the cosmos could ensure that data travels swiftly and reliably. Additionally, enhanced algorithms could allow for the compression of data into smaller packets, making it easier to send information even across vast stretches of space. One of the most exciting possibilities involves utilizing local resources during space missions. Instead of sending all the supplies needed for an expedition from Earth, astronauts could rely on in-situ resource utilization. By extracting fuel, water, and even building materials from the planets and moons they visit, astronauts could sustain themselves without the need for a constant flow of supplies from Earth. This approach not only reduces the logistical burden and costs associated with space travel, but it also enhances the sustainability of long-term missions. In this brave new age of space exploration, global cooperation will be essential. The future of space is a shared endeavor. No single nation can conquer the cosmos alone. Pooling resources, knowledge, and expertise will allow humanity to craft more effective strategies for exploration, development, and understanding. Joint missions could combine the strengths of various nations, incorporating diverse technologies and strategies. This collaboration could bring us closer to solving the mysteries of the universe and unlocking the secrets of life beyond Earth. As we adapt our exploration strategies and technologies to the unique conditions of the universe, we open the door to a new era of discovery. By developing flexible ships, harnessing robotic assistance, advancing communication technologies, utilizing local resources, and fostering international collaboration, humanity can embark on an extraordinary journey into the cosmos. The wonders of the universe are vast and awe-inspiring, offering untold stories, beliefs, and mythologies for those who choose to observe and interpret them. Imagine a reality where stars are born in extraordinary, spectacular ways, or where entire galaxies collide in an immense cosmic spectacle. For sentient beings in such a universe, these events might serve as pivotal moments in their understanding of existence. Celestial occurrences like supernovae, massive explosions marking the death of a star, might be seen as messengers, symbols of transformation and rebirth. The sudden brilliance of a supernova could be interpreted as a sign of hope, inspiring civilizations to create rituals to honor the memory of the fallen celestial entity. Similarly, deep, dark nebulae, vast clouds of gas and dust, could become sources of wisdom in certain societies. Their inhabitants might see these nebulae as guardians of knowledge, leading to belief systems centered on learning and introspection. Such societies might even organize their calendar around the cycles of these nebulae, celebrating certain times of the year when the clouds are most visible. In this way, their lives would align with the cosmic rhythms, reinforcing their connection to the greater universe. Finally, civilizations living near black holes might craft rich mythologies centered around balance and the unknown. The black hole, with its dual nature as both creator and destroyer, could inspire tales of courage and resilience. Myths could describe journeys across the event horizon, the point of no return, where life and oblivion meet. These civilizations would teach their descendants to embrace the unknown and face the unimaginable with courage, forever shaping their view of the cosmos as a place of infinite mystery and potential. The vastness of the cosmos holds an infinite number of possibilities, each celestial body and every stellar event potentially sparking the imaginations of sentient beings. If the distances between these celestial bodies were vastly different, entire mythologies and legends might emerge, inspired by the journeys to far-off realms. The belief in exploration and discovery could permeate societies, encouraging curiosity, bravery, and a relentless pursuit of the unknown. These beings, driven by the allure of distant stars and planets, would likely weave tales of heroism and adventure that center around those who dared to venture beyond the familiar, driven by the belief that the universe held untold mysteries, waiting to be uncovered. In such a universe, the celestial landscape itself would become a canvas for the imagination. Each cosmic event, a shooting star, a distant nova, or the quiet flicker of a new constellation, would transform into a tapestry of beliefs and stories, shaping how beings understand their place in the vast expanse of space. The stars would no longer be mere points of light. They would be living symbols, each carrying its own meaning and significance. The intricate interplay between celestial phenomena and cultural narratives would influence everything from spiritual beliefs to daily practices, ensuring that the universe was not just a backdrop for life, but an active participant in shaping it. Every stellar occurrence would ignite fires of interpretation. For ancient civilizations, the night sky was not simply a source of wonder, but a guide, an ever-present influence on everything from agriculture to governance. Imagine, for instance, the dazzling trail of meteors streaking across the heavens. In early societies, these brilliant displays might be seen as divine omens, heralding the arrival of gods or signaling impending changes in the world below. These cosmic occurrences would not just be awe-inspiring spectacles, they would be interpreted as messages, sacred communications from the heavens that could alter the course of history. In many cultures, such events were not only observed but revered, deeply interwoven with the collective consciousness and spiritual practices of the people. Consider the cataclysmic brilliance of a supernova, the death of a massive star in a brilliant explosion of light. This awe-inspiring event, marking the end of a star's life cycle, could easily be interpreted as a symbol of transformation. For some, it might represent the death of the old and the birth of the new, a harbinger of rebirth and change, while for others, it could signify the inevitable end of an era. As the light from a supernova travels across vast distances to reach distant worlds, the story it tells may echo themes of destruction, renewal, and the cyclical nature of existence. Such events, grand and fleeting, would stir emotions and spark myths that transcend generations. Eclipses, too, have left an indelible mark on human imagination. The temporary darkening of the sun or moon is not just a visual phenomenon, but an event that has long stirred fear, awe, and speculation. Ancient peoples often interpreted these rare occurrences as battles between celestial beings, divine forces locked in conflict that held profound significance for the people of Earth. These stories, steeped in myth, would help to explain and contextualize the unusual, offering comfort or guidance during times of uncertainty. Eclipses were not just astronomical events. They were spiritual crossroads, moments when the veil between the earthly and the divine seemed to thin. As ancient cultures charted the movements of celestial bodies, they began to notice patterns, celestial rhythms that governed the passage of time. Calendars based on the positions of the stars and planets became essential tools for everything from agricultural practices to religious observances. These cosmic calendars formed the backbone of societies, dictating the ebb and flow of life. In this way, celestial events, whether they were regular or rare, were inextricably tied to the daily lives of ancient peoples. They became markers of time, indicators of prosperity or calamity, and points of spiritual reflection. The significance of the cosmos was not limited to the tangible. It was also profoundly symbolic. The stars themselves were often seen as more than just lights in the sky. Constellations, patterns of stars that seemed to form coherent shapes, became symbols of power, wisdom, or courage. They were stories etched in the sky, each constellation telling its own tale. Ancient civilizations often used these constellations for navigation, relying on the stable positions of certain stars to guide them across vast oceans. The North Star, for instance, became a fixed point in the sky for sailors, offering guidance and certainty in an otherwise unpredictable sea. Yet, while constellations held their place as constant guides, the more dynamic and fleeting celestial phenomena held a different kind of power. Comets, for example, streak across the night sky with an intensity and speed that leave observers with a sense of awe and wonder. These bright, blazing objects often seem to appear out of nowhere, only to vanish just as quickly. The suddenness and unpredictability of such events imbued them with a sense of magic, as if they were messengers from another world. Historically, comets have been seen as omens, signaling significant events or changes. In some cultures, the appearance of a comet was believed to announce the arrival of a great leader, the fall of an empire, or a new era of human history. Solar eclipses, too, evoke a unique emotional response. The temporary darkening of the sun or moon creates a rare moment of transformation in the sky. These events have often been interpreted as signals of impending change, or as moments of divine intervention. Their rarity, combined with the dramatic shift in light, makes them unforgettable experiences, etched into the memories of those who witness them. The awe they inspire is a reminder of how even the most predictable patterns of nature can carry an air of mystery and wonder. This interplay between constellations and celestial phenomena reveals a deeper connection between humanity and the cosmos. While the stability of constellations provides a sense of continuity and permanence, the fleeting nature of phenomena like comets and eclipses offers moments of clarity and revelation. Both hold their place in the human psyche, guiding individuals through the passage of time, whether by providing a constant point of reference or by illuminating the sky with a momentary burst of light. Now, imagine a universe where conditions were drastically different in the early stages of planetary formation. What if the universe was significantly warmer during this critical period? A hotter environment could offer new possibilities for the emergence of life. Molecules essential for life, such as proteins and nucleic acids, might form more easily, leading to the rapid development of life forms. In such a world, civilizations could arise much earlier in the planet's history, potentially possessing technologies far beyond anything humanity could currently conceive. These civilizations, born in an environment where energy was abundant and easily harnessed, might develop technologies that seem like magic to us. Machines capable of manipulating energy, bending space-time, or even altering the very fabric of consciousness itself. Socially, these civilizations might look vastly different from our own. With resources in abundance, competition for survival could become less of a driving force. Instead, these societies might prioritize collective well-being, focusing on sustainability and harmony with their environments. In this utopian setting, knowledge sharing might replace the pursuit of individual wealth, and advancements could be aimed at improving the quality of life for all. Conversely, if the environment were unstable, civilizations might develop highly adaptable social structures, ones that prioritize resilience and constant innovation as survival strategies. These civilizations, shaped by the unique conditions of their home worlds, would likely see the universe through a different lens. Where humans view the stars as distant and cold, they might see them as beacons of opportunity and enlightenment. Their understanding of the cosmos would be based not on fear or superstition, but on a deep, intimate knowledge of the forces that shape their existence. The myths and stories they would create would reflect their advanced understanding, weaving together science, spirituality, and art in ways that humanity can only dream of today. Thus, the story of the cosmos is not just one of cold, indifferent science. It is a story of wonder, of human curiosity, of the ceaseless desire to understand and explain the universe. From the distant stars to the fleeting comets, the celestial realm continues to inspire, guiding cultures, shaping beliefs, and fueling the imagination of all who look up at the night sky. Communication methods could evolve in response to their environment, adapting in ways that are unimaginable to us. For example, if an extraterrestrial atmosphere were to differ significantly from ours, their systems of communication might take on entirely unique forms, such as intricate light patterns or sound frequencies designed to convey meaning across vast distances. These methods would likely transcend our basic concept of language, pushing the boundaries of how we understand interaction. In such an environment, language would no longer be confined to mere words, but could involve complex signals that are visual, auditory, and perhaps even tactile, broadening our understanding of communication's role in society. Their understanding of the universe would also be shaped by the physical and cosmic conditions surrounding them, leading to spiritual and philosophical systems that are far removed from human concepts. These civilizations might explore ideas of existence, consciousness, and reality in ways that challenge or even completely dismantle our human-centered worldview. Their philosophies could include beliefs about the nature of the universe that might seem unrecognizable or alien to us. These unique perspectives would inevitably prompt profound questions about the very fabric of reality, sparking debates and revelations that have never crossed our minds. A hotter start to the universe might also catalyze civilizations that operate on principles and technologies beyond our comprehension. The conditions of their early environment could have led them to develop entirely unfamiliar approaches to energy, survival, and society. Technologies that harness energy from sources we have yet to even consider, as well as social structures that prioritize sustainability over competition, would flourish in such a world. The diversity of life forms and intelligences in the cosmos could be far greater than we ever imagined, showcasing an extraordinary range of possibilities for life beyond Earth. In space, civilizations could exploit residual cosmic heat in ways that we are only beginning to understand. This heat, which originates from the early universe and continues through processes like the decay of radioactive elements and thermal emissions from celestial bodies, offers vast energy potential. Rather than relying on the direct energy of a nearby star, these civilizations could design systems that harvest the faint, almost imperceptible heat that permeates the universe. Picture solar panels that do not merely capture sunlight, but are tailored to absorb the subtle thermal radiation that spreads through the cosmos. These specialized materials could convert extremely low levels of heat into usable energy, powering their technologies in environments where sunlight is a distant memory. Additionally, the ability to harness energy through geothermal means could be taken to an entirely new level. Much like the geothermal energy systems on Earth, these civilizations could tap into the heat of nearby stars or planets, converting thermal energy directly into electricity. This method would not only support their energy needs, but also open up avenues for the development of technologies in heating, cooling, and propulsion that are far more advanced than anything currently available on Earth. The ability to harvest and manipulate cosmic heat would be integral to their continued growth, enabling them to survive and thrive in environments that humans might find inhospitable. Life support systems in these civilizations would also benefit from the advanced management of thermal energy. Excess heat generated by machinery or even the activities of the inhabitants could be stored and redistributed when needed. With advanced insulation techniques, they could preserve this heat and use it during colder periods, effectively recycling it to maintain a steady and sustainable temperature. This form of heat recycling would not only reduce the need for additional energy sources, but could also enable these civilizations to live in harmony with their environment, making them resilient even in the harshest conditions. In some of the more extreme regions of space where residual heat is abundant, advanced civilizations might turn to thermoelectric principles. By creating materials that efficiently convert temperature differences into electricity, they could develop self-sustaining energy systems that operate independent of traditional power sources. In such environments, technologies would evolve to thrive on this basic yet abundant energy resource, leading to a stable and reliable foundation for societal development. Through the integration of these technologies, civilizations would cultivate a sustainable way of life, supported by the very heat that permeates the cosmos. The profound impact of a dramatically different universe would not only be felt in technological and environmental shifts, but also in the way these civilizations understand their place in the cosmos. If physical laws varied from what we know, if gravity were weaker or time flowed differently, it would not just be a scientific curiosity. It would fundamentally alter the way that these societies are structured and how their inhabitants perceive existence itself. For instance, in a universe where resources are abundant and energy is easily accessible, the traditional notions of competition, scarcity, and individual ownership might dissipate. In such a society, collaboration and sustainability would likely replace conflict and exploitation as the foundational principles of social organization. With this abundance, societies might prioritize long-term planning, cooperation, and the collective good over the short-term gains that often dominate in more resource-scarce environments. New forms of governance could emerge, where decisions are made not by the few but by the collective, based on the needs of the entire community. The way in which knowledge, stories, and cultural traditions are shared might also evolve, as these civilizations come together to explore their new realities. Cultural identity could become deeply intertwined with the shared experiences of living in a world so different from anything humanity has encountered. On a philosophical level, a universe with altered physical laws would inevitably lead to a re-examination of the nature of life and consciousness. With new variables at play, the boundaries of life as we know it could expand to include forms of existence and intelligence that we cannot even imagine. This would challenge the human-centric views of intelligence, possibly redefining what it means to be alive. The discovery of life forms with completely different cognitive structures or biological processes could spark a revolution in our understanding of what intelligence truly means, leading to new ethical considerations about how we interact with other sentient beings. These encounters with alien life could also lead to profound philosophical debates about the interconnectedness of all beings in the universe. If life is not an isolated phenomenon, but rather part of a grander, more universal system, what does that mean for our understanding of existence? What is our place in this cosmic web? These questions would challenge humanity to reconsider its relationship with the cosmos, and might even lead to a rethinking of our place in the grand narrative of the universe. Spirituality could also undergo a transformation. New cosmic phenomena, from strange celestial events to entirely new forms of matter or energy, could inspire awe and reverence in ways that are not currently possible. Civilizations might not only look to the universe for answers, but begin to see it as a living, breathing entity with which they are deeply connected. This could spark the creation of new belief systems that see the cosmos not merely as a backdrop for human activity, but as a dynamic, ever-changing force that shapes and sustains life. The resurgence or reinterpretation of spiritual practices could arise from this, reflecting a deeper understanding of the interconnectedness of all life and energy in the universe. Ultimately, inhabiting such a radically altered universe would offer more than just the opportunity for survival. It would provide a vast canvas upon which civilizations could redefine themselves. In the process, they would reimagine their culture, philosophy, and identity as they seek to understand their place in a reality so different from the one they knew. The challenges posed by this new reality would not just be about adapting to survive, but about forging new paths of growth, cooperation, and discovery. The temperature of the cosmos plays a pivotal role in shaping the conditions that give rise to life and energy. Just as the heat in a kitchen affects the cooking process, the cosmic temperature dictates the processes that form the elements and materials essential for life. In the earliest moments of the universe, the temperature was so high that atoms and matter could not even form. As it cooled, the building blocks of stars and galaxies, hydrogen and helium, came into existence, setting the stage for the creation of the universe as we know it. Stars began to form, igniting nuclear fusion and producing vast amounts of energy in the process. As these stars lived and died, they expelled matter into the surrounding space, enriching it with heavier elements like carbon, oxygen, and iron. These elements would eventually form planets and other celestial bodies, giving rise to the resources necessary for life. On Earth, this process led to the formation of coal, oil, and natural gas, crucial resources for our modern world. However, if the temperature of the cosmos were to change, whether by cooling or heating, it would have a profound impact on this entire sequence. A cooler universe might slow or even stop the formation of new stars, limiting the availability of heavy elements necessary for the creation of planets and life. On the other hand, a hotter universe could accelerate star formation, leading to rapid changes in the cosmic landscape. However, this might also create an environment where resources are destroyed before they have a chance to solidify into usable forms, hindering the development of complex life. In the end, the temperature of the cosmos is not just a background factor in the universe's formation. It is an active force that shapes the very foundation of existence. Its influence extends far beyond the formation of stars and planets, affecting the very processes that lead to the creation of life itself. Whether the universe is hotter or cooler, its temperature will continue to shape the future of civilization in ways that we are only beginning to understand. Temperature fluctuations across the vast expanses of space have profound effects on the distribution of resources throughout galaxies, particularly in areas where thermal conditions vary significantly. In regions with elevated temperatures, stars are likely to form at an accelerated pace, driven by the abundance of energy. On the other hand, cooler areas of the universe may lack the necessary conditions for star formation, which could slow down or even halt the birth of new stellar bodies. The dynamics of gravity and radiation pressure also play pivotal roles in shaping the cosmos. Areas rich in energy have a tendency to attract more matter, becoming focal points of resource accumulation. These energy-rich regions act as hotspots, driving the uneven distribution of materials across the universe. Ultimately, the temperature of space does more than merely influence the formation of stars and planets. It has far-reaching consequences for where and how energy-dense resources come together. Understanding the intricate interplay between temperature, gravity, and radiation pressure is key to unraveling the cosmic dance that governs the universe's resource landscape. This relationship holds even greater significance when viewed through the lens of the early universe, shortly after the Big Bang. The infant universe was an inferno, an intensely hot and dense environment where energy manifested in forms that seem strange to us today. During these primordial moments, thermal energy became one of the most significant forces shaping the cosmos. Thermal energy, generated by particles moving at staggering velocities, gave rise to the universe's most fundamental building blocks. Quarks and electrons emerged first, followed by protons and neutrons as the universe continued to expand and cool. Over time, these subatomic particles began to coalesce into atoms, predominantly hydrogen and helium, setting the stage for the formation of the first stars and galaxies. As the universe evolved, another form of energy, nuclear energy, came to the forefront, powering the stars through nuclear fusion. In the cores of these stars, immense gravitational forces cause lighter elements to fuse, forming heavier elements and releasing vast amounts of energy in the process. This is the very energy that fuels stars, including our own sun. However, beyond these well-known forms of energy, the early universe may have given rise to more exotic sources of energy, which remain theoretical to this day. One of the most enigmatic of these is dark energy. Thought to comprise a significant portion of the universe's total energy content, dark energy is believed to be responsible for the accelerated expansion of the cosmos. Despite its ubiquity, dark energy remains poorly understood, and its origins may trace back to the universe's hot, dense beginnings. Some scientists speculate that other, yet-to-be-discovered forms of energy could also have emerged from the extreme conditions of the early universe. Concepts like quantum fluctuations hint at the existence of temporary particles and energies that may not fit neatly into our current understanding of physics. These fluctuations could have given rise to energy forms that lie outside the realms of conventional science, suggesting that there is a treasure trove of untapped energy waiting to be discovered in realms of physics yet unexplored. The search for these novel forms of energy is more than just an academic pursuit. It is deeply tied to our quest for a more complete understanding of the universe's history and its ultimate destiny. Every new breakthrough in energy science brings us one step closer to reshaping our knowledge of both the cosmos and the fundamental laws that govern it. As civilizations in the universe evolve, their strategies for acquiring and utilizing resources will likely undergo dramatic transformations. In their infancy, a civilization would likely focus on exploiting the resources closest to home. This mirrors the early stages of human development on Earth, where primitive societies relied on local materials such as wood, stone, and animal products for survival. In an extraterrestrial context, the first settlers on a new planet would initially exploit natural resources like minerals, water, and fertile land. However, as civilizations grow, they inevitably face challenges such as resource depletion, environmental degradation, or overpopulation. To adapt, these civilizations would need to develop advanced technologies to extract resources more efficiently. For instance, they might deploy robotics or automated systems to mine asteroids, extracting valuable minerals and resources while minimizing human labor and the risks associated with such endeavors. This shift in resource extraction is analogous to humanity's transition from manual labor to mechanized production, which has dramatically increased efficiency and productivity across industries. As civilizations reach the limits of their home planet's resources, the next logical step would be to expand their search for energy and materials beyond their immediate vicinity. This marks the dawn of interstellar resource utilization, a phase in which civilizations begin to tap into the vast resources scattered throughout the galaxy. Picture spacecraft designed to extract helium from the dense atmospheres of gas giants or harvest water from the frozen moons of distant planets. Such innovations would vastly expand a civilization's resource base, opening new pathways for energy generation and providing the necessary materials to sustain growing populations. This shift from local to interstellar resource acquisition would not only redefine the way civilizations interact with their surroundings, but could also be the key to their continued survival and growth in an ever-expanding universe. Through these evolving strategies, the relationship between temperature, energy, and resource distribution continues to unfold, guiding the development of civilizations on a cosmic scale. Whether it is the energy forces of the early universe or the technological advancements that allow for interstellar resource extraction, each discovery and innovation brings us closer to understanding the grand tapestry of the cosmos. The intricate web of energy resources, whether formed in the fiery crucibles of star births or harvested from distant worlds, shapes the future of life and progress across the universe. The universe, ever dynamic and ever changing, continues to weave its story, with every fluctuation in temperature, every burst of radiation, and every new discovery pushing the boundaries of what we know. Moreover, the concept of sustainability could play a pivotal role in shaping the evolution of strategies for resource acquisition as civilizations advance. As societies become more acutely aware of their environmental impact, having witnessed the catastrophic consequences of poor resource management, they may begin to adopt circular economy principles. This framework promotes the idea of reusing materials, reducing waste, and maximizing resource efficiency. Such a paradigm would lead to a fundamental shift in how resources are used, with entire ecosystems benefiting from these more sustainable practices. Over time, some civilizations may go even further, developing deeper, more symbiotic relationships with their environments. Through the use of advanced biotechnology, they might cultivate resources naturally, employ alien life forms in their farming systems, or even genetically engineer plants to flourish in hostile climates. These innovations would not only enhance their resource acquisition capabilities, but also help maintain ecological equilibrium, fostering a harmonious balance between technological advancement and environmental health. Ultimately, the evolution of resource management strategies will depend heavily on a civilization's technological development, environmental consciousness, and the shifting challenges posed by their surroundings. The response to these challenges could lead to groundbreaking solutions that ensure the longevity of civilizations, enabling them to thrive sustainably for generations. This will be especially critical as they venture further into the cosmos, where the forces of nature and the vast, ever-changing landscape of space will demand adaptive and responsible approaches to resource utilization. By embracing sustainability at a cosmic scale, these civilizations could ensure that the pursuit of prosperity does not come at the cost of their planetary or galactic ecosystems, but rather works in harmony with them. At the heart of this cosmic journey lies the curious phenomenon of time, and how it is altered by the very forces that govern the universe. Altered cosmic conditions, such as those near massive objects or in extreme environments, have a profound influence on how we perceive and experience time. The key to understanding this is gravity. When gravity is intense, as it is near black holes or neutron stars, space and time themselves are warped. This distortion of space-time means that time appears to slow down dramatically for someone in the immediate vicinity of such a massive object, compared to an observer far away in a region where gravity has less influence. A simple thought experiment helps illustrate this. Imagine standing atop a towering mountain while a friend remains at sea level. Both of you have synchronized clocks. As you glance at your friend's clock, you notice it ticks at a steady pace, but your clock seems to be moving more slowly. This difference is not an illusion, but a direct consequence of the gravitational effects exerted on time itself, demonstrating how proximity to massive objects can warp the passage of time in tangible, measurable ways. Additionally, the expansion of the universe itself plays a role in how time is experienced. As galaxies move away from each other, their light undergoes redshift, meaning its wavelength stretches and shifts toward the red end of the spectrum. This phenomenon signals a cosmic change that affects how time is perceived on a universal scale. Looking back into the distant past of the universe, we would witness its evolution through a different timeline, one distinct from our own present. On a more personal level, human perception of time is also influenced by psychological factors. In moments of intense emotional or physical experience, such as extreme stress or extraordinary beauty, many people report that time seems to either speed up or slow down. This subjective experience of time can interact with the objective changes happening in the cosmos, adding a layer of complexity to our understanding of time itself. Thus, time is not a fixed, uniform experience, but a malleable phenomenon, shaped by the forces that govern space, gravity, and the expansion of the universe. The flow and perception of time are influenced by the ever-changing conditions of the cosmos, which are constantly in motion. Whether through the immense gravitational influence of celestial bodies or the vast distances between galaxies, time behaves differently depending on where and when one observes it. In the grand scheme of the universe, time is not a simple, linear progression, but an intricate, dynamic feature of reality. The ongoing changes in a planet's environment can also deeply influence the evolutionary processes of its inhabitants. Imagine a world where temperatures fluctuate dramatically, or resources become scarce due to environmental shifts. These changes would put immense stress on the species that call the planet home, dictating their survival and reproduction. Species that can quickly adapt to new conditions, such as altered temperatures or shifts in resource availability, will thrive. Meanwhile, those that cannot keep pace may face extinction. This natural selection process drives the evolution of species, with advantageous traits becoming more prevalent over successive generations. For example, if a planet experiences prolonged droughts, plant species capable of storing water more effectively will likely dominate. Meanwhile, those that cannot adapt may slowly fade from existence. As these changes unfold, entire ecosystems are reshaped, leading to a transformation in biodiversity. Furthermore, when species are forced to adjust to new environments, they may develop entirely new characteristics. This process, known as adaptation, can be seen in many forms, such as the evolution of new physical traits or changes in a species' behavior to better suit their altered surroundings. Over time, this could lead to speciation, a phenomenon in which populations of a species diverge so significantly that they can no longer interbreed, ultimately giving rise to entirely new species. The relationship between environmental shifts, survival pressures, and adaptation is a dynamic and ongoing process. It's not merely about the survival of individual organisms, but about the larger tapestry of life that evolves over time. This process contributes to the remarkable diversity of species found on any given planet, showcasing the adaptability and resilience of life in the face of ever-changing environmental conditions. Understanding these evolutionary impacts is not only crucial for the species involved, but also for the ecosystems they inhabit. As environments continue to change, so too must the species that live within them, continually adapting to the shifting conditions of the world around them. Another fascinating aspect of time is how it behaves under extreme conditions, particularly when influenced by gravity and speed. Time dilation, the phenomenon where time slows down in the presence of strong gravitational fields or at high velocities, adds an intriguing layer to our understanding of the cosmos. In a hotter universe, temperature and the behavior of particles would play a significant role in how time is experienced. In this environment, particles would possess greater energy, causing them to move faster. This increased velocity could lead to noticeable time dilation effects for particles in motion, especially when compared to a stationary observer. However, as we consider the interplay between gravity and temperature in a universe that is expanding and heating up, the situation becomes more complex. In regions of the universe that are hotter and less dense, gravitational forces would be weaker. As a result, the time dilation effects caused by gravity would also be less pronounced. On the other hand, the faster movement of particles in these hot regions would lead to greater time dilation. Therefore, the overall time dilation effect in a hotter universe would be a delicate balance between the increased energy and speed of particles and the decreased influence of gravity. This complex interaction between speed, gravity, and temperature creates an intricate framework for understanding how time could be experienced differently throughout the universe. As the universe continues to expand, it will inevitably undergo a gradual cooling process, which has profound implications for its future. Picture the universe as a vast balloon, slowly inflating over time. As the balloon expands, the energy within it spreads out, leading to a gradual decrease in temperature. Right now, the universe is filled with the faint remnants of the heat from the Big Bang, known as cosmic microwave background radiation. As the universe cools, molecular activity slows, and stars begin to burn out, their life cycles drawing to a close. Some stars will collapse into white dwarfs, others into neutron stars or black holes, signaling the end of the active stellar era. This cooling trend will also affect galaxies, which will continue to drift apart as the expansion accelerates, their interactions becoming rarer and rarer. Over unimaginable spans of time, galaxies might become isolated, floating alone in a cold, dark expanse, their only companion the distant glow of cosmic radiation. The cooling universe could eventually reach a state known as heat death, where everything reaches a uniform temperature. In this state, there would be no significant energy differences left to drive the creation of new stars or the dynamics of galaxies. Although matter would still exist, it would be in a static, lifeless state, evenly distributed across the cosmos. The vibrant, star-filled universe would fade into a cold, dark void, marking the ultimate fate of the cosmos. This shift from a warm, active universe to a cold, inert one invites us to reflect on our place within this grand cosmic timeline and the eventual demise of all celestial bodies in an endlessly expanding universe. The end stages of the universe will be deeply influenced by the initial conditions that existed at the moment of its creation. Imagine the universe as a tiny, extremely hot and dense point, a singularity, which exploded in what we call the Big Bang. This event set the stage for everything that followed, the formation of galaxies, stars, and ultimately life itself. The conditions at this moment, how much matter and energy existed, how they were distributed, and the rate of the universe's expansion, are critical in determining the long-term fate of the universe. For example, if there had been slightly more matter, gravity could have caused everything to collapse back in on itself in a big crunch, where the universe implodes into a singular point. On the other hand, if there had been slightly less matter, the universe could have expanded forever, eventually leading to a cold, dark end where galaxies drift apart and all stars burn out. There's also the possibility of a more balanced scenario, where the expansion slows and halts, creating a stable universe where galaxies and stars remain at fixed distances from each other, though life would eventually face significant challenges as stars die out. Each of these potential futures hinges on those critical moments just after the Big Bang, setting the course for the entire evolution of the universe. The universe, with its vast, unknowable expanse, is continually expanding, and yet there are still mysteries that deepen the intrigue surrounding its future. One of the most perplexing and fascinating concepts in this exploration is dark energy. This enigmatic force is believed to be driving the accelerated expansion of the universe. However, it remains an elusive and poorly understood phenomenon. If dark energy behaves in a manner different from current theories, the implications could dramatically reshape our understanding of cosmic evolution. The fate of the universe, in fact, may be intimately connected to its very origins, and even the slightest variation in those initial conditions could chart a completely new course for its ultimate destiny. It's as if the universe's fate is already written in the first chapter, its birth, yet that story could still take an infinite number of different paths. Picture for a moment a universe that began with just a tiny bit more heat than what we currently believe. A minuscule change in the early temperature of the cosmos could send the universe into a vastly different trajectory. In our familiar universe, the Big Bang triggered a rapid expansion that eventually cooled enough to allow the formation of atoms, stars, galaxies, and all the structures that define the cosmos we see today. However, what if that initial temperature was slightly higher? The repercussions could be profound. With a hotter beginning, the conditions would change in ways that could delay or even alter the formation of stars. The higher temperature would mean that matter would remain in a more energetic state for longer. The early universe would not have cooled quickly enough for atoms to form at the usual pace, which could drastically delay the ignition of the first stars. In this alternate reality, stars might burn much hotter and faster. Imagine a universe populated by super bright stars, dazzling and luminous, but burning out in a fraction of the time we know. These stars would go through their life cycles at an accelerated pace. Instead of the slow-burning, stable stars we observe in our universe, they would rapidly exhaust their fuel, exploding in violent supernovae. These cataclysmic events, in turn, would produce heavy elements at a rate far faster than in our reality. This higher rate of stellar death would have cascading consequences. Many stars might not even live long enough for planets to form around them, let alone for life to arise. The very stages of cosmic evolution could be upended. Galaxies, more densely packed with stars, could experience higher rates of radiation. The intense energy levels would create environments where life, as we know it, could not exist. The very forces that might form moons and planets could destabilize, leading to chaotic orbits and abrupt climatic shifts on any planet that did manage to form. As time passed in this hotter universe, the cosmic landscape would evolve in starkly different ways. The prevalence of massive stars would give rise to black holes, which, over billions of years, would dominate the universe. The universe could see violent galaxy collisions in which matter would be churned into a chaotic soup of energy and radiation. The final state of such a universe might involve what is known as a heat death, where the energy once available for stars to burn and for life to thrive would be exhausted, leaving behind a cold, dark, and sterile expanse, devoid of the vibrant structures we see today. Such a scenario, though purely speculative, demonstrates how a seemingly minor fluctuation in the early temperature of the universe could set off a chain of events, leading to a universe far more chaotic and less hospitable than the one we observe. The delicate balance that underpins the conditions required for stars, galaxies, and life could be entirely undone. Turning away from the physical specifics of the universe, there's also the fascinating realm of higher dimensional theories that challenge our understanding of space and time. While cross-dimensional travel is often relegated to the realm of science fiction, the idea of a slightly warmer universe opens the door to intriguing possibilities. The temperature of the universe is directly tied to the energy levels of particles. In a universe just a little bit hotter, particles would behave differently, interacting in more energetic and unpredictable ways. Imagine that the elevated temperatures would allow particles to move faster, increasing their interaction rates. This could open up the potential for the kind of anomalies theorized to exist in higher dimensions, such as wormholes, potential gateways to other realms or realities. However, while the idea is exciting, simply increasing the temperature of the universe wouldn't necessarily create these phenomena. Theories like string theory, which suggests the existence of extra dimensions, argue that reaching those dimensions would require far more than just increased heat. It would take specific and extraordinary conditions, conditions that go far beyond temperature alone. String theory, along with quantum mechanics, proposes a vision of reality that is far more complex than we see with our naked eyes. According to string theory, the universe's most fundamental building blocks aren't particles, but incredibly small, vibrating strings. These strings can exist across multiple dimensions, beyond the three that we can observe. This opens up a multitude of possibilities, including the idea of parallel universes or alternate realities that could be interconnected in ways we can't yet fully comprehend. In parallel with string theory, quantum mechanics also offers insight into the idea of cross-dimensional interactions. At the quantum level, particles can exist in multiple states or locations at once, a phenomenon called superposition. This behavior suggests that reality, as we experience it, may only be a small slice of a much more complicated existence. Some theorists believe that this quantum behavior might allow particles to access higher dimensions, perhaps even creating cross-dimensional interactions that we cannot directly perceive. The concept of the multiverse also builds on these ideas. What if there are many universes, each with its own set of physical laws and dimensions? If these universes could interact with one another, it could explain bizarre phenomena that currently defy conventional explanations. Even more intriguing is the idea of brains, multidimensional objects that could exist in higher dimensional space. Perhaps our entire universe is just one of many floating in this higher dimensional space, and the interactions between these brains might be responsible for events that we interpret as cross-dimensional occurrences. These theoretical frameworks, string theory, quantum mechanics, the multiverse, and brains, represent the cutting edge of scientific thought, pushing the boundaries of what we know and, more importantly, what we can imagine. They offer tantalizing glimpses into the unknown, suggesting that the universe is far more complex and interconnected than we can currently perceive. Now, consider what the future holds. As the universe expands, it also grows hotter. This increase in temperature, coupled with the ever-changing nature of cosmic structures, could lead to vastly different interactions between the universe's regions. In a hotter universe, the expansion would stretch galaxies farther apart, reducing their gravitational influence on each other. This would create a scenario in which galaxies could no longer easily merge or interact, leading to greater cosmic isolation. With these distances stretching ever farther, the space between stars, planets, and galaxies could become an even more desolate and empty region, potentially reducing the likelihood of meaningful interactions between celestial bodies. What we could witness is a universe becoming more and more isolated, with fewer opportunities for stars and galaxies to interact, their fates sealed by the inexorable expansion and increasing separation that define the universe's future. In conclusion, the universe's evolution, marked by its expanding reach and fluctuating temperature, holds a future that is shaped by forces both familiar and mysterious. Whether through the accelerated expansion driven by dark energy or the fundamental laws that govern the behavior of particles and cosmic structures, even the smallest change at the beginning of time could have long-lasting effects. The question of what awaits the universe at the end of its journey is one that remains shrouded in mystery. But one thing is certain: the more we explore, the more we uncover about the vast, complex, and ever-evolving universe that we call home. As the cosmos continues to evolve, so too does our understanding of how its myriad forces shape the interactions and dynamics within it. One of the most significant contributors to this complex interplay is temperature, which, especially in areas with active star formation, can create some of the most energetically charged regions in space. These areas, filled with vast clouds of gas and dust, possess the potential to spark a chain of cosmic events that could alter the very fabric of the universe. In such hot and dense environments, new stars may be born, and with them, the possibility of interactions that result in the exchange of matter across vast distances. This kind of interaction has the potential to create entirely new star systems or even influence the course of life itself, if such an event were to occur within the right conditions. However, a hotter universe is a double-edged sword. While it can foster increased isolation by stretching the already vast distances between cosmic objects, it also fuels energetic processes that can unexpectedly bind distant regions together. The future of connectivity within the universe hinges on a delicate balance of factors: the rate at which space itself is expanding, the distribution of matter across galaxies, and the way different forces, gravitational, electromagnetic, and others, interact with each other over time. These ever-shifting forces create an unpredictable and dynamic environment that scientists are only beginning to grasp. Thus, the future of cosmic connectivity will not depend on temperature alone, but also on the intricate dance of these complex and evolving phenomena. As our understanding of the universe grows, so too does the need for more sophisticated communication technologies that can adapt to the constantly changing nature of space. The challenge of transmitting information across such immense distances, where the very nature of time and space can behave unpredictably, is unlike anything humanity has ever faced before. Communication technologies would have to evolve at a pace that matches the dynamic shifts in the cosmos. Advanced signal processing methods could be employed to ensure that data is transmitted clearly, even when the laws of physics shift. These adaptive algorithms would need to adjust the way data is encoded, helping minimize the risk of signal distortion caused by varying spatial conditions. Think of this as a form of a flexible language, one that adjusts its grammar in real time based on the complexity of its environment. Moreover, these adaptive communication systems would require a radically different approach to the traditional idea of fixed infrastructure. Instead of relying on centralized networks, communication might be facilitated by a decentralized web of interconnected devices that can dynamically reroute signals as needed. Such a network would be incredibly resilient, able to adapt to shifting spatial dynamics in the same way that water finds different routes through a changing terrain. In a universe where distances, temperatures, and energies are constantly shifting, these flexible, decentralized systems would become essential for maintaining the flow of information. In addition to these advancements, quantum communication methods may play a pivotal role. By utilizing the unique properties of quantum particles, such as entanglement, it may be possible to transmit information instantaneously, regardless of the distance between the sender and receiver. This could completely revolutionize how we communicate across the stars, eliminating the constraints of time delays that limit traditional methods of signal transmission. Such a leap forward would make it possible to exchange information across vast expanses of space in real time, enabling a level of communication that has, until now, been confined to the realm of science fiction. Artificial intelligence, AI, could also enhance communication systems by predicting and adapting to the ever-changing conditions of space in real time. With its ability to analyze vast amounts of data and adjust network parameters on the fly, AI could optimize signal pathways, ensuring faster, more reliable communication even when spatial dynamics are unpredictable. This intelligent, autonomous system would be akin to having a skilled navigator guiding the data through an unpredictable cosmic landscape. As space itself continues to evolve, these advancements in AI and quantum communication would ensure that humanity and any civilizations that follow are able to maintain a constant flow of information, even in the face of the universe's chaotic transformations. The way civilizations react to changes in their ability to communicate or travel across the cosmos will be shaped by many factors: their level of technological advancement, their cultural values, and their historical context. Imagine for a moment a scenario in which humanity suddenly develops the capability to send messages to distant star systems at unprecedented speeds. This breakthrough would likely spark immense excitement and curiosity, igniting a wave of scientific inquiry, technological innovation, and cooperation among people across the world. For many, the prospect of real-time exchanges with distant extraterrestrial civilizations would create a sense of shared purpose and unity, marking the beginning of a new era of cosmic exploration. On the other hand, what happens if distances become so vast that communication breaks down, or if the very fabric of space itself hinders our efforts to communicate? In such a scenario, despair and isolation could set in, pushing a civilization inward and stifling its capacity for outward exploration. Without the constant exchange of ideas and culture that comes with interstellar communication, innovation may slow, and progress may come to a halt. The loss of contact with other civilizations could also lead to a sense of abandonment, which might breed distrust, xenophobia, and even aggression, as each civilization fights for survival in an increasingly hostile universe. The breakdown of communication could shift a society's focus inward, driving it to resolve its internal struggles rather than seeking solutions on a galactic scale. The way that a civilization interprets and reacts to these cosmic changes can have profound effects on its philosophy and values. Greater contact with other civilizations might lead to an emphasis on collaboration, unity, and shared purpose, potentially prompting profound shifts in governance towards more universal considerations. Conversely, a lack of interaction could breed a sense of competitiveness, or even hostility, leading to more aggressive behavior as civilizations attempt to secure their place in a universe that may seem indifferent to their existence. The universe itself, constantly in flux, presents a set of challenges that shape not only the course of civilization, but also the interactions between celestial bodies. One of the most significant forces in this cosmic dance is gravity. Gravitational force, the fundamental attraction between objects with mass, dictates how stars, planets, and galaxies interact. But what if the basic properties that govern gravity were to change? What if the mass of a planet or star were altered, or the distances between celestial bodies became different from what we know today? In such a scenario, the gravitational interactions between objects would change dramatically. Larger masses would attract more objects, pulling them closer and potentially destabilizing the orbits of nearby bodies. Smaller masses, by contrast, would struggle to maintain their hold on surrounding matter, resulting in fewer bodies orbiting them. Similarly, changes in the distances between celestial objects would dramatically alter their interactions. Bodies that are closer together would experience a stronger gravitational pull, which might result in tighter orbits, while those spaced further apart could drift apart, weakening their gravitational bonds. Such shifts in gravitational dynamics could result in previously unseen configurations of stars, planets, and even entire galaxies. Some star systems might collide, while others might be pushed to the edges of the universe. Isolated and disconnected, the entire structure of the cosmos could shift, creating new astrophysical phenomena that challenge our current understanding. This altered gravitational landscape could lead to strange and exotic planetary systems, stars that behave in unexpected ways, or galaxies that are more diffuse and scattered than we ever imagined. But gravity is not the only force at play. Magnetic fields and other forces may also reveal surprising phenomena. Neutron stars, for example, are remnants of massive stars that have exploded in supernovae. These objects are so dense that their gravity curves space-time, potentially altering the paths of nearby celestial bodies. If a neutron star were to pass close to our solar system, it could disrupt the orbits of planets or even affect the trajectories of satellites. Similarly, the magnetic fields of certain planets are highly unstable, and if we encounter such a planet, it could generate magnetic storms powerful enough to disrupt communication systems and navigation on nearby spacecraft. The universe is a vast and unpredictable place, and as we continue to explore it, new phenomena and forces will inevitably reveal themselves. As we look to the stars, we must be prepared for the unexpected, ready to adapt our technologies, philosophies, and strategies to navigate the ever-shifting landscape of the cosmos. Dark matter, an elusive and invisible substance, remains one of the most profound mysteries in the cosmos. Though we cannot see it directly, we know it exists because of its observable effects on the gravitational dynamics of galaxies. It exerts an unseen influence, guiding the motions of stars and entire galaxies, revealing itself only through its interaction with the visible universe. Yet, despite its pervasive presence, dark matter resists all attempts to be fully understood. It doesn't emit light, nor does it interact with electromagnetic forces in ways that we can detect. As a result, it remains an enigmatic force present in large quantities throughout the universe, but hidden from our direct observation. The presence of dark matter could change how we understand gravitational fields, pushing us toward new frameworks of physics. Regions dense with dark matter may alter the behavior of galaxies, suggesting the existence of entirely new phenomena related to gravity, phenomena we have yet to observe. As scientists delve deeper into the universe's vastness, they continue to look for these unexpected forces, ever pushing the boundaries of our comprehension. Each discovery, no matter how small, opens the door to further questions, leading us down new paths of inquiry that will hopefully bring us closer to uncovering the true nature of these cosmic mysteries. Yet, dark matter is far from the only enigma lurking in the vastness of space. The universe is teeming with phenomena that challenge the limits of our knowledge. One such mystery is dark energy, the mysterious force responsible for the accelerated expansion of the universe. Like dark matter, it remains largely unobservable and incomprehensible. We only see its effects on a cosmic scale as it pushes galaxies further apart, reshaping the very structure of the cosmos. Together, dark matter and dark energy make up most of the universe's mass and energy, yet they remain invisible and largely unfathomable. Among the more tangible cosmic oddities are rogue planets, planets that wander through space without a home star to orbit. These solitary worlds, untethered to any sun, present an intriguing puzzle. How might life, if it exists, survive on such isolated and freezing bodies? Without the warmth of a star, what might their surfaces or atmospheres look like? Could these rogue worlds harbor alien environments or ecosystems totally unlike anything we can imagine on Earth? These rogue planets, drifting aimlessly through the void, spark the imagination, raising questions about the potential for life in the most unexpected places. Another perplexing concept is that of cosmic inflation, the theory that the universe expanded exponentially in the moments after the Big Bang. This rapid growth would explain the large-scale structure of the universe, but the mechanism behind it remains unclear. What triggered this sudden burst of expansion? What occurred in those earliest moments that led to the universe's rapid inflation? Understanding this process is crucial for piecing together the origins of the universe, but much about it remains shrouded in uncertainty. Consider, too, the possibility of life existing in forms beyond our current understanding. Life, as we know it, thrives within the conditions found on Earth, but could life exist in environments that defy our definitions of biology? Perhaps in the thick, gaseous atmospheres of distant exoplanets, or in the icy oceans beneath the frozen surfaces of moons like Europa or Enceladus, life might exist in ways we cannot yet comprehend. These hypothetical organisms could function in extreme conditions, living without the same biochemical pathways that sustain life on Earth. The discovery of such life forms would challenge everything we know about biology and force us to redefine what it means to be alive. As scientists continue to probe the universe, these mysteries push us ever forward in our quest for knowledge. Each discovery invites deeper inquiry, each answer sparks more questions, and the pursuit of understanding opens up new realms of exploration. Our tools and methods may evolve, but the drive to understand the universe, to peel back its layers of mystery, remains constant. This journey of exploration and discovery not only enriches our knowledge of the cosmos, but also redefines our place within it. The more we uncover, the more we realize just how little we truly know, keeping us on the edge of excitement and curiosity. The search for answers about the universe has always been a powerful catalyst for progress. Our insatiable curiosity compels us to build new technologies, develop innovative methodologies, and push the limits of what is possible. For example, the desire to peer deeper into space has led to the creation of some of the most advanced telescopes and observational tools, enabling us to capture images of distant galaxies and to examine the behavior of stars, black holes, and dark matter in unprecedented detail. In doing so, we uncover not only new aspects of space, but also new ways of thinking about the fundamental laws of physics. Moreover, the pursuit of space-related research has catalyzed technological advances in other fields, too. The need for advanced materials and better communication systems sparked by the challenges of space exploration has led to innovations that have widespread applications here on Earth. These innovations often spill over into other areas of life, leading to improvements in everything from medical technologies to consumer electronics. The tools and techniques developed in the quest for space knowledge often have broader benefits, making the journey of exploration valuable not only for the answers it provides, but also for the unintended advances it spurs. The allure of space is not only scientific, it also inspires a deep emotional connection. The mysteries of the cosmos ignite the imagination of people all over the world, creating a sense of wonder and a shared curiosity that transcends borders. This collective fascination with the unknown drives not just current generations of scientists, but inspires future dreamers, thinkers, and innovators. Every discovery, every new revelation about the universe invites people to dream bigger, to ask deeper questions, and to explore the unknown. As we push forward into an era of space exploration that seems boundless, we realize that the answers we seek are only the beginning of a never-ending journey. In exploring the concept of alternate universes, we open a whole new realm of possibilities. What if our universe is just one of many, each with its own rules and physical laws? Imagine a vast, infinite multiverse where every possible configuration of forces and particles exists in parallel realities. In some of these universes, gravity might behave differently, or electromagnetism might be stronger or weaker. Matter and energy could take entirely new forms, and the very nature of space and time might differ from what we know. These alternate universes could host exotic phenomena that challenge everything we think we understand about physics, allowing us to explore entirely new concepts of reality. Extra dimensions add another layer of intrigue to this idea. Our experience of the universe is limited to 3 spatial dimensions and 1 time dimension, but some theories suggest there may be hidden dimensions beyond our perception. These extra dimensions might be curled up, invisible to our senses, yet they could profoundly influence the behavior of the cosmos. These unseen dimensions could give rise to new particles, new forces, or even entirely new laws of physics that govern the multiverse in ways we can't yet imagine. The very idea of these unseen dimensions challenges our most basic assumptions about the nature of reality. It suggests that what we perceive as the fabric of the universe may be just a small part of a much larger and more complex whole. These hidden realms may influence everything from the motion of galaxies to the behavior of particles at the quantum level, inviting an entirely new way of thinking about the universe. In science fiction, these alternative realities and forces often serve as the backdrop for thrilling tales of space exploration. But beyond the realm of storytelling, these ideas have real implications for the future of scientific inquiry. The exploration of alternate universes, extra dimensions, and new forces could ultimately lead us to an understanding of the universe that is far more complex and mind-bending than anything we currently imagine. Heat, too, plays a critical role in the discovery of ancient extraterrestrial artifacts, offering yet another layer of complexity to the exploration of the unknown. Temperature changes, whether gradual or sudden, can dramatically impact the preservation of materials, especially those that might be remnants of ancient alien civilizations or otherworldly objects. High heat can break down organic and inorganic materials alike, causing substances to become fragile, degrade, or disintegrate over time. When exposed to extreme temperatures, any biological materials or substances from other worlds could be rendered unrecognizable or destroyed altogether. Yet, paradoxically, heat can also aid in the discovery of these artifacts. Rising temperatures can cause the melting of ice and permafrost in cold regions, exposing buried materials that have remained hidden for millennia. This warming process may uncover structures or remnants that were previously preserved beneath frozen landscapes, offering a glimpse into ancient worlds that have long been sealed away. As the ice thaws and the land shifts, new artifacts may emerge, offering unparalleled opportunities for discovery. The interplay of heat and time could reveal clues about the past that were once out of reach, opening up entirely new areas of exploration and understanding. Alterations in heat can profoundly alter the chemical composition of surrounding environments, with far-reaching consequences for how materials interact with their surroundings. In such circumstances, phenomena like oxidation and corrosion can become more pronounced, revealing a complex interplay of physical processes that could remain hidden under ordinary conditions. As materials respond to heat in increasingly unpredictable ways, the task of detecting and analyzing artifacts requires a shift in scientific methodologies. Researchers must adapt, constantly refining their tools and techniques in order to uncover these hidden treasures with greater precision, ensuring they can effectively navigate the challenges posed by changing thermal conditions. While increased heat can threaten the integrity of extraterrestrial artifacts, often accelerating degradation, it can also act as a catalyst for discovery, unlocking the mysteries of the cosmos that have lain dormant for eons, deep beneath the surface. Understanding these thermal dynamics is not merely an academic exercise. It is essential for both preserving these artifacts and fully comprehending the ancient cosmic secrets they may hold. The universe's vast history and evolutionary trajectory serve as a rich backdrop for archaeological endeavors, offering insights into the forces that shaped not just human civilizations, but the very fabric of existence. Though many associate archaeology with the excavation of ancient human structures and relics, picturing dig sites where researchers painstakingly unearth artifacts dating back thousands of years, the broader context of the universe is just as significant in interpreting these findings. The cosmic origins of certain materials, such as gold, silver, and trace metals, provide an extraordinary layer of depth to archaeological discoveries. These elements were not originally formed on Earth, but in the hearts of dying stars or during explosive events like supernovae, which then scattered them throughout space. When archaeologists study ancient relics, they are in effect tapping into a cosmic narrative, a history that stretches back billions of years, far beyond the reach of human civilization. This perspective enriches our understanding of not just trade routes or technological advances, but also the cultural values that drove ancient peoples to seek and use such extraordinary materials. Artifacts imbued with materials born from the cosmic furnace tell stories that transcend human experience, pointing to our shared origins with the universe. In addition to the artifacts themselves, cosmic events such as meteorite impacts have shaped both the Earth and human history. The archaeological record can reveal the layers of history where ancient societies responded to these cosmic occurrences, providing insights into how they interacted with or were influenced by the impact of these extraterrestrial bodies. The discovery of a meteorite at an ancient site, for instance, might not only shed light on the technological capabilities of a civilization, but also offer clues about how these peoples viewed the heavens and used such celestial gifts, either as functional tools or as objects of worship and reverence. Human evolution is itself a product of a universe in constant flux. Just as stars are born, live, and die, their fates shaped by gravitational forces and thermodynamic principles, so too have human societies evolved in response to their environment. Understanding how celestial phenomena, such as the cycles of climate change, have influenced ancient civilizations can offer invaluable insights into migration patterns, societal adaptations, and cultural shifts. The study of ancient astronomical knowledge, or the alignment of architectural wonders like temples and pyramids, also reveals how early humans sought to understand the cosmos, embedding this celestial awareness into their cultural fabric. These deep connections between the terrestrial and the cosmic suggest that our history is far from isolated. Instead, it is inextricably linked to the very forces that govern the universe. This broader perspective does not merely place human history within a cosmic context, but rather reveals how the universe has played an active role in shaping the development of civilization itself. In this way, the universe's cosmic history is not merely a passive backdrop, but a dynamic participant in the unfolding of human culture and society. It informs our understanding of who we are and where we came from, revealing the deep connections we share with the stars and the planets that surround us. The potential discovery of alien ruins could provide further remarkable insights into the adaptability of life in environments vastly different from our own. Imagine a civilization that flourished under extreme conditions, perhaps on a planet subject to high radiation levels, intense atmospheric pressure, or extreme temperatures. Such ruins could offer an unparalleled glimpse into how these beings built their societies, developed technology, and expressed creativity through art and architecture, all while grappling with challenges far beyond the scope of human experience. For instance, if these ruins were found on a planet blanketed by thick clouds, blocking most sunlight, the inhabitants might have found innovative ways to illuminate their world, perhaps harnessing bioluminescence or advanced light manipulating technology. Such adaptations would not only highlight their creativity, but also offer clues about their technological prowess in solving everyday challenges. The architectural remnants of their civilization might reveal how they managed issues of weight, gravity, and stress in their buildings, especially in a world where environmental forces vastly differed from those on Earth. Additionally, an analysis of their artifacts might reveal intriguing details about their social structures. Did they live in cooperative communities, or were they solitary beings? The nature of their artifacts, tools, art, and everyday objects could reflect cultural practices or spiritual beliefs shaped by their unique environment, offering profound insights into their worldview. If these extraterrestrial beings developed technologies to utilize local resources, It would underscore the deep connection they had with their environment, highlighting how life evolves in response to the specific challenges it faces. Ultimately, the discovery of alien ruins would offer a story not just of survival, but of resilience, innovation, and creativity. These ruins would illuminate the various ways in which life can thrive under different conditions, expanding our understanding of life's potential forms and capabilities across the universe. They could redefine what we consider life, showing us that adaptation and survival are concepts that stretch far beyond Earth's constraints. In the boundless reaches of space, conflict could emerge for any number of reasons, ranging from competition over resources and energy to the clash of ideologies between civilizations. Picture two advanced species vying for control of a rare, energy-rich planet, both sides wielding their technologies in a battle for dominance. Yet, unlike the wars we are familiar with on Earth, conflicts between extraterrestrial civilizations might unfold in radically different ways. The scale of the universe introduces new dimensions to how these struggles would manifest. Instead of traditional warfare, these civilizations might engage in more sophisticated forms of negotiation, diplomacy, and competition, perhaps relying on interstellar treaties, resource-sharing agreements, or other collaborative frameworks to resolve their disputes. Advanced technologies could facilitate peaceful solutions in ways unimaginable to civilizations still dependent on primitive methods of communication. The development of real-time communication systems across vast cosmic distances might allow for rapid, direct dialogue between parties, fostering compromise without the need for violence. Furthermore, space is replete with untapped resources. Comets, asteroids, and uncharted regions of space could offer abundant energy and raw materials. If rival civilizations were aware of these alternative sources of growth, conflict over a single, contested location might seem myopic. Instead, they could choose to cooperate, embarking on joint exploration missions to discover new energy sources and forge alliances that transcend past hostilities. These possibilities suggest that in the vastness of space, the future of intercivilizational conflict may be shaped more by collaboration and innovation than by destruction and war. Moreover, the boundless and ever-expanding frontiers of space have the potential to shift our perspective on existence itself, compelling civilizations to adopt a broader, more cooperative outlook. In the vast cosmic expanse, civilizations might come to realize that their very survival hinges on mutual collaboration when faced with universal threats. Whether it's the peril of asteroid impacts or rogue celestial phenomena that wander unpredictably through the galaxy, the stakes for survival are immeasurable. In this scenario, what initially begins as territorial disputes or competition over resources could evolve into a united front, a collective effort aimed at defending against these shared cosmic dangers. This shared vulnerability might sow the seeds of understanding, fostering not just peaceful resolution but lasting partnerships, built not on competition, but on the understanding of mutual interdependence. Conflict resolution in this universe, shaped by its vastness and the existential risks of space, might not only be a reflection of advanced technological prowess, but also a profound shift in how civilizations view their place in the cosmos. The realization could dawn that cooperation is not simply a strategy for survival, but a pathway to achievements far greater than what any single civilization could attain on its own. This could usher in a new era, one where collaboration triumphs over confrontation, and where civilizations find that working together propels them toward collective advancement rather than individual triumphs. As the universe continues its inexorable expansion and evolution, the very nature of space may cultivate the conditions for cooperation among the most advanced of civilizations. A critical aspect to consider is how these civilizations may perceive resources, challenges, and threats. If the universe becomes increasingly unstable, or if vital resources such as energy or habitable space become scarcer, different societies may come to realize that only through collaboration can they hope to survive and flourish. In this shifting paradigm, a civilization might find itself confronting a common enemy in the form of a cosmic disaster, a celestial event that endangers multiple worlds. In such a scenario, the primal instinct for self-preservation could catalyze an unprecedented level of cooperation, with civilizations recognizing that working together boosts the odds of overcoming threats that would otherwise be insurmountable in isolation. Moreover, as knowledge spreads across civilizations, the sharing of scientific discoveries and cultural insights could foster a deeper sense of mutual respect and admiration. When societies begin to recognize that they share a common heritage, etched in the stars themselves, a sense of interconnectedness might take root. This newfound understanding could lead to shared endeavors, joint missions in space exploration, collaborative technological advancements, or even the collective preservation of cultural identities and histories. The galaxy, once perceived as an uncharted wilderness, might gradually be seen as a shared home, where each civilization's existence is woven into the fabric of a larger collective experience. In addition, as civilizations advance, their understanding of the universe's complexities could give rise to a more profound sense of empathy. They might become acutely aware of the fragility of life and of the intricate web of interconnectedness that binds all forms of existence. This realization could shift their priorities, moving them away from competition for dominance and toward collaboration that transcends the ambitions of individual civilizations. The stars, once seen as mere frontiers for conquest, could evolve into a vast network of mutual aid and exchange. However, this shift toward a more cooperative cosmic society is by no means assured. The universe is a place of unpredictability, fraught with forces and complexities that might derail efforts at collaboration. Histories of conflict, divergent ideologies, and differences in communication styles may pose substantial obstacles. Despite these challenges, the ever-changing nature of the universe could still lay the foundation for extraordinary partnerships, ones that defy the boundaries of what we currently understand as possible. The concept of cosmic diplomacy, which refers to cooperation between civilizations, both terrestrial and potentially extraterrestrial, on matters related to space exploration and resource utilization, could become an essential aspect of this new age. As humanity's technology advances and its presence in space grows, the diplomatic landscape is likely to undergo profound transformations. One manifestation of this evolution could be the establishment of international treaties aimed at the responsible use of outer space. These agreements could set clear standards for the peaceful exploration of space, ensuring that resources like water ice on the moon are not subject to territorial disputes, and that space debris is handled in ways that protect the integrity of satellites and spacecraft. In this evolving landscape, agencies dedicated to overseeing space activities could emerge, serving as collaborative bodies that ensure the peaceful and equitable use of space. These agencies could facilitate international cooperation, providing a platform for nations to discuss and resolve issues related to shared technologies such as satellite communications or planetary exploration. By aligning their scientific missions, pooling resources, and sharing data, nations could embark on ambitious goals that no single country could realistically accomplish alone. Furthermore, should humanity discover signs of intelligent life beyond Earth, cosmic diplomacy could be pushed to even greater heights. A new framework for communication and interaction with extraterrestrial entities would likely be needed, one that establishes universally accepted protocols for engagement. This could foster a shift in humanity's self-perception, transforming how we see ourselves, not as isolated nations, but as a unified species, Earthlings, bound together by a common identity. This new perspective could also influence discussions about pressing global challenges such as climate change and the distribution of resources here on Earth. The realization that we are part of a broader cosmic community might inspire unprecedented levels of cooperation to tackle the problems facing our planet. As technologies advance and the possibilities for space travel and colonization expand, new diplomatic opportunities and challenges will inevitably arise. Territorial claims over celestial bodies, for example, will require international negotiations to ensure that exploration is driven by cooperation rather than competition. Similarly, the development of legal frameworks for space mining and settlement will be crucial in ensuring that the resources of the cosmos benefit all of humanity, rather than being monopolized by a select few. Cosmic diplomacy, therefore, could evolve through the establishment of international treaties, the creation of collaborative agencies, and perhaps even standardized frameworks for interactions with extraterrestrial life. This evolution would not only help address the practical challenges of space exploration, but could also foster a spirit of collaboration that leads to unprecedented achievements in science, exploration, and the resolution of earthbound crises. As we venture deeper into the universe, we will inevitably encounter ethical dilemmas that arise from our interventions and actions in space. The moral implications of manipulating celestial bodies are vast and complex. If humanity were to attempt altering the course of an asteroid to prevent a catastrophic collision with Earth, we would face immense ethical challenges. The potential for unforeseen consequences is staggering. Actions intended to protect one world might inadvertently wreak havoc on another. A seemingly beneficial change could lead to larger disasters affecting ecosystems or populations that were previously untouched by the threat. The discovery of extraterrestrial life brings with it additional moral quandaries. What responsibility do we have toward these potential beings? Should we intervene in their natural evolution, especially if they are in a less advanced stage of development? And given the technological superiority that humanity possesses, do we have the right to impose our will on another form of life, no matter how primitive? These ethical questions deepen when we consider the possibility of genetic manipulation both on Earth and in space colonies. As humanity ventures into the stars and establishes settlements on other planets, the ability to modify human genetics for the purpose of adapting to new environments could lead to profound societal changes. This technological advance could create new forms of inequality, as those with access to genetic enhancement might elevate themselves above others, leading to divisions that challenge the very essence of what it means to be human. In this uncharted future, humanity will have to navigate not only the wonders of space, but also the profound ethical challenges that arise with it. As we stand on the precipice of cosmic exploration, the decisions we make today will shape the future of our species and the future of life itself across the stars. Moreover, the act of exploring and potentially colonizing other worlds brings forth a multitude of ethical dilemmas, particularly concerning ownership and stewardship. The very notion of claiming rights over planets, resources, and entire ecosystems raises profound questions about humanity's place in the universe. To assert dominion over celestial bodies implies a hierarchical relationship with the cosmos, one that suggests a superiority or right to exploit what lies beyond Earth's boundaries. But are we truly justified in this pursuit, especially when considering the history of environmental destruction and resource depletion that humans have wrought on our home planet? Earth's ecosystems, once teeming with balance, have been disrupted by the unchecked exploitation of resources. It begs a fundamental question. How can we, as stewards of this fragile planet, justify exploiting other worlds in a similar manner? Herein lies a pressing ethical concern. What does it mean to be responsible caretakers of an interstellar ecosystem? As humanity pushes the boundaries of space exploration, seeking to understand, alter, and possibly inhabit other worlds, these ethical considerations demand our attention. They remind us to tread carefully and with great responsibility, urging us to strike a delicate balance between the urge to explore and the imperative to act responsibly. This isn't just about the immediate benefits or desires of human civilization, but the long-term consequences of our actions, which could ripple through the universe, affecting not only our survival, but the very existence of other life forms that may inhabit the cosmos alongside us. The ethical principles guiding human behavior have always been shaped by the challenges societies face. As we expand our reach into the cosmos, these challenges take on even more profound dimensions. The simple act of living on a distant planet where resources are finite and survival depends on cooperation could fundamentally shift our moral beliefs. Imagine humanity stranded on a barren world, where every drop of water, every piece of food, and every breath of air is shared among the population. In such a setting, the values of collaboration, sharing, and collective well-being would become paramount. People would quickly recognize that the strength and unity of the community would determine their survival, and individualism would give way to a more communal ethos. In the face of cosmic threats, such as asteroid collisions or the inhospitable conditions of alien environments, the need for unity would only grow more pressing. A moral framework centered on survival would emerge, one in which the protection of the community would outweigh individual desires. The idea of sacrificing for the common good could become central to the moral code, reinforcing the notion that caring for one another is not just desirable, but essential for the collective well-being of the species. When survival becomes a shared goal, the ethical foundation of society would likely shift toward values of mutual support and interconnectedness. As humanity ventures deeper into the cosmos, questions about our place in the universe will inevitably arise. What is our purpose in this vast, seemingly infinite expanse? What moral duties do we owe to potential life forms that might exist on distant planets? These existential inquiries will spark philosophical discussions that challenge the very foundations of human ethics. In a universe filled with untold possibilities, could humanity's moral responsibility extend beyond Earth, potentially embracing the protection of life on other planets? This could give rise to new moral philosophies that emphasize interconnectedness, not just among people on Earth, but across the universe. The extreme challenges presented by the harsh conditions of space would likely force humanity to refine its ethical frameworks, evolving them to prioritize survival, cooperation, and respect for life, whether human, alien, or even microscopic. As our understanding of the universe grows, so too will the ethical beliefs that shape our behavior, compelling us to consider the broader consequences of our actions in an ever-expanding, increasingly complex cosmic landscape. In addition to these questions about humanity's place in the universe, the idea of advanced civilizations influencing the destiny of the cosmos raises fascinating ethical dilemmas. Imagine a group of beings with knowledge and technological capabilities far beyond our own, holding the power to influence not just their own world, but the very fabric of space-time itself. With such power comes an extraordinary responsibility. First and foremost, to protect their home environment. If these advanced beings are capable of manipulating energy and matter on a cosmic scale, they would also have the ability to prevent ecological disasters, mitigate the effects of climate change, and ensure the long-term survival of their planet's ecosystems. This would require a commitment to sustainable practices, utilizing their technological prowess to ensure that their planet thrives without depleting its resources. Such stewardship would go beyond mere survival, emphasizing the importance of nurturing the environment for future generations, maintaining biodiversity, and addressing the long-term consequences of technological advancements. Furthermore, as explorers of the cosmos, these civilizations might also bear the responsibility of observing and understanding the universe. They could study celestial phenomena, like supernovae, black holes, and potentially hazardous asteroids, sharing their knowledge with other civilizations to protect them from existential threats. By developing technologies to mitigate these dangers, they could enhance the safety of countless other planets and species across the cosmos. However, the ethical considerations become more complicated when it comes to interacting with less advanced civilizations. An advanced civilization must weigh the potential benefits of sharing technology and knowledge with younger species against the risks of cultural disruption or the imposition of existential threats. Would they impose their advanced technologies on less developed civilizations, potentially destabilizing their social structures or even threatening their survival? Or would they take a more measured approach, allowing these civilizations to evolve on their own terms, respecting their autonomy and freedom to develop at their own pace? Furthermore, such civilizations could also play a vital role in preserving the cosmic diversity of life. As guardians of knowledge, they might take on the task of protecting endangered species, fostering the growth of intelligent life forms, and ensuring that the rich tapestry of life and consciousness continues to flourish across the universe. Advanced civilizations, wielding great power and knowledge, not only influence the course of their own worlds, but also shape the broader trajectory of the universe. Every decision they make could have ripple effects across time and space, with the potential to either create or destroy. Such profound responsibilities would weigh heavily on their shoulders, reminding them that they are not just masters of their own fate, but custodians of the cosmos. Their ethical framework would be one of careful deliberation, striving to balance progress with preservation, understanding that each action taken could have consequences beyond their own understanding, echoing across the far reaches of time and space. As science continues to advance, pushing the boundaries of our knowledge and understanding of the universe, new and revolutionary technologies are on the horizon. One such possibility lies in the exploitation of quantum mechanics, the science governing the behavior of particles at their most fundamental level. If humanity could harness the strange properties of quantum mechanics, such as superposition and entanglement, we could develop quantum computers that would perform calculations at unimaginable speeds, revolutionizing fields such as medicine, climate forecasting, and materials science. Another area of immense potential is the development of advanced materials, inspired by the extreme conditions of the cosmos. Materials that can withstand the intense pressures, temperatures, and radiation found in places like supernova or on the surfaces of distant planets could become crucial in advancing industries like aerospace. These materials could make space travel safer, more efficient, and more sustainable, opening up new possibilities for humanity's exploration and settlement of distant worlds. As our understanding of the universe deepens, so too will the technologies that enable us to explore and interact with the cosmos, presenting new ethical challenges and responsibilities that will shape the future of human civilization. Understanding the cosmic environments that exist beyond our Earth has the potential to unlock incredible advancements in technology and material science, with profound implications for life on our planet. By studying the harsh and unique conditions in space, we can unlock the secrets of the universe that, when applied to Earth, could lead to revolutionary breakthroughs across many sectors. For example, the development of lightweight and highly durable materials could transform industries ranging from infrastructure to consumer goods, making them stronger, more sustainable, and more efficient than ever before. As scientists explore these extreme cosmic environments, it's clear that the knowledge gleaned from the cosmos could shape the very foundation of future technological progress. Energy generation is another field poised for groundbreaking advancements, with cosmic processes such as nuclear fusion providing a potential model for the power sources of tomorrow. Fusion, the process that occurs naturally in stars, combines light atomic nuclei to release enormous amounts of energy. Replicating this process on Earth has been a long-standing scientific goal, and if successful, it could unlock an almost limitless source of clean, sustainable power. This would not only transform the way we power our cities, but could be the key to addressing climate change, reducing our dependence on fossil fuels, and paving the way for a greener future. The technologies developed to harness nuclear fusion could have wide-ranging effects, potentially revolutionizing everything from how we generate electricity to how we use energy in our daily lives. In parallel, the realm of artificial intelligence, AI, stands on the brink of an era of incredible growth. As we deepen our understanding of the universe, this expanded knowledge could lead to the development of AI systems that are faster, more intelligent, and more adaptable than ever before. By incorporating insights from cosmic phenomena in the natural world, we might be able to develop algorithms and machine learning models that can solve complex problems with unparalleled efficiency. These advancements in AI could have a profound impact on a wide array of fields, from resource management to space exploration. By equipping these systems with the ability to learn and adapt at a rapid pace, we could create intelligent machines that help us navigate the challenges of both Earth and beyond, all while ensuring that we approach these innovations with care, sustainability, and respect for the environment. Each of these technological advancements, driven by an evolving understanding of the cosmos, represents more than just a drive for progress. They signal a shift in how we approach innovation itself, moving away from exploitation of resources and towards solutions that foster harmony with the universe. As our exploration of space continues, the potential for groundbreaking technologies seems limitless, with possibilities that were once deemed impossible now within reach. Space, with its extreme conditions and unpredictable environments, serves as a crucible for innovation, challenging our current knowledge and inspiring creative solutions that could forever change life on Earth. The cosmic environment is filled with extreme conditions that push the boundaries of what we know about materials and processes. Space is a realm of intense radiation, crushing gravity, and extreme temperatures, all of which present immense challenges for our current technologies. Yet it is precisely these challenges that spark innovation. Scientists and engineers working in space must think creatively to solve problems that often seem insurmountable. The materials and techniques they develop to withstand these harsh conditions have the potential to improve life on Earth in ways we may not yet fully understand. For example, studying the effects of microgravity on biological systems has led to new discoveries in medicine and agriculture. In the weightlessness of space, scientists can observe how plants grow and develop without the usual pull of gravity, leading to insights that could improve agricultural techniques here on Earth. These discoveries could revolutionize food security, particularly in regions with challenging growing conditions. Additionally, the study of materials in space has led to advancements in everything from electronics to construction materials. The extreme temperatures and radiation in space require engineers to develop materials that can withstand these conditions, leading to innovations that could improve everything from electronic devices to protective clothing for extreme weather. Space exploration has also had a profound impact on communications technology. Techniques developed to transmit data across vast distances in space have led to improvements in internet technology, enhancing both speed and reliability. Innovations in communication systems developed for space missions have, trickled down to benefit everyday devices, enabling faster, more efficient communication across the globe. These advancements show just how interconnected our progress in space exploration is with the technologies we rely on here on Earth. The unique properties of the cosmic environment act as a testing ground for innovation, pushing the limits of our understanding and forcing us to think outside the box. The solutions developed in response to the extreme challenges of space exploration often have applications far beyond their initial purpose, benefiting industries and sectors that may not seem directly related to space at all. In this way, space exploration not only expands our understanding of the universe, but also drives technological progress here on Earth, with innovations that transform how we live, work, and interact with the world around us. If we imagine a universe that began with higher temperatures, the nature of technology and materials might be vastly different from what we see today. In the early stages of the universe, when it was incredibly hot, atoms barely had time to form, and everything existed in a chaotic state of particles. As the universe cooled, atoms began to bond, forming the building blocks of matter as we know it. However, in a universe that cooled more gently, matter might have interacted differently, leading to entirely distinct forms of technology and devices. The abundant energy in such a universe could have allowed for the creation of novel materials with properties that defy our current understanding, enabling technologies that harness energy in ways we can only imagine. These materials might be far more efficient at using heat or light than today's solar panels, allowing for new ways to capture and use renewable energy. In such a universe, communication technologies might also have developed in entirely different ways. Electromagnetic radiation, which forms the basis for most of our communication technologies, behaves differently in environments with extreme energy levels. This could lead to the development of entirely new methods of transmitting information, possibly using unknown particles or frequencies that allow for communication over vast distances. In this kind of universe, the very tools and machines we create might reflect the environmental influences of the cosmos. Space travel, for example, could progress more quickly in a universe where energy is abundant and particle reactions lead to more efficient propulsion systems. Instead of relying on traditional combustion or electric engines, we might develop technologies that manipulate fundamental forces directly, opening up possibilities for space travel that were once thought impossible. In short, the technological landscape in a hotter universe would likely involve advanced materials designed to harness immense amounts of energy efficiently, alternative communication methods, and propulsion systems powered by the unique conditions of that universe. These developments would fundamentally change how civilizations interact with their environments and each other, leading to entirely new histories and cultures that unfold under vastly different cosmic conditions. Furthermore, the development of consciousness itself would be influenced by the unique conditions of the universe. If we imagine a universe with altered cosmic conditions, the path of consciousness might evolve in unexpected ways. For example, on a planet with a different mix of gases in its atmosphere, life forms might evolve to adapt to those conditions, leading to entirely new forms of communication, social structures, and cognitive abilities. In a low-gravity environment, beings might evolve larger brains to process complex tasks more efficiently, or they might develop different sensory modalities to navigate their world. On a planet with intense radiation, life forms could evolve heightened protective instincts or adaptability, fostering a form of consciousness focused more on survival than exploration. The social dynamics of these environments would also play a critical role in the development of consciousness. In environments where resources are scarce, traits like empathy and cooperation might evolve, shaping how life forms interact with one another. Consciousness, in this context, would not be static, but rather dynamic, shaped by the environmental pressures that each species faces. In a universe with radically different conditions, consciousness could evolve in ways that are entirely alien to our understanding, leading to cognitive experiences and forms of intelligence that are beyond our comprehension. As we explore these possibilities, it becomes clear that the cosmos holds a vast array of conditions that could give rise to forms of life, intelligence, and consciousness that are completely unlike anything we know. The very nature of consciousness itself is shaped by the environments in which life evolves, and in the vast expanse of space, the potential for new forms of awareness is limitless. The mental and cognitive processes of astronauts, for example, might undergo significant adaptation as they live and work in space. Without the pull of gravity, spatial awareness and orientation would shift, requiring astronauts to rely on visual cues rather than physical sensations to navigate their surroundings. These changes in cognitive processes highlight just how deeply consciousness is influenced by the environment, and how even the most fundamental aspects of being can evolve in response to the cosmos. The vastness of space can be a profound challenge for the human psyche. As astronauts venture further into the void, far from the familiar embrace of family, friends, and the comforts of Earth, the psychological toll can be immense. The isolation experienced during these extended missions can gnaw at one's mental resilience. Loneliness becomes a constant companion, and stress may accumulate in ways that are hard to fathom. Yet, the mind is a remarkable organ, capable of adapting in ways that ensure survival and progress in these extreme environments. Over time, astronauts' brains may develop new coping mechanisms, evolving to better manage the isolation and confinement that space presents. This mental shift is not merely about coping, it's about transformation. With the pressures of distance and isolation, the need for human connection becomes paramount. As a result, astronauts often develop stronger bonds with their fellow crew members. They learn to rely on one another in ways they might not have on Earth. In a sense, the confinement of space creates a tightly knit community where teamwork becomes not just a necessity, but a lifeline. Such bonds can alter the way individuals interact with each other, strengthening communication and collaboration, often with a heightened sense of empathy and shared purpose. Meanwhile, the mind is constantly exposed to new complex challenges. Operating intricate machines, troubleshooting unexpected technical failures, and adapting to ever-changing conditions are just a few of the tasks astronauts face. These experiences push the limits of human cognition, encouraging the development of new ways to solve problems. As astronauts confront these challenges day in and day out, their brains grow more adept at creative thinking and critical problem solving. The ability to innovate on the spot, to think outside the box, becomes an invaluable asset, especially when lives are at stake. Creativity and resourcefulness become essential for survival and the success of the mission. These cognitive changes are not just vital for those in space, they offer intriguing insights into the flexibility and resilience of the human mind. Studying how humans adapt mentally to such extreme environments reveals our innate capacity to evolve. This ability to adapt isn't limited to astronauts, but can also provide valuable lessons for dealing with the challenges we face here on Earth. The way the human mind navigates obstacles in the vacuum of space can serve as a guide for overcoming personal, social, or environmental hurdles in everyday life. As our imaginations soar toward the cosmos, the idea of telepathy, or nonverbal communication, begins to take shape. This concept stretches beyond mere science fiction, offering tantalizing possibilities for how intelligent beings, perhaps even from distant stars, might connect. Imagine two creatures, each from a different planet, meeting for the first time. They might not speak a word. Instead, they exchange thoughts or emotions directly, bypassing the need for language. Telepathy, in this scenario, would dissolve the barriers that spoken words often erect, fostering a deeper, more immediate connection between individuals. It could create a space for clearer understanding and empathy, where ideas and emotions flow without the constraints of verbal communication. Such a form of communication would be invaluable in situations where nuance and understanding are paramount. In high-stakes scenarios, such as during a scientific experiment or a tense conflict, the ability to instantly share thoughts and information could drastically enhance cooperation. With telepathy, there would be no need for misinterpretation or delay. Knowledge and experience could seamlessly transfer from one mind to another, facilitating faster decision-making and collective action. But telepathy is not the only way nonverbal communication might manifest. Other forms of communication could emerge in intelligent beings, such as body language, gestures, or even visual cues like changing colors on their skin. These forms of expression would communicate emotions, intentions, and even complex ideas without a single word being spoken. In environments where sound is distorted or even absent, like the vacuum of space or beneath the ocean's surface, such nonverbal cues could become the primary means of connection. They would convey meaning in ways words might fail, adding layers of depth to every interaction. The implications of telepathy and nonverbal communication extend far beyond individual interactions. They could radically alter the very structure of societies. In a world where people communicate through deep mental connections rather than words, relationships might evolve in entirely new directions. Communities could function on a level of mutual understanding and empathy, forming bonds that are based not on superficial exchanges, but on a profound mental connection. This could lead to societies that are more unified, more cooperative, and perhaps even more compassionate. It would be a world where the divisions caused by language and cultural barriers are no longer relevant, where the focus is on collective understanding and shared experience. As we contemplate these possibilities, it is essential to consider how such communication might affect life in a universe with a vastly different origin than our own. Imagine a universe where the early conditions were far hotter than our own, altering the very building blocks of existence. The extreme heat of such a universe would lead to the rapid formation of matter and energy, but this would come at a cost. The elements crucial for life, like hydrogen and helium, might form differently, potentially resulting in a more limited range of chemical reactions necessary for the emergence of complex structures. In such a hot universe, the formation of planets would be far more volatile. Many planetary bodies could remain in a molten state, while others might have atmospheres that are too unstable to support life. The opportunities for life to emerge would be dramatically reduced, and any life that did arise would likely have to survive in extreme conditions. Such organisms might look very different from anything we are familiar with, evolving unique strategies to cope with their harsh environments. In such a universe, the fate of civilizations could be quite different. Stars may form in abundance, burning brightly, but only for brief periods before their energy is exhausted. The result would be a chaotic cycle of birth and death, with little time for stability or progress. Any civilizations that did manage to arise would be forged in the crucible of constant cataclysmic events. Technological advancements might not progress along the same trajectory as ours. Rather than developing technologies for exploration or societal improvement, these civilizations might focus more on manipulating their environment to ensure survival. In such an environment, the emphasis would likely be on resilience rather than prosperity. Societies would be centered around survival in extreme conditions. The struggle to endure might dominate every aspect of life, from daily tasks to cultural values. In such a universe, the history of civilizations could be defined not by their exploration of new frontiers, but by their ability to adapt, endure, and overcome the forces of nature that sought to destroy them. The history of our universe is marked by transformative moments, each shaping the course of existence. One of the most significant of these moments occurred shortly after the Big Bang, roughly 8 billion years ago. This cataclysmic event marked the birth of space and time itself, setting in motion the processes that would lead to the formation of galaxies, stars, and ultimately life. Following this explosion, the universe underwent a rapid expansion, a phase known as cosmic inflation. This expansion smoothed out the energy fluctuations of the early universe and set the stage for the formation of the first galaxies. As time passed, stars began to form from the gas clouds that filled the universe. These stars illuminated the cosmos and played a pivotal role in the creation of heavier elements through nuclear fusion. When some stars reached the end of their life cycle, they exploded in dramatic supernovae, scattering these newly created elements into space. This process laid the foundation for the formation of planets and, eventually, the conditions necessary for life. On Earth, the formation of our solar system was a slow and delicate process. Over billions of years, dust and gas coalesced into the Sun and its orbiting planets. Earth, in particular, developed the right conditions to support life, with liquid water and a stable atmosphere. The emergence of photosynthesis was a revolutionary event, radically altering the Earth's atmosphere and paving the way for complex life to flourish. As life continued to evolve, intelligence emerged, and with it, the development of technology. Humanity's understanding of the universe expanded through the discovery of fundamental laws such as gravity, the laws of motion, and the nature of light. These breakthroughs allowed us to peer deeper into the cosmos, revealing the underlying forces that shape our existence. Our quest for knowledge continues, driven by the same curiosity that led our ancestors to look up at the stars and wonder what lies beyond. The exploration of space during the past century has brought us closer to understanding parts of the universe that were once beyond our reach. From landing on the moon to sending probes deep into the outer planets, humanity has embarked on a journey that has significantly expanded our knowledge of the cosmos. These missions have allowed us to peer into the vastness of space, revealing its secrets and unlocking new mysteries that continue to fascinate and inspire. Each key event in space exploration has added layers to the rich narrative of the universe, illustrating that the cosmos is not a static, fixed entity, but one that is dynamic, constantly evolving and changing over time. As we reflect on this historical tapestry of exploration, it becomes clear that the story of space is not just one of distant stars and galaxies. It is also a story of life, discovery, and an ever-deepening quest for knowledge. This ongoing pursuit drives us to push the boundaries of what we know, motivating us to explore the unknown and understand more about the universe in which we live. The vast expanse of space, with its infinite horizons and its strange manipulation of time, challenges our very perception of reality. In this cosmic context, storytelling and the preservation of history could undergo a remarkable transformation. As humanity ventures further into the universe, our tales might no longer be limited to Earth's geography. Instead, we might share our experiences and histories in a broader interstellar context. Imagine historians and storytellers crafting narratives that weave together the history of our planet with the broader cosmic journey of humankind. These storytellers would document our triumphs and struggles as we navigated the challenges of space travel, highlighting the milestones of discovery and the evolution of our civilization as we expanded beyond Earth. As we established colonies on distant planets and moons, local legends could begin to emerge, reflecting the unique environments and challenges faced by these new societies. Stories of survival, exploration, and connection would form the bedrock of culture in a truly cosmic society. Consider a colony on a distant planet, where the inhabitants recount the tales of the first settlers who ventured into the unknown, their experiences shaped by the strange landscapes, unfamiliar climates, and even encounters with alien life. These stories, passed down through generations, would become the foundation of cultural identity, deeply intertwined with the environments in which they lived. The preservation of this cosmic history would rely on advanced technologies that we can only begin to imagine. Digital archives could float within space stations, storing not only texts and images, but entire virtual experiences. Future generations might be able to relive the momentous first steps on Mars, or even take in the breathtaking views of distant galaxies through interactive narratives. With the presence of massive cosmic objects distorting time, some might even witness historical events as they unfolded, adding an entirely new dimension to how we understand the past. History could transform into a collective endeavor, with individuals from diverse backgrounds and homes contributing to a vast, interwoven narrative tapestry. In this new era, methods of expression would stretch beyond traditional art forms, embracing holographic displays and immersive virtual experiences. These evolving mediums would provide a richer connection to both the past and the present, allowing us to engage with history in ways that feel personal, immediate, and vivid. In this cosmic narrative, the essence of humanity, the dreams, struggles, and creativity that define us, would grow even more profound. Echoing through the stars, our journey as a species would be reflected in every chapter of our story, as we learn not only how to navigate our own world, but how to explore the universe itself. But what if the universe had begun in a slightly different way? Imagine that the conditions immediately after the Big Bang had been even a fraction hotter than they were. The implications of such a change would be vast and transformative, altering the very fabric of the universe in ways that we might struggle to comprehend. In the first moments after the Big Bang, temperatures were so high that fundamental particles were created in a searing, dense landscape. If the universe had started out a little hotter, the behavior of these particles could have been significantly different. Energy levels would have varied, which would have influenced how these particles interacted with each other. This hotter scenario could have had a profound effect on the fundamental forces of nature, such as gravity and electromagnetism. The increased temperatures might have caused these forces to have stronger or more pronounced effects on the matter around them, leading to entirely different outcomes in how matter itself formed. During the process known as nucleosynthesis, when particles combined to form atoms, higher temperatures could have resulted in the creation of a greater abundance of heavier elements. These elements, such as iron and carbon, are crucial to the formation of stars and planets. If there had been more of them, the process of star formation would have played out in a dramatically different way. Furthermore, changes in temperature could have impacted the rate at which the universe expanded. A hotter start to the universe might have caused it to expand more rapidly, or alternatively, slow down depending on the balance of forces at play, such as the mysterious presence of dark energy. This would have had a profound impact on the structure and distribution of galaxies, potentially leading to entirely different cosmic architectures. Instead of the universe we know, we might have seen a vastly different cosmic landscape, with galaxies and star systems arranged in ways that would have been unrecognizable to us. In essence, even the slightest variation in the early conditions of the universe could have set the stage for an entirely different cosmic reality. The universe we know today, with its stars, galaxies, and life-supporting planets, could have looked very different, if not entirely alien, had the temperature in those early moments shifted just a little. Such a change would have influenced not only the fundamental makeup of the universe, but the trajectory of life itself, potentially altering the course of evolution and the possibility of intelligent beings like us ever coming to exist. The vastness of space and the many variables at play continues to offer us endless opportunities for exploration and discovery, even as we ponder what might have been in the early, fiery days of creation. The concept of dimensions and alternate universes, both fascinating and mind-bending, has been intricately linked to the theory of cosmic inflation. This theory suggests that shortly after the Big Bang, the universe underwent an extraordinary rapid expansion known as inflation. If the universe had originated from a slightly more energetic state, the dynamics of this inflationary phase might have unfolded in a way that opened up a multitude of possibilities. It's conceivable that regions of space could have cooled at different rates, leading to a branching off of distinct regions, or even entirely separate pocket universes. These universes could potentially have their own set of physical laws, diverging from the ones we know. In such an alternate reality, everything might be different, from the very nature of dark matter and dark energy to the behavior of gravity. These mysterious forces, which continue to baffle scientists, might operate entirely differently, resulting in new kinds of cosmic structures, or even gravitational forces that behave in unexpected ways. It's an incredible thought. A universe just a little more energetic than ours could lead to the emergence of entirely different forces, galaxies, or even dimensions. The possibilities are as vast as the cosmos itself, suggesting that the universe we experience might be just one of many unfolding in unpredictable and unimaginable ways. This idea of parallel universes and alternate dimensions has captivated the human imagination for centuries, appearing in countless narratives across cultures. Since the dawn of civilization, people have looked up at the stars and told stories of celestial journeys, using the vast expanse of space as a canvas for both aspiration and caution. These tales, from ancient myths to modern science fiction, serve as a mirror to humanity's curiosity and its ceaseless drive for knowledge. But more than that, they highlight the moral and ethical questions that arise as we push the boundaries of our understanding and technological abilities. One compelling narrative could follow an explorer venturing into the great unknown of space in search of a new home for humanity. Along the way, this character could encounter alien civilizations, each with their own rich histories, stories, and traditions. Through these encounters, the explorer and the aliens could engage in cultural exchanges, finding common ground despite vast differences in biology and technology. This exchange would emphasize themes of unity, cooperation, and mutual respect, showing how collaboration, even between vastly different beings, can foster survival and growth. On the other hand, a darker narrative might center around a technologically advanced society that uses its capabilities to exploit the resources of the universe, perhaps without regard for the consequences. This tale would serve as a warning about the dangers of unchecked ambition, echoing the ecological disasters and societal collapses found in many cultural traditions. In such a story, a group of renegades or rebels might rise up, striving to reclaim their freedom and restore balance to a universe that has been tipped toward exploitation rather than cooperation. The consequences of such unchecked technological expansion would offer a sobering reminder of the need for wisdom and restraint in the face of power. An even more intriguing narrative might focus on a cosmic phenomenon like a black hole or a supernova, treating these forces of nature not just as objects, but as characters in their own right. These celestial bodies, with their immense power to transform and destroy, could become symbols of personal and societal transformation. The characters who encounter them might be forced to face their own fears and doubts, learning vital lessons about change, letting go, and accepting the impermanence of existence. Such stories would invite deep reflection on how humans adapt to the challenges they face, both on Earth and beyond. In all these narratives, regardless of the direction taken, the central theme remains the same: the exploration of humanity's relationship with the cosmos. Whether through the lens of adventure, caution, or profound transformation, these stories seek to understand our place in the universe, reflecting our aspirations, fears, and the connections we seek to form with others. These stories might not only entertain, but also provoke thought about the nature of existence itself, both within our own world and in the unexplored reaches of space. Dreams, art, and literature are often the means by which we process these cosmic mysteries. Through them, we express not just our curiosity about the universe, but also our fears and our hopes. In dreams, our subconscious mind wrestles with the vastness of space, often imagining ourselves as explorers, soaring through alien worlds or conversing with beings from distant stars. These dream scenarios capture our innate desire to understand what lies beyond our reality, to connect with something far greater than ourselves. Through these experiences, we confront both the awe and the anxiety that come with contemplating the unknown. Artists, too, seek to capture the grandeur of the cosmos through their work. Whether in paintings, sculptures, or performances, artists channel the beauty and chaos of the universe into tangible creations that evoke powerful emotions. A swirling galaxy painted with bold strokes, or an abstract representation of a cosmic phenomenon, can stir feelings of awe and wonder, urging viewers to reflect on the mysteries of the universe. These works of art, though diverse in form, share a common purpose: to express our relationship with the vast, ever-changing cosmos that surrounds us. Similarly, literature is another realm where we grapple with our cosmic significance. Writers, both authors and poets, have long explored the intricacies of human existence, weaving tales that delve into our yearning to understand the universe. Stories of explorers traveling into the farthest reaches of space mirror our own desires to uncover the mysteries of the cosmos. But they also examine the contrasts between human emotions, our hopes, fears, and ambitions, and the cold, indifferent nature of space. Through characters facing impossible challenges, literature reflects on themes of isolation, discovery, and the deep longing for connection in an infinite universe. All of these forms of expression, dreams, art, and literature do more than just reflect the human condition. They provoke us to question our place in the universe and the relationships we cultivate, both with each other and with the cosmos itself. They act as windows into the vast expanse, showing us not only our inner thoughts and emotions, but also the greater universe we are a part of. When we gaze at the stars, we don't just see distant suns, but reflections of ourselves, our hopes, our struggles, and our dreams. At the very heart of the universe's beginning lies the concept of chance. After the Big Bang, the universe began as a hot, dense ball of energy, where particles constantly collided and interacted in a state of tumultuous chaos. This environment, though chaotic, also provided the ideal conditions for randomness to shape the course of cosmic evolution. Small, random fluctuations in density allowed for regions of space to begin attracting more matter, setting the stage for the formation of stars and galaxies. The randomness of these fluctuations influenced not only where galaxies would form, but also the types of stars they would host. Over time, the chaotic processes of the universe began to give rise to structure, revealing how order could emerge from chaos. These random fluctuations in the early universe didn't just determine the locations of galaxies. They also influenced the elements that would eventually make up planets, stars, and life itself. The debris left over from star formations swirling in protoplanetary disks would coalesce into planets through random interactions between particles. These planets' size, composition, and orbits emerged not from predetermined laws, but from a series of fortunate random occurrences. This interplay of probability, though governed by the fundamental laws of physics, highlights the importance of chance in shaping the universe we know. The notion of chaos theory, which explores how small changes in initial conditions can lead to vastly different outcomes, becomes especially significant when we think about the evolution of alternate universes. Imagine a game of dominoes lined up in a perfect row. Pushing just one domino might seem insignificant, but the resulting cascade could change the entire arrangement. In the case of alternate universes, tiny variations in their initial conditions, such as the amount of matter or the strength of fundamental forces, could lead to completely different paths of evolution. These minor differences could create universes with entirely distinct galactic structures and laws of physics, and even the potential for life. Chaos theory helps explain the unpredictability of cosmic events and the evolution of complex systems. By applying this concept, scientists can develop models to simulate different scenarios, exploring how tiny variations in the universe's formation could lead to vastly different outcomes. These simulations provide insights into the intricate dance between order and disorder, shedding light on how alternate universes might evolve in unpredictable ways. In our own universe, seemingly random events can have profound consequences. The explosion of a nearby supernova, for instance, could send shockwaves through space, altering the chemical makeup of nearby planets and creating conditions that foster the development of life. What begins as a random occurrence, an event millions of light years away, can suddenly take on immense importance, changing the course of history for planets far removed from the event itself. Similarly, in our personal lives, randomness often intersects with choice. A chance encounter with a stranger can lead to a life-altering partnership or friendship. The universe, much like our own lives, is full of moments where chance and choice collide, creating opportunities and pathways that would otherwise remain hidden. In both our universe and in the realm of alternate realities, randomness plays a pivotal role in shaping the future, transforming what might seem like inconsequential moments into significant events. In the context of an altered universe, beings embarking on a journey of discovery would face a reality where even the basic rules of physics might be different. Gravity could behave in strange ways, affecting how explorers move and interact with their environment. These explorers, guided by curiosity and ambition, would need to adapt their technologies and bodies to survive and thrive in these new alien worlds. The challenges they face would be unique, shaped by the unpredictable forces at play in their universe. And in their quest for understanding, they would uncover not only the secrets of the cosmos, but also the deeper mysteries of existence itself. As we venture further into the depths of our universe, it becomes increasingly clear that the experience of time itself could be profoundly altered by the environments we encounter. Imagine, for a moment, a reality where time is no longer a constant, where its passage is fluid, fluctuating depending on the forces and elements surrounding these beings. A day in such a world could feel like an eternity, or pass in the blink of an eye. This shift would reshape how progress is understood, as the concepts of beginnings, endings, and durations become malleable. Time's elasticity could push these beings to redefine their very sense of achievement and growth, influencing the way they chart their explorations. Communication in this altered reality would be equally impacted. If sound no longer traveled in the same way, these beings might abandon traditional auditory forms of expression. Instead, they might develop entirely new systems of interaction, perhaps relying more on the visual realm or even manipulating light as a primary means of conveying ideas. This could lead to the creation of complex visual languages or sophisticated light signals, a new form of communication that transcends our current understanding. As they journey through the unknown, their discoveries would likely be nothing short of extraordinary. Elemental compositions, chemical reactions, and even the very materials they interact with could behave in ways we cannot yet fathom. The boundaries of science would be pushed, leading to technological breakthroughs that arise from the very challenges these beings face. Such innovations could propel them into realms of progress we have only dreamed of, opening doors to new possibilities and profound insights. This journey of discovery would not only be a quest for knowledge, but also a journey of transformation. The beings involved would be forever changed, not just by the alien worlds they explore, by their own evolving perceptions of existence. Their philosophies and worldviews would likely shift in response to their environment as they ponder their place in the universe in a way that reflects the unique challenges they face. This ongoing evolution of thought would lead to a deeper sense of wonder, curiosity, and perhaps even awe. Their very sense of self could transform, reshaping how they feel, think, and interact with the cosmos. With each step into the unknown, they would be met with not only discovery, but also an expanding sense of mystery. The questions they ask would grow ever more profound, probing the very essence of existence itself. As they grapple with these existential challenges, concepts of fate and destiny would likely play a central role in their philosophies. These two ideas, while seemingly similar, would manifest in very different ways across various civilizations. Fate, often seen as a predetermined course of events, could create a sense of inevitability among these beings. If fate governs their actions, their lives could feel as though they are on a set path, one that cannot be altered regardless of individual or collective actions. Such a worldview could lead to societies that struggle against this unseen hand, their efforts often seeming futile in the face of a grand design. The rise and fall of their civilizations might feel destined, a cycle of birth and decay that they cannot escape, no matter how hard they try. In contrast, the concept of destiny could present a more flexible view of existence. Rather than seeing life as a fixed trajectory, Destiny might be viewed as a series of possibilities that are shaped by the decisions and actions of individuals and societies. In this framework, the choices made by civilizations could steer them toward different futures, offering a sense of agency and control over their path. Such a perspective would emphasize the power of choice and innovation, where progress is driven by creativity and collective will. A society that embraces destiny would likely see itself as an active participant in shaping its own future, rather than a passive subject to the whims of fate. These contrasting views of fate and destiny would shape civilizations in unique ways, influencing not only their cultural expressions but also their technological advancements and social structures. Civilizations that believe in fate might develop philosophies that help them cope with their perceived lack of control, creating rituals, stories, and practices designed to help them accept their role in a preordained universe. They may look to the stars, not with hope, but with a quiet resignation, understanding that their destiny is already written. Conversely, societies that embrace destiny might push the boundaries of exploration and innovation. With the belief that their future is unwritten, they would see every action as an opportunity to shape their collective story. Driven by ambition and the desire to forge their own path, these civilizations would constantly seek to expand their horizons, venturing into uncharted territories in the hope of discovering new possibilities. The interplay between these two ideas would manifest in fascinating ways across the universe. Civilizations with differing beliefs about fate and destiny would face their challenges with different mindsets. Some might approach problems with stoicism, accepting that their struggles are part of a grand, inevitable design, while others would tackle obstacles head-on, confident in their ability to change their fate through action. These divergent perspectives would lead to civilizations developing distinct cultural narratives, conflict resolutions, and technological advancements, each shaped by their underlying philosophy about the nature of existence. As we consider how these forces play out across different societies, we are reminded of the profound impact that philosophical beliefs have on technological and cultural evolution. Just as throughout history, humanity's understanding of the universe has been dramatically reshaped by discovery, these beings too would experience a similar transformation. The history of science is filled with moments where new knowledge has shifted our worldview, opening up new realms of possibility. Take, for example, the moment when humanity first turned its gaze to the stars through the lens of a telescope. This momentous leap allowed us to peer into the vastness of the cosmos, uncovering moons orbiting distant planets. This discovery, in turn, shattered the long-held belief that Earth was the center of the universe, opening our minds to the unimaginable scale of the cosmos and our place within it. Now, consider the potential ramifications of a discovery on a similar scale, such as the detection or creation of dark matter. Dark matter, which is thought to make up a significant portion of the universe's mass, remains elusive, detectable only by its gravitational effects. To observe dark matter directly would not only challenge our current understanding of physics, but could redefine the very structure of the universe itself. This revelation could lead to new scientific paradigms, pushing the boundaries of cosmology and physics in ways we can scarcely predict. The discovery of extraterrestrial life would be another Earth-shattering breakthrough. Imagine a mission that uncovers microbial life on a distant planet or in the icy waters of a far-off moon. Such a discovery would be a profound confirmation that we are not alone in the universe, sparking a wave of philosophical and scientific inquiry into the origins and diversity of life. What does it mean for us as humans if life exists beyond Earth? How would our understanding of life's potential shift, and what implications would it have for our place in the cosmos? In addition to these groundbreaking discoveries, phenomena like gravitational waves are offering us new ways to perceive the universe. These ripples in spacetime, first detected only in recent years, provide us with a unique window into cosmic events, such as the collision of black holes. Gravitational waves allow us to explore the universe's most violent and mysterious events that were previously invisible to us. This new way of observing the cosmos opens up pathways to understanding the universe's fabric in a way we never could before, reshaping our understanding of gravity and reality itself. As we continue to push the boundaries of knowledge, each new discovery takes us further down a path of awe and wonder, transforming our understanding of the universe and our place within it. The journey of exploration, whether in the realms of time, space, or philosophy, promises to be one of perpetual discovery, forever altering how we think, feel, and engage with the world around us. Each breakthrough carries with it the potential transformation of our knowledge, our technology, and even our very selves. As advancements in quantum physics continue to unfold, they promise to fundamentally alter our understanding of reality itself. Concepts like quantum entanglement, where particles become instantaneously connected across vast distances, challenge our traditional views of space, time, and the very fabric of separateness. The possibility of harnessing such understanding could lead to breakthroughs that revolutionize technology, communication, and perhaps most significantly, our understanding of the universe. These discoveries have the potential to transform not only the way we perceive the cosmos, but also our very identity within it, pushing the boundaries of human knowledge and redefining our quest for meaning in the vast, infinite expanse of space. Consider for a moment a civilization living in the orbit of a distant planet. This advanced society might utilize the gravitational forces of nearby celestial bodies to their advantage in ways that seem almost fantastical. Imagine them as skilled surfers, gliding effortlessly through space, riding the waves of gravity to propel themselves forward. Just as a surfer uses the pull of the ocean's waves, these beings could align their ships with the gravitational fields of massive planets, using the natural forces of space to gain velocity without expending significant amounts of energy. This technique, known as gravitational slingshot, could enable them to travel vast distances across the cosmos, carefully selecting their trajectory to harness the forces around them and accelerate their journey. Now, envision how these civilizations might use the heat from their local stars to their advantage. The energy emitted by their sun could become the cornerstone of their way of life, with highly advanced systems designed to capture and store its warmth. Reflective materials could be used to direct sunlight into their homes and habitats, keeping them comfortable and functional even when their star sets. Furthermore, these societies could develop mechanisms to convert this solar heat into usable energy, powering their technologies and supporting their daily activities. In environments with extreme temperatures, they could engineer shields or concentrators to manage the heat, either protecting themselves from its harmful effects or harnessing it for energy production. Should these beings achieve sufficient technological mastery, they might even begin experimenting with more complex manipulations of cosmic forces. Picture the ability to create artificial gravity fields to stabilize ships or control the conditions within their settlements. Imagine the potential for adjusting the temperature of an entire environment, tailoring it for optimal agriculture, or engineering energy-efficient systems that make the most of their resources. In this vast and ever-changing universe, where gravity and heat shape the very nature of existence, the possibilities for innovation and adaptation are virtually limitless. Each civilization might develop its own unique ways of interacting with these cosmic forces, finding novel methods to thrive in the dynamic and sometimes unpredictable dance of the cosmos. As we peer into the boundless stretches of space, the potential for new, unknown cosmic forces emerging becomes increasingly tantalizing. The universe, an ever-evolving tapestry, continually reshapes itself in ways that we have only begun to understand. While we have a solid grasp on fundamental forces such as gravity and electromagnetism, we are still left to wonder about the mysteries that lie hidden beyond our current reach. One such mystery is dark energy, an enigmatic force that is responsible for the accelerated expansion of the universe. Scientists continue to work tirelessly to unlock its nature, raising profound questions about what this force truly is and whether it is merely another facet of the universe's intricate design or something entirely new. A deeper understanding of dark energy could revolutionize our conception of physics, perhaps requiring us to completely rethink the very fabric of the universe. Furthermore, the study of cosmic phenomena such as neutron stars and black holes reveals extreme forces that operate under the most hostile conditions imaginable. These environments push the boundaries of known physics, testing the limits of our understanding. The interactions taking place in such regions could lead to the emergence of entirely new forces or behaviors that challenge our current models of the universe, forcing us to reconsider everything we thought we knew about the laws of nature. If a previously unknown cosmic force were to emerge, it would likely force a dramatic shift in the frameworks that scientists have spent centuries developing. New theories, tools, and instruments would be required to study and understand these forces, demanding innovations in both our scientific approaches and our technologies. As we explore distant galaxies or study the cosmic microwave background radiation, we are likely to encounter phenomena that stretch the limits of human imagination. Each new discovery carries with it the potential for uncovering new forces, each with its own set of properties, behaviors, and implications. Some of these forces could have far-reaching effects on the development of advanced technologies that harness these unknown energies. In a very real sense, the universe is one massive experiment, constantly changing and evolving as we explore it. Each new layer of discovery brings us closer to unlocking the mysteries of existence, revealing phenomena that, until now, have remained hidden from our understanding. This ongoing journey not only enriches our scientific knowledge, but also opens up new possibilities for humanity, potentially altering the way we perceive and interact with the cosmos. As we continue to peel back the layers of the universe, we move ever closer to grasping a deeper, more profound understanding of the forces that shape everything around us. To truly coexist with the vast, often unpredictable forces of the universe, both in the context of space exploration and potential encounters with cosmic phenomena, humanity would need to develop a range of strategic and tactical adaptations. The first priority would be the creation of robust technologies capable of withstanding the extreme conditions of space. This would require spacecraft designed to endure the harshest environments, from intense radiation and powerful gravitational fields to the wide temperature fluctuations found in the vacuum of space. Lightweight yet incredibly durable materials would be essential for this undertaking, allowing for long-term exploration and survival in the most unforgiving regions of the cosmos. In addition, advanced navigation systems would become crucial for charting a course through the unknown. These systems would need to account for potential hazards, such as asteroid fields, comets, and even previously undiscovered cosmic threats. Imagine spacecraft equipped with advanced sensors, capable of detecting subtle changes in the environment ahead, enabling real-time adjustments to their travel paths. Such technology would be vital not only for avoiding dangerous obstacles, but also for making the most of the gravitational forces that could propel ships to far-off destinations. In this ever-expanding universe, as we venture deeper into the unknown, humanity's adaptability, resourcefulness, and curiosity will be our guiding lights, pushing us further into the cosmic frontier. The idea of collaboration as humanity ventures into the unknown expanse of space becomes paramount. Just as nations across Earth have come together for ambitious space missions, so too must countries unite in the vastness of space, where the challenges and complexities are often beyond individual borders. In this pursuit, the sharing of technology, knowledge, and expertise is not just beneficial, but necessary to ensure the safety and efficiency of these endeavors. Collaborative partnerships are not merely ideal, they are vital to navigating the unknowns of space. International guidelines born from these partnerships could be established to provide a framework for responding to potential dangers that may arise in the cosmic frontier. This united front would ensure that when unforeseen circumstances occur, there is a coordinated, rapid, and well-prepared response, drawing from the collective wisdom and resources of all nations involved. Safety in space, unlike on Earth, is a matter of survival not only for the astronauts involved, but for the integrity of humanity's continued exploration. As such, this kind of cooperation would offer strength through shared responsibility and mutual support. Training and preparation in this collaborative approach cannot be overstated. Astronauts and crew members would need to undergo rigorous, multifaceted simulations that replicate the unpredictable conditions they could face in space. These simulations, akin to emergency drills on Earth, would not be mere formalities. They would be critical to ensuring that these explorers are equipped to handle sudden, unexpected situations in an environment where even the slightest mistake could have catastrophic consequences. Just as emergency responders train for a variety of situations on Earth, astronauts would engage in exercises designed to prepare them for the chaos and uncertainty that space missions inevitably bring. Yet, even with all the technological advancements, there must also be an embrace of adaptability and resilience. The universe is an ever-changing entity, and new discoveries will always surprise even the most advanced systems and meticulous plans. By fostering a mindset of flexibility, astronauts, engineers, and all those involved in space exploration can adapt to new challenges that arise as the unknown becomes known. This adaptability will be critical in managing the complexities of coexisting with the forces of the universe, transforming each journey into space into a safer, more informed, and ultimately more successful venture. The metaphor of a vast ocean is helpful in visualizing how small disturbances can lead to profound consequences. Imagine, if you will, that the universe is like a sprawling ocean where each droplet represents a potential timeline. All these droplets may originate from the same place, created under similar conditions, and at first glance seem indistinguishable. However, even the smallest shift, a gentle breeze or the landing of an insect, can create subtle variations in their paths, which might grow more pronounced over time. These variations, though seemingly insignificant at first, can ultimately lead to entirely different outcomes. In the context of parallel timelines, this is precisely how small differences can spiral into vast divergences. For example, if two timelines start from the same point, let's say two individuals are faced with the same decision at a crossroads, one might choose to turn left while the other turns right, a seemingly inconsequential decision, but over time, these two individuals will live completely different lives. Relationships, opportunities, and choices will unfold in ways that would have been impossible to predict, resulting in the formation of separate realities, cultures, and societies. What began as a minor divergence at a single moment in time grows into a complex web of alternate possibilities. This principle is beautifully encapsulated in the metaphor of a seed growing into a tree. The seed is the initial event, and even the slightest variation in the early stages of growth, say a small deviation in the angle at which the seed is planted, can lead to radically different trees as time goes on. The branches and fruits of these trees, representing the timelines, will diverge and grow in entirely different ways, even though they share a common origin. The concept of parallel timelines is not merely a speculative idea. It is a testament to the intricate and interconnected nature of our universe, where all possible futures exist within the grand web of reality. The nature of timelines takes on even more intrigue when considered in relation to cosmic temperatures. These temperatures, which have evolved since the Big Bang, play a crucial role in shaping the development of the universe and influencing everything from the formation of galaxies to the birth of life itself. In parallel universes, even slight variations in cosmic temperature could have profound implications for the existence of life and the nature of reality itself. A cooler cosmos might slow the process of star formation, resulting in fewer stars and, consequently, fewer habitable planets. A warmer universe, on the other hand, could accelerate the pace of stellar evolution, leading to an explosion of new stars and a more vibrant array of potential life forms. As these divergent timelines unfold, life would adapt to their unique cosmic conditions. In some timelines, beings might evolve in a more stable environment, while in others, they would face extreme conditions that force rapid evolutionary changes. The idea that these alternate timelines could somehow intersect or influence one another adds another layer of complexity. Just as different environments on Earth give rise to diverse species and ecosystems, so too could these timelines harbor entirely different forms of life and matter. The interactions between timelines, should they occur, could involve the exchange of knowledge or technology, perhaps through theoretical portals between worlds. This idea of crossing over or collision of parallel worlds opens up a fascinating narrative about the meeting of completely different cosmic realities. Fundamental changes in the laws of physics could arise as a result of varying cosmic temperatures. In a colder universe, gravitational forces might be stronger, as matter would be more densely packed, while in a hotter universe, particles might behave more erratically, moving with greater freedom. These differences would not merely affect how life evolves, they would reshape the very fabric of existence, creating realms where space, time, and even the laws of nature operate under entirely different principles. The interplay between these timelines could at times result in them brushing against each other, leading to exchanges of energy, matter, and perhaps even conflict. These interactions would likely be born from fundamental differences in the way the laws of physics govern each universe, making such encounters unpredictable and fraught with potential dangers. However, they could also provide opportunities for growth and understanding, as different forms of life and matter from disparate timelines come into contact with one another. As these parallel universes evolve and adapt, the fundamental question of the nature of existence itself becomes ever more intriguing. Are we alone in this vast cosmos? Is our reality merely one of many? The study of parallel universes, with its blend of science, philosophy, and speculation, seeks to answer these questions while exploring the infinite possibilities that may exist within the multiverse. One of the most promising avenues for studying these parallel universes lies in advanced computer simulations. Much like scientists use computer models to simulate complex systems on Earth, they can create simulations that mimic the conditions of alternate universes. These models could explore various laws of physics, constants, and initial conditions, enabling researchers to visualize how even the smallest changes might give rise to entirely new realities. Through these simulations, scientists could investigate scenarios where gravity behaves differently, or where the forces of nature fluctuate in ways that are beyond our current understanding. Quantum field theory, which explores the fundamental particles and forces that constitute the universe, offers another framework for investigating alternate realities. By manipulating the principles of this theory, scientists could make predictions about how different universes might function. The study of quantum phenomena, such as entanglement and superposition, could provide insights into how these parallel realities might interact with one another or even overlap with our own universe. Another crucial tool in this investigation could be the study of cosmic phenomena, such as the cosmic microwave background radiation, which is the afterglow of the Big Bang. This radiation contains clues about the early universe and might, in some cases, hint at the existence of neighboring universes. Observations of strange cosmic events, like the collision of galaxies or the behavior of dark matter, could offer indirect evidence of parallel realities, helping to build a case for the existence of alternate worlds just beyond our reach. The study of parallel universes is in many ways an exploration of the very nature of reality itself. By using a combination of theoretical physics, computer simulations, and imaginative inquiry, we can begin to peel back the layers of existence and consider the infinite possibilities that may await us in the unexplored corners of the multiverse. Each discovery, each new insight, brings us closer to understanding not just the universe we inhabit, but also the vast network of parallel timelines that may stretch out before us, each offering a different version of reality. Furthermore, interdisciplinary collaboration has the potential to significantly deepen our exploration of parallel universes. Physicists could join forces with philosophers and cognitive scientists to explore the far-reaching implications of these parallel realms, especially concerning consciousness and human perception. The way we understand how humans perceive reality might become central to refining theories about these alternate universes, offering us a more comprehensive view of existence across different dimensions. By integrating methodologies from diverse fields, we gain a better grasp of the complexities surrounding the study of parallel universes. While direct observation of alternate realities is still out of our reach, these interdisciplinary frameworks, combined with creative scientific practices, offer pathways toward understanding what might lie beyond the confines of our universe. This exploration not only fuels our curiosity, but expands the very limits of our comprehension, inviting new realms of thought and discourse about existence itself. In a universe with a higher thermal baseline, energy systems and networks would need to adapt drastically to meet the demands of such an environment. A higher thermal baseline essentially means that the average temperature of the environment is hotter than what we are accustomed to, and this would inevitably impact every facet of energy generation, distribution, and consumption. The traditional methods we rely on for power generation, fossil fuels, nuclear, and solar energy would all experience unique challenges under these conditions. The heat would affect the efficiency with which these energy sources operate. For example, fossil fuels might burn more efficiently at higher temperatures, while solar power, particularly photovoltaic cells, would struggle due to their tendency to lose efficiency as temperatures rise. To counteract this, innovative cooling technologies would become indispensable, alongside new solar panel designs engineered to function optimally under hotter conditions. Energy transmission networks would face significant challenges as well in this heat-dominant universe. The very wires used to transport electricity would be subject to higher resistance as they heat up, leading to increased energy loss during transmission. This would necessitate the development of new materials and design strategies aimed at minimizing this resistance and optimizing the flow of electricity. Furthermore, advancements in energy storage systems would be crucial. As temperatures rise, conventional batteries and storage devices might discharge energy at a faster rate, leading to a greater demand for more efficient, heat-resistant storage solutions. In such a heat-driven universe, cooling solutions would be in high demand. District cooling networks, for example, could become more widespread, offering a centralized cooling system that serves entire areas rather than relying on individual installations. This would reduce the strain on local systems and ensure more efficient management of resources. Moreover, the push toward renewable energy sources would intensify, with an increasing emphasis on geothermal and ocean thermal energy. These sources of power, derived from the natural heat of the earth and oceans, would align well with the higher thermal environment, presenting a sustainable and efficient way to meet the energy needs of this hotter world. The pursuit of advanced heat management technologies would become a priority. As scientists and engineers develop innovative ways to handle higher temperatures, the focus would shift towards energy systems that can function effectively in extreme heat. These systems might include improvements in waste heat recovery, new cooling methods, and even novel ways of storing energy for long-term use. In this hotter universe, the relationship between energy production, transmission, storage, and consumption would become more intricate, requiring an adaptive approach to meet the demands of the new environmental conditions. Energy recycling and conversion processes would also undergo significant transformations. Imagine energy as a river flowing through various channels, each representing a different type of process. Energy recycling refers to capturing waste energy, such as heat from industrial processes or excess sunlight, and redirecting it back into the system for reuse. This is similar to rerouting part of the river upstream to ensure it flows again rather than letting it dissipate into the environment. Energy conversion, on the other hand, involves transforming energy from one form to another, such as converting sunlight into electricity through solar panels, or turning chemical energy from fuels into motion in cars. Each conversion process has its own efficiency levels, costs, and environmental impacts. While energy recycling aims to minimize waste and improve efficiency, energy conversion processes often incur losses as not all the input energy is transformed into useful work. In fact, much of the energy in conversion processes is lost as heat, mechanical vibrations, or other forms of waste. Technologies like heat exchangers for recycling energy and turbines or batteries for conversion are specifically designed for these tasks, each optimized to perform under certain conditions. The efficiency of these systems directly influences their effectiveness in reducing waste and ensuring sustainable energy use. Advancing both energy recycling and conversion technologies would be vital as we strive for a more sustainable future. Optimizing recycling technologies would help us make better use of the resources we already have, ensuring they are used as efficiently as possible. Likewise, breakthroughs in energy conversion could lead to more efficient ways of harnessing energy, reducing the environmental impact of energy generation. This dual focus on improving both recycling and conversion is key to creating a world where energy is used more responsibly and sustainably. New energy sources provide exciting opportunities to push the boundaries of our current capabilities. These alternative sources, such as nuclear fusion, wind, solar, and geothermal energy, offer the promise of cleaner, more sustainable power. Traditional energy sources like fossil fuels contribute significantly to pollution and climate change, but renewable energy harnesses the forces of nature without harming the environment. By shifting to these clean alternatives, we not only protect our planet, but also ensure that future generations will have the resources they need to thrive. Among the most promising of these new energy technologies is nuclear fusion, the process that powers the sun. If we can harness fusion on Earth, it could provide nearly limitless energy with minimal waste. Fusion uses abundant fuel sources, such as isotopes of hydrogen, and produces power without the long-lived radioactive waste associated with current nuclear reactors. This breakthrough could revolutionize energy generation, making it both abundant and clean. The potential for fusion to transform the global energy landscape is immense, offering a future where energy is both sustainable and virtually unlimited. The relentless march of progress in energy storage systems has unlocked possibilities once confined to the realm of dreams. These advancements have paved the way for more efficient methods to capture and store energy for later use, addressing one of the most significant hurdles in our quest to depend on intermittent energy sources like solar and wind. Solar panels rely on sunlight, and wind turbines need, well, wind. But with these innovative storage technologies, energy can now be harnessed and preserved when the sun isn't shining or the wind isn't blowing, making it available on demand. This breakthrough has the potential to revolutionize the way we power our homes, industries, and even vehicles. By expanding our energy portfolio with solutions such as these, we move closer to enhanced energy security and independence. No longer would nations be subject to volatile energy imports. Instead, the ability to produce and store energy locally not only bolsters national security, but also fuels economic growth. The rise of new technologies demands a fresh workforce, creating jobs and opportunities in industries that didn't even exist a few decades ago. These energy innovations represent not just a solution for current energy needs, but also a gateway to a more sustainable and resilient future. One where we aren't merely surviving, but thriving. However, the future of energy goes beyond merely how we power our lives. It taps into the very structure of the universe itself. The notion of a hotter cosmic beginning would fundamentally alter the very conditions of space as we know it. Picture the early universe, a time when everything was a dense, fiery cauldron of energy. If that starting point were even hotter, the entire trajectory of cosmic development could shift dramatically. In a universe teeming with heightened energy, particles would collide with unimaginable speed and intensity, creating a far more chaotic environment. This surging energy could alter the very formation of the most fundamental elements, hydrogen and helium, the building blocks of stars and galaxies. Instead of forming in the usual way, these elements might form differently, or perhaps not at all, changing the entire chemical makeup of the cosmos. In such an environment, stars would form much differently, if at all. These cosmic giants, born of a hotter universe, would likely be more massive, burning hotter, and emitting radiation of a far more intense nature. The radiation from these massive stars would have a profound influence on their surroundings, altering the conditions for planet formation. The habitable zones, those specific regions around stars where conditions are just right to sustain life, would be pushed to the farthest reaches of space. Planets formed near these stars would be subjected to extreme radiation, making it nearly impossible for life to develop. The surfaces of these worlds might be bombarded continuously, stripping away any atmosphere that might have existed, turning them into barren, hostile wastelands. Water, essential for life as we know it, might evaporate entirely, leaving behind desolate, dry landscapes. But the influence of a hotter universe doesn't stop at star formation. Cosmic events such as supernova, those violent, explosive deaths of stars, would occur more frequently, releasing far greater amounts of energy. These explosions could trigger bursts of new star formation or, conversely, create conditions so hostile that they extinguish any nascent life. A universe born of greater heat would likely render the emergence of life incredibly unlikely, emphasizing the fragile balance that exists in our current, more temperate universe. While some planets may retain the faintest glimmer of habitability, Most would transform into worlds where life is not just unlikely, but nearly impossible. This shift in cosmic conditions reminds us of the dynamic and ever-changing nature of space. Space is not a static backdrop, but a constantly evolving environment that can be influenced by numerous factors, including cosmic radiation and the shifting thermal dynamics of the universe. Cosmic radiation, which emanates from countless sources, be it the sun, supernova explosions, or distant galaxies, can profoundly affect the environment of planets. As high-energy particles travel through space, they can alter conditions on planets, influencing their ability to support life. If radiation levels were to rise significantly, it could disrupt biological processes, causing mutations and possibly rendering certain life forms vulnerable to extinction. Moreover, the increased radiation would pose significant challenges for long-term space travel, presenting dangers for both astronauts and future colonists. Similarly, the thermal dynamics of space, the way heat moves and is transferred, play a crucial role in shaping the conditions on planets and moons. As our sun goes through its natural cycles, it emits varying levels of radiation and heat. These fluctuations can lead to significant temperature changes on nearby planets, possibly making them either too hot or too cold to support life. If the temperature of a planet's surface rises or falls beyond a certain threshold, it could destabilize the conditions necessary for liquid water, thus hindering life's ability to survive. Furthermore, cosmic events like the birth of new stars or the expansion of galaxies can radically alter the distribution of energy throughout space, either shielding certain areas or exposing them to more extreme conditions. A nearby star going supernova, for example, would release a burst of radiation capable of drastically altering the conditions in the surrounding regions. Ultimately, the interplay between cosmic radiation and thermal dynamics is a delicate balance that determines how hospitable space truly is. It directly affects the potential for life on other planets, and as we venture farther into the cosmos, understanding these forces will be key to ensuring safe travel and perhaps even future colonization efforts. As we push the boundaries of human exploration, we must consider not just the physical challenges, but the invisible, ever-present forces that shape the environments of distant worlds. Life, however, has proven itself to be an extraordinary force of adaptation. The diverse ecosystems we see on Earth today are just a glimpse of the many ways life can evolve to survive in extreme environments. Each planet or moon has its own unique set of conditions, and organisms may evolve in fascinating ways to meet the challenges of their environment. On a planet with extreme temperatures, where the heat is unbearable or the cold is stifling, life forms might evolve reflective surfaces or thick insulating layers to regulate their body temperature, allowing them to survive in environments that would otherwise be inhospitable. In environments rich with radiation, some organisms might develop protective shields or tough exoskeletons that absorb harmful rays, similar to how creatures on Earth have evolved to survive in high radiation environments. In places where light is scarce, like the dense, turbulent atmospheres of gas giants, life could evolve bioluminescence. These organisms might use light not only for communication or mating rituals, but also to lure prey in a world where darkness reigns supreme. Meanwhile, deep beneath the surface of alien oceans, life forms might be found in the crushing depths of underwater trenches. These creatures would need flexible, resilient bodies capable of withstanding crushing pressure, along with specialized organs that allow them to survive in the cold, dark, and high-pressure conditions. Some might even employ unique biochemical processes to generate energy, tapping into geothermal sources rather than sunlight to fuel their metabolic needs. In resource-scarce environments, life could form symbiotic relationships with other species, working together to access vital nutrients and water. These life forms might share resources in ways that we can only begin to imagine, creating intricate ecosystems that allow survival where others would fail. The adaptability of life in the universe, driven by its relentless quest to survive, is truly one of the most remarkable phenomena in existence, revealing the infinite possibilities that await in the far reaches of space. As we continue our exploration of the cosmos, The discovery of these far-flung life forms and the understanding of how they thrive in environments beyond our current comprehension could lead to groundbreaking revelations about the nature of life itself. The more we learn, the closer we get to unlocking the mysteries of life's potential in the universe and the intricate mechanisms that sustain it. Organisms, in their ceaseless drive to adapt and survive, could evolve remarkable abilities to store and conserve essential resources with unparalleled efficiency. Through the development of specialized tissues and organs, these organisms might acquire the means to retain water during droughts, thus ensuring their survival even in the harshest of conditions. Such adaptations reveal the profound brilliance of evolution, showcasing the boundless potential for life, not merely to survive, but to thrive in the most unlikely environments. Across the vast expanse of the universe, each of these unique adaptations stands as a testament to the resilience, ingenuity, and creativity inherent in life itself. The possibilities for life to find a way to exist, no matter how extreme the conditions, seem endless, hinting at a universe rich with undiscovered marvels and untold stories. Imagine, if you will, a universe where the fundamental rules of temperature, much like in our own reality, follow basic physical principles, yet differ in crucial ways. In this alternate universe, the average temperature is lower by a certain fraction compared to ours. This seemingly subtle shift would have profound consequences on both the environment and the organisms that inhabit it. In our own universe, temperature plays a pivotal role in determining the state of matter. Water, for instance, remains a liquid at temperatures just above freezing, but turns into ice when the temperature drops lower. Now, in this parallel universe, with its significantly cooler temperatures, water might remain frozen for much of the time, thus reshaping the entire ecological landscape. Ice and cold-resistant life forms would dominate, evolving unique adaptations to cope with the near-permanent state of freezing temperatures. As temperatures decrease, chemical reactions, including those necessary for life itself, would inevitably slow down. Biochemical processes vital for metabolism would likely operate at a much slower pace, or perhaps evolve into entirely different mechanisms for storing energy. The climate, too, would undergo striking changes. In this cooler world, the seasons might be vastly altered. Long, harsh winters could prevail, with only brief and fleeting summers offering a window of opportunity for life to flourish. The landscape would be dominated by ice, with only a few regions capable of supporting life when conditions were favorable enough. What makes this scenario so intriguing is that, despite the differences in temperature and other environmental factors, the laws of physics remain constant. However, the way these laws manifest in this cooler universe would lead to a reality that, while structurally similar to our own, would be radically different in terms of its characteristics. From the simplest physical interactions to the complex web of life, the nature of existence itself would shift dramatically. This parallel universe would present an alternate version of reality, one shaped by subtle changes that reverberate through every aspect of the cosmos. The impact of these changes, from the behavior of matter to the ways life forms adapt, underscores how even slight alterations in the fundamental conditions of existence can lead to entirely different outcomes. Now, consider the fascinating possibility of two opposing universes interacting with one another. In this scenario, each universe operates under its own distinct set of physical laws, histories, and realities, yet occasionally they overlap or communicate in some mysterious way. Such interactions could open the door to countless unexpected and mind-bending phenomena. One of the most captivating ideas in this regard is the notion that events in one universe might influence the other, perhaps through a process akin to quantum entanglement. This quantum phenomenon suggests that particles can become interconnected even when separated by vast distances, so that a change in one particle can instantaneously affect its counterpart. If this concept were to apply to entire universes, actions taken in one reality might send ripples through the fabric of the other, resulting in interconnected events that span across both worlds. This possibility of inter-universe communication extends further to the exchange of energy, matter, or even information between parallel realities. Imagine, for example, the potential for a transfer of biological or technological innovations from one universe to another, sparking radical transformations and altering the course of history in both realms. This exchange could lead to entirely new phenomena, blending elements from both universes to create hybrid realities. Such events would be profound and unpredictable, offering a glimpse into a new form of reality where the boundaries between separate universes blur and merge into one. However, the excitement surrounding these interactions must be tempered by a sense of uncertainty. The rules governing each universe might be so fundamentally different that a collision or merging of the two could lead to catastrophic or chaotic results. The very nature of existence in one universe might not align with the conditions in the other, leading to unpredictable and potentially destructive consequences. In such a scenario, the fundamental laws of physics and biology could break down, creating a reality that defies comprehension. The idea of universes interacting in such a way challenges the limits of our understanding, presenting us with a mystery that is as thrilling as it is unnerving. As we delve deeper into the realm of dual or mirrored realities, we are confronted with profound philosophical questions about the nature of existence. Imagine a civilization that lives in a world where different versions of reality coexist, each one a mirror reflection of the other. These civilizations would inevitably develop belief systems shaped by their understanding of these parallel worlds. They might question whether their actions in one reality could affect another, or whether the two exist independently of each other. Such inquiries would spark philosophical debates and intellectual exploration on an unprecedented scale, as these societies sought to understand the implications of their existence within this dual framework. In such a world, the pursuit of knowledge would take on a new dimension. Advanced technologies would be developed to explore and analyze the nature of these parallel realities, perhaps using sophisticated instruments capable of detecting subtle shifts in the fabric of space-time. Concepts from quantum physics, which already hint at the possibility of multiple outcomes occurring simultaneously, would form the foundation for these explorations. In this context, storytelling would play an essential role in shaping how civilizations interpret their existence. Myths and narratives would evolve, drawing from the rich tapestry of dualities, and artistic expressions would reflect the struggles and triumphs of interacting with alternate versions of reality. As humans navigated the complexities of these dual worlds, they would undoubtedly face ethical dilemmas that challenge their understanding of free will and determinism. Would their decisions in one reality ripple across to the other? And if so, what responsibility would they bear for the consequences of those actions? The intersection of choice and fate would become a central philosophical inquiry, sparking deep debates among scholars, artists, and religious thinkers. Over time, such questions would shape the culture and values of these civilizations, leading them to reevaluate their concepts of self, identity, and purpose. In the pursuit of exploring these dual realities, societies would not only be seeking knowledge, but also embarking on a profound journey of self-discovery. By examining the reflections of themselves in these alternate worlds, they would uncover deeper truths about their own existence, their role in the grand tapestry of the universe, and their place in the intricate web of interconnectedness that binds all life together. On the other hand, envision a universe where the conditions are markedly hotter than our own, where stars burn hotter and faster, dramatically altering the landscape of the cosmos. In such a universe, the life cycle of stars would be significantly shortened. They would consume their nuclear fuel more rapidly, resulting in more frequent and violent supernova explosions. These cosmic events would unfold at a much faster pace, forcing astronomers to revise their models and predictions to account for the increasingly frequent and intense stellar phenomena. As temperatures rise, the behavior of matter and energy would change dramatically. In this hotter universe, the gas and dust clouds that normally collapse to form new stars would become more turbulent due to the increased thermal energy. This heightened activity could potentially slow down the process of star formation, making it far more chaotic and unpredictable. New models would be required to understand these conditions and anticipate the birth rates of stars in this more volatile environment. The entire structure of the universe would be shaped by this heat, creating a reality where the rules governing the cosmos are fundamentally altered. In this hotter universe, the life and death cycles of stars would unfold in fast forward, reshaping everything from the formation of galaxies to the very fabric of space-time itself. The challenge of understanding and predicting such a universe would require entirely new scientific paradigms, pushing the boundaries of human knowledge and imagination to their limits. The universe, with its shifting temperatures and evolving laws, would be an ever-changing canvas, one that demands constant adaptation and exploration to unlock its mysteries. As the universe continues to evolve, the effects of increasing heat on galactic interactions become ever more pronounced. The gravitational forces between galaxies, once operating under certain conditions, are amplified in hotter environments, leading to more intense and frequent collisions and mergers. Galaxies, which in cooler conditions might move gently through space, could experience a far more tumultuous existence, causing rapid shifts in their structure and behavior. These transformations complicate the task of predicting the future of galaxies and forces scientists to rethink established models of cosmic evolution. On a larger scale, the broader implications of a hotter universe affect not only galaxies, but the very fabric of the cosmos itself. The cosmic microwave background radiation, often considered a remnant echo of the Big Bang, could begin to show signs of change as the universe warms. This radiation, crucial for understanding the universe's infancy, could behave differently under new thermal conditions, requiring a reevaluation of long-standing theories about the universe's early moments. As temperatures rise, scientists will need to refine their methods of interpreting this fossil radiation to ensure it continues to yield accurate data. A hotter universe, in this sense, becomes a puzzle where each new discovery leads to an even more intricate challenge for astrophysicists. In this rapidly changing environment, scientists will be forced to adjust their existing theoretical frameworks and develop new predictive models that can keep pace with the dynamic shifts occurring across cosmic scales. The fundamental laws of physics, while constant, will need to be applied in innovative ways, as these laws must accommodate an environment that is evolving in ways never before observed. As we look toward the future of astronomical research, it becomes clear that the methods used to study cosmic phenomena will have to evolve as well. One of the most significant shifts in how we study the cosmos will come from advancements in technology. Traditionally, astronomers have relied heavily on telescopes and direct observational methods to track celestial bodies and their movements. But as the universe heats up and the number of variables at play increases, astronomers will likely turn to more sophisticated tools. Artificial intelligence, AI, and machine learning will become indispensable, allowing scientists to process and analyze vast quantities of data far more efficiently than before. These technologies excel at identifying patterns within the noise of seemingly random cosmic events, offering new insights into phenomena like stellar explosions, black hole mergers, and even the movements of distant galaxies. Moreover, AI and machine learning will serve as powerful tools for predicting future events. These systems, capable of learning from both historical data and real-time observations, will be able to adapt to new conditions. Imagine a future where the actions of distant stars, or even the collision of galaxies, could be predicted with a high degree of accuracy. These predictions would not only change our understanding of cosmic events, but could provide crucial information for preparing for phenomena like supernovae or asteroid impacts that could one day affect Earth. Another essential tool that will aid scientists in this new era of space exploration is the use of simulations. The idea of creating a virtual universe where scientists can adjust variables such as gravity, density, and cosmic energy states offers a promising way to explore the future of cosmic events. By manipulating these parameters in a controlled environment, scientists can simulate a range of potential outcomes, allowing them to anticipate the results of various cosmic phenomena. This ability to model complex systems will help predict everything from black hole formations to supernova explosions, providing invaluable insights into the universe's most extreme events. Furthermore, interdisciplinary collaboration will be key to refining our understanding of the universe. The combination of physics, mathematics, and computer science will allow researchers to develop increasingly sophisticated mathematical models that can account for the vast complexity of cosmic interactions. These models will take into consideration gravitational forces, energy states, and the compositions of different celestial bodies. By continuously adapting these models in response to new data, scientists will be able to make predictions that become more precise over time. As we expand our knowledge of the cosmos, new celestial bodies and phenomena will continue to be discovered. And with each discovery, our predictive models will become more refined. This cycle of observation, data collection, and model adjustment promises to make our understanding of the universe's future more accurate. In time, the ability to forecast cosmic events will become so advanced that events once thought unpredictable could be anticipated with remarkable precision. While this progress in predictive technology will be groundbreaking, it will also have profound implications for how we manage our planet. A hotter universe may be the ultimate challenge to our civilization, one that stretches across space and time. But here on Earth, scientists and engineers are already thinking about how we can adapt to these rising temperatures. As the universe heats up, Earth will not remain untouched. We will face challenges in the form of more extreme weather patterns, rising sea levels, and perhaps even new threats to our atmosphere. To meet this challenge, we must turn to innovative solutions. One promising avenue is the development of advanced materials designed to reflect more sunlight, acting as shields against the rising heat. These materials could be employed on spacecraft, satellites, or even human habitats, ensuring that they remain cool despite the surrounding temperature increase. Imagine a spacecraft orbiting a distant planet, protected by reflective surfaces that keep its internal systems functioning smoothly, despite the intense external heat. Similarly, Earth-based solutions might include the creation of space-based solar panels, a network of satellites designed to capture sunlight more efficiently. These panels could beam energy back to Earth, providing a virtually unlimited source of clean energy and reducing humanity's dependence on fossil fuels, which contribute to global warming. Geoengineering also presents an exciting possibility for counteracting rising temperatures. Scientists are exploring methods to manipulate the Earth's climate in deliberate ways, such as increasing cloud coverage to reflect more sunlight and reduce the amount of heat absorbed by the planet. Though these techniques offer potential solutions, they come with significant risks and require careful management to avoid unintended consequences. On a smaller scale, human societies may need to rethink how they build cities and manage natural resources. New urban designs could incorporate natural cooling techniques, such as using trees and plants to create shaded areas or implementing water features to reduce heat. By blending nature with urban development, we can create environments that naturally mitigate the effects of heat. Agricultural practices will also need to adapt. As temperatures rise, growing heat-resistant crop varieties will become essential, and techniques that conserve water will be critical. In some regions, this may involve changing where and how crops are grown. As conditions become more extreme, communities will need to rethink their food production strategies to ensure food security. Ultimately, solving the challenges posed by a hotter universe will require a global effort. Nations and organizations must work together, pooling resources and knowledge to develop sustainable strategies for managing the increasing heat across space and Earth. By embracing collaboration and technological innovation, humanity can meet the challenges of an increasingly hostile environment and continue to thrive despite the odds. As we venture further into the unknown realms of space, technological innovation remains our greatest ally. The harsh environment of space demands solutions that are not only advanced, but highly specialized. In the vacuum of space, every piece of equipment must function without the atmosphere's protective shield, requiring materials that can withstand extreme temperatures and radiation levels. Life support systems will continue to play a pivotal role in ensuring human survival, offering solutions to air, water, and food management in space environments. As we look ahead, the challenges of space exploration will continue to evolve, but with each advancement in technology, we move closer to unlocking the secrets of the universe. Through a combination of adaptive technologies, interdisciplinary research, and global cooperation, humanity can navigate the complexities of a hotter universe and continue its journey through the cosmos. Communication technology faces a unique set of challenges when it comes to connecting across vast distances, especially in space. While signals travel at the speed of light, the immense distances between celestial bodies introduce delays that can be measured in minutes, hours, or even days. To bridge these gaps, we rely on advanced communication systems that are designed to mitigate the effects of such delays while maintaining a constant and reliable link. This requires intricate satellite and relay systems capable of transmitting vast amounts of data over light years, ensuring that astronauts and scientists on Earth remain in constant contact, no matter where they are in the universe. Building and refining these systems is crucial as space missions push further into the unknown. Energy generation, too, must be reimagined to meet the demands of cosmic exploration. Solar panels, a staple of energy collection, are effective when sunlight is abundant, but the harsh and unpredictable nature of space presents a different reality. Solar panels designed for use in space must be able to function even in low-light conditions, such as when collecting energy from distant stars or during extended periods of darkness on distant moons and planets. To ensure a constant energy supply, cutting-edge storage technologies are also necessary, so that power is available when it's needed most. These innovations in energy capture and storage are essential for keeping long-term space missions running smoothly. Alongside energy generation, the need for exploration and research is driving major advances in robotics and automation. Robots have become indispensable tools in space exploration, venturing into environments that are simply too dangerous or distant for humans to reach. These machines are not just remote-controlled devices. They are autonomous, equipped with sophisticated sensors and artificial intelligence, AI, that allow them to make decisions in real time. In uncharted, hostile territories, human oversight may not be possible, but AI-driven robots are designed to carry out tasks, analyze data, and adapt to changing conditions. As a result, they are transforming how we explore and understand space, enabling missions to proceed even when human presence is not an option. Ultimately, the technological evolution we're witnessing in response to the demands of space exploration showcases humanity's ability to adapt, innovate, and overcome obstacles. Every breakthrough, from advanced communication systems to autonomous robotics, is not only a response to the immediate challenges of space, but also a reflection of our intrinsic desire to push the boundaries of what is possible. Each technological advancement offers a glimpse into humanity's future as we continue to reach for the stars. These innovations pave the way for future generations to uncover the mysteries of the universe, pushing us closer to understanding the cosmos and our place within it. Artificial intelligence, AI, and synthetic organisms are emerging as pivotal players in this journey, holding remarkable potential to adapt to and even transform the conditions of distant worlds. Imagine, for a moment, environments that are radically different from anything we know on Earth. Planets with extreme temperatures, toxic atmospheres, or even places without solid ground beneath our feet. In such alien settings, AI could play a key role in overcoming these challenges, analyzing vast amounts of data to help us understand the unique conditions of distant planets or moons. It would allow us to make informed decisions about how to survive and thrive in these environments. One of AI's most significant roles in space exploration is in the development of autonomous robots. These intelligent machines would be equipped with the capacity to navigate unfamiliar planetary surfaces, making decisions based on real-time data and transmitting critical information back to Earth. The robots could explore new worlds, surveying terrain and collecting samples, all while ensuring that humanity's presence is felt even in the most remote corners of the universe. These autonomous explorers would pave the way for human missions, conducting research in areas where human beings might not be able to venture for decades or even centuries. Meanwhile, synthetic organisms could revolutionize our approach to life in space. Imagine life forms specifically engineered to thrive in environments that would otherwise be inhospitable to humans. Organisms designed to absorb toxic gases and convert them into breathable oxygen, or microbes that extract water from the atmosphere to make a desert planet habitable. These synthetic organisms could even serve as the foundation of self-sustaining ecosystems, making it possible for humans to live on distant planets for extended periods. They could also help create a balance between alien biomes and human habitats, supporting the creation of livable spaces for future space colonies. AI also has the potential to enhance our understanding of complex biomes by simulating the intricate relationships between organisms in unfamiliar environments. This knowledge could guide the design of synthetic organisms that complement Earth-based species, helping to establish hybrid ecosystems that can adapt to new planets. Together, AI and synthetic life forms could form the cornerstone of future space exploration and habitation, creating a new paradigm for how we live and thrive in the cosmos. As we venture deeper into the unknown, the collaboration between AI and synthetic organisms will be vital. Together, they could usher in a new era of space exploration, one where humanity not only survives in space, but thrives, transforming hostile environments into new homes. This collaboration may ultimately redefine our understanding of what it means to exist in space, providing us with the tools to adapt, innovate, and flourish in an often unwelcoming universe. The future of exploration is not just about surviving, it is about transforming the very fabric of existence to suit the needs of human life, wherever we may go. The quest for understanding our universe is not merely an academic pursuit. It has the potential to reshape entire civilizations. Each new discovery in space, whether it's the formation of stars or the behavior of black holes, has the power to inspire people around the world to think bigger, dream longer, and reach further. As we uncover the mysteries of the universe, we may find ourselves questioning our place in the grand tapestry of existence. This new understanding can challenge our perspectives, fostering a sense of unity as we realize that, despite our differences, we are all part of the same cosmic story. The technologies we develop to explore space often lead to innovations that benefit life on Earth. Space research has already spawned breakthroughs in communication, navigation, and even medicine, technologies that have transformed our daily lives. For example, the development of satellite communication systems for space missions has revolutionized how we connect with one another, shrinking the globe and making global communication faster and more efficient. This relationship between space exploration and technological innovation is symbiotic. As we push the boundaries of space exploration, we create new technologies that, in turn, improve life on Earth. The pursuit of cosmic understanding also fosters international collaboration. Space exploration is a global endeavor, with nations frequently coming together to pool resources, share knowledge, and work towards common goals. This spirit of cooperation has the potential to foster peace and solidarity among countries, breaking down barriers and building alliances in the name of discovery. As we work side by side to explore the cosmos, we may find new ways to resolve conflicts and promote understanding, showing the world that when we come together in the pursuit of knowledge, there are no boundaries. Moreover, as our understanding of the universe expands, so too does our philosophical perspective. Questions about the potential for life on other planets or the implications of our place in the cosmos could drive humanity to rethink its priorities. This new awareness might encourage us to focus more on sustainability and stewardship of Earth, recognizing that our planet is not just a place to live, but an integral part of a much larger cosmic system. As we venture into the stars, we must also learn to care for our home planet, ensuring its survival for future generations. The dream of exploring other planets or establishing colonies on distant moons presents new challenges, not just technological, but societal, ethical, and economic. As humanity imagines life on other worlds, we must consider what it means to live and govern in such environments. How will new societies be structured? What economic models will sustain these off-world colonies? What ethical questions will arise when humans begin to alter entire ecosystems to suit their needs? These challenges prompt us to innovate not only in technology, but also in how we think about community, governance, and what it means to be part of an interstellar civilization. Ultimately, the pursuit of cosmic understanding is not just a journey into the unknown. It is a journey that has the power to transform societies, spark collaboration, and redefine what it means to be human in the grand context of the universe. As we continue to explore the stars, We are not just seeking knowledge, we are shaping the future of humanity itself. The quest to understand extreme cosmic phenomena, such as the conditions near black holes or the chaotic moments following the Big Bang, is filled with both monumental challenges and groundbreaking opportunities. These enigmatic phenomena lie at the very edges of what we can comprehend, and studying them requires overcoming immense obstacles. The distances involved make it difficult to gather data directly, and the extreme conditions near objects like black holes present unique challenges. Black holes, for instance, do not emit light, making them invisible to traditional telescopes. Instead, their presence is inferred from the effects they have on nearby matter, requiring scientists to develop sophisticated detection methods. Near a black hole, the gravitational forces are so intense that they warp space and time, creating conditions where conventional physics break down. To study such environments, scientists must create entirely new theoretical frameworks that can accommodate the bizarre effects of these regions. Understanding black holes and other extreme cosmic phenomena requires years, if not decades, of research and testing. Yet, despite these challenges, breakthroughs continue to emerge. Advances in observational technology, such as powerful telescopes and highly sensitive instruments, have allowed us to gather data from previously unreachable locations. The first ever image of a black hole's shadow, captured by a global network of radio telescopes, marked a historic moment in our understanding of these mysterious objects. Similarly, experiments conducted in particle accelerators that simulate conditions similar to the early universe have provided new insights into the forces that shaped our cosmos. These breakthroughs demonstrate that, despite the immense obstacles, the pursuit of knowledge about the universe is both possible and essential to our understanding of the cosmos. In the ever-evolving realm of scientific discovery, a transformative shift has occurred. What was once a landscape marked by solitary pursuits is now a dynamic hub of interdisciplinary collaboration. Astronomers, physicists, and engineers, once working in their isolated domains, are now uniting to tackle the age-old questions of the universe. Their combined expertise has fueled a new wave of progress, where the boundaries between fields blur and new approaches emerge. The synthesis of ideas, the cross-pollination of knowledge, and the merging of technologies have given rise to innovative methodologies that are reshaping our understanding of the cosmos. As these disciplines converge, a shared mission emerges to unlock the deepest mysteries of the universe. United by this singular goal, scientists are overcoming obstacles and pushing past the limits that once constrained them. The challenges that once seemed insurmountable now serve as stepping stones toward further exploration. Each discovery, no matter how small, acts as a beacon guiding humanity to the next frontier of knowledge. In this collaborative environment, every new revelation builds on the last, propelling us forward in an endless cycle of cosmic inquiry. But as the collective quest for knowledge expands, so too does the potential for a new kind of connection. In this reimagined universe, the way we view the accumulation of knowledge might radically shift. Imagine a world where every discovery made by an individual is shared instantaneously with everyone else. No longer would information have to be painstakingly disseminated over time, slowly trickling down to the masses. Instead, learning could become a communal endeavor where knowledge spreads like wildfire. The barriers to collective understanding could rapidly dissolve, with new ideas and concepts building upon each other in real time. In such a scenario, the pace of innovation would accelerate exponentially. Ideas would ripple outward, cascading across the global intellectual landscape in a way that transcends time and distance. No longer would breakthroughs emerge in isolated pockets, confined by the limitations of communication and geography. Instead, innovations would unfold simultaneously across vast stretches of space and time. A discovery made in one corner of the universe could spark a chain reaction of progress elsewhere, igniting new possibilities for exploration and understanding. However, while this vision of immediate knowledge sharing holds incredible promise, it is not without its potential pitfalls. The very thing that could drive progress, the rapid exchange of ideas, might also stifle creativity. In a world where everyone is privy to the same information, the uniqueness of individual exploration could be lost. The diverse paths of thought that currently shape our understanding of the universe might converge too quickly, leading to a more homogeneous worldview. The depth of independent exploration, the willingness to question and challenge assumptions, could be sacrificed in the rush to share and assimilate knowledge. In this new intellectual landscape, reality itself might be perceived differently. With constant collaboration, the very nature of understanding could shift from linear to multidimensional. The insights of one individual could spark new avenues of thought in others, creating an interconnected web of ideas that continuously evolve. This constant exchange of knowledge could lead to a richer, more complex grasp of existence, one that transcends the limitations of current thought. And yet, this depth of understanding would hinge on striking a delicate balance between the speed of knowledge dissemination and the value of independent discovery. As humanity extends its gaze to the stars, the importance of communication technologies grows ever more critical. Today, our most reliable means of communication rely on radio waves, which, while effective over short to medium distances, face significant challenges as the cosmos stretches further out. The analogy is simple. Just as shouting across a lake becomes more difficult the further apart the two voices are, radio waves lose strength over vast distances. This limitation has sparked a quest for new technologies capable of overcoming the vast expanses of space, technologies that could revolutionize how we communicate across the stars. One promising avenue lies in laser-based communication. Unlike radio waves, which disperse as they travel, laser beams can maintain their intensity over far greater distances. Picture a flashlight beam cutting through the darkness of space, its focused light carrying a message to distant spacecraft or celestial bodies. This innovation holds the potential to improve the clarity and speed of interstellar communication, ushering in a new era where messages can travel through the cosmos with unprecedented efficiency. Yet, even beyond laser communication, the field of quantum communication offers tantalizing possibilities. Quantum mechanics, the bizarre and counterintuitive laws that govern the microscopic world, could hold the key to communication that is both faster and more secure than anything previously imagined. In quantum communication, information is transmitted through the entanglement of particles. Two particles that, once linked, can affect each other instantaneously, regardless of the distance between them. Imagine flipping a coin on one side of the galaxy, only for someone light years away to instantly know the result. If harnessed, this phenomenon could allow for near instantaneous communication, potentially opening the door to real-time conversations with spacecraft or even future colonies on distant worlds. In addition to these advanced methods, satellite networks play a vital role in extending the reach of communication systems. By establishing a constellation of satellites that relay signals across vast stretches of space, we could ensure that spacecraft remain in constant contact with Earth, no matter how far they travel. These satellite networks act as a series of mirrors, bouncing signals between them, maintaining a stable connection that stretches across the cosmos. This infrastructure would be crucial for ensuring that messages are received and sent with minimal delay, no matter the distance involved. Artificial intelligence could further streamline this process, managing vast amounts of data and ensuring that critical messages are prioritized. Just as a librarian sorts through books to maintain order and accessibility, AI could help filter through the noise of space communication, ensuring that only the most important signals reach their destination. By automating this process, AI would not only enhance the efficiency of communication, but also reduce the chances of important information being lost in the flood of data that flows through the ether. The potential for these technological advancements to unlock the secrets of distant worlds is immense. With each new leap forward, the dream of interstellar communication draws closer to reality. However, the journey to bridging these cosmic distances is not without its challenges. It is a journey that requires both innovation and patience, as we continue to push the boundaries of what is possible. Yet with each breakthrough, the possibilities multiply and the path forward becomes ever more exciting. In the distant future, we might live in a universe where the traditional methods of communication, speaking or sending signals, no longer suffice. The vast distances between stars and galaxies would demand new, more innovative methods. One possibility could involve the use of light pulses encoded in patterns of light and sent across space using laser technology. This method would allow messages to travel vast distances, but would require precise alignment to ensure the signal reaches its intended destination. Laser beams could act as the interstellar equivalent of a flashlight, sending messages through the darkness of space with pinpoint accuracy. Another exciting possibility lies in the use of gravitational waves, the ripples in the fabric of space-time caused by massive objects moving through the universe. If we could encode information onto these waves, it would create a unique communication channel that could bypass obstacles that other signals might encounter. Gravitational waves could travel through space, unaffected by the usual barriers that hinder traditional forms of communication, making them a potential game-changer in the quest for interstellar dialogue. Quantum entanglement, too, holds great promise for the future of communication. This phenomenon, where particles become linked in such a way that changes to one particle instantly affect the other, could offer a means of instantaneous communication across vast distances. If harnessed, quantum entanglement could allow for the transmission of information faster than the speed of light, defying the limitations imposed by current technologies. Finally, biosignals and chemical communication could also play a role in this future of interstellar communication. By encoding messages into the genetic code of specially engineered organisms or synthetic entities, we could send information across environments where traditional electronic signals fail. These biocommunication methods would open up entirely new avenues for communication, particularly in contexts where electronic signals are unable to penetrate or survive. As we contemplate these possibilities, it becomes clear that the future of communication is diverse and dynamic as the universe itself. The methods we use to connect with one another, whether through light, gravity, quantum particles, or biology, will depend on the unique characteristics of the civilizations involved, their environment, and the technologies they develop. In this vast, ever-expanding universe, the ways in which we communicate are only just beginning to reveal themselves. And as we continue to explore the cosmos, we open the door to a future where connection across time, space, and even species becomes an essential part of our shared experience. The rapid evolution of technology has not only reshaped the way we live, but also how we communicate, often presenting barriers that extend beyond mere technical limitations. The very essence of technology has the potential to create divides, particularly across different cultures. As technology becomes increasingly embedded in daily life, it can magnify cultural differences, altering how civilizations use communication tools and, in turn, leading to conflicts or misinterpretations. A message that might seem clear in one cultural context could be entirely misunderstood in another. This miscommunication becomes all the more complex as the speed at which information travels accelerates, leaving little room for thoughtful dialogue and reflection. The rapid exchange of data often results in hasty conclusions, devoid of the nuances that typically come with deep consideration or awareness of diverse traditions. For meaningful inter-civilizational dialogue to flourish in this digital age, deliberate efforts must be made to ensure equitable access to technology. However, this alone isn't enough. There must also be a mutual willingness to adapt to the communication styles and values of others. This delicate balancing act is critical. It enables technology to harness its potential to connect people while minimizing its disruptive effects. In doing so, it lays the foundation for a rich, complex tapestry of exchanges between civilizations, fostering mutual understanding and cooperation in an increasingly interconnected world. As we look further into the future, the expansion of the universe could introduce a new layer of complexity to our understanding of the cosmos. In a hotter universe where conditions are rapidly evolving, the concept of cosmic prediction or divination may take on profound significance. The rising temperatures could give way to environments that are more chaotic and unpredictable, where long-established patterns and cycles become more difficult to anticipate. In such an environment, ancient practices of reading the skies for insight into natural events may see a resurgence as societies seek stability in a rapidly changing world. Historically, celestial bodies have always played a vital role in human understanding, guiding the rhythms of seasons, tides, and agricultural cycles. As the universe warms and climatic conditions shift, these cycles could be thrown into disarray, compelling societies to look back to the stars for answers to navigate the new, unpredictable landscape. This practice could transform into a modern form of cosmic divination, where not only astronomers but also thinkers from a variety of disciplines interpret celestial phenomena. The goal would not simply be to forecast agricultural or navigation needs, but to anticipate ecological shifts on a broader scale, unraveling the mysteries of a universe in flux. The relevance of cosmic prediction may go beyond mere practicality. It could also emerge as a psychological need for humans, offering a sense of connection and continuity in a world that feels increasingly uncertain. Just as astrology once offered comfort in turbulent times, a scientific or philosophical interpretation of cosmic events could serve as a metaphorical compass, helping people feel grounded and purposeful as they navigate the complexities of a warming planet and ever-changing environments. As our comprehension of cosmic forces deepens, the intersection of science and spirituality might become more pronounced. The urge to predict and interpret phenomena beyond empirical data could become a more integral part of how societies understand and cope with the chaotic nature of a hotter universe. This blending of scientific inquiry with spiritual yearning could lead to a revival of practices once dismissed as superstition or mysticism, transforming them into credible frameworks for understanding human existence. For millennia, people have looked to the stars for guidance, believing that celestial influences could shape their lives in meaningful ways. With the continued expansion of our understanding of astronomy, some of these mystical practices may gain renewed significance. One such practice is astrology, which interprets the positions and movements of celestial bodies as indicators of personal traits, behavior, and future events. As public interest in space exploration grows, astrology may evolve to reflect a heightened sense of human connection to the cosmos, with each planetary alignment or celestial event offering fresh insights into personal identity and life's course. In a world where the search for meaning and belonging intensifies, cosmic rituals may find new relevance. Already, many existing traditions utilize lunar phases or planetary cycles to guide various rituals, meditations, and spiritual practices. As humanity's awareness of cosmic phenomena expands, practitioners of these ancient traditions might find fresh inspiration. They may create new rituals aligned with significant astronomical events, such as supermoons, meteor showers, or eclipses, seeing these as powerful moments for personal reflection or collective intention setting. These celestial phenomena may be regarded as key moments for accessing higher wisdom, making them central to rituals that strengthen a person's connection to both the universe and their own inner peace. At the same time, the growing popularity of mindfulness and holistic wellness practices may merge with cosmic rituals. For those seeking balance and well-being, guided meditations focused on the flow of cosmic energy could become commonplace, alongside ceremonies that honor the cyclical rhythms of the universe. These practices would aim to foster harmony, both within individuals and between humanity and the cosmos, as people look for ways to align themselves with greater forces in an increasingly unpredictable world. Such practices, both scientific and mystical, point to a deeper need for connection. In a world that seems increasingly disjointed and uncertain, practices rooted in cosmic influences may resonate more profoundly with people. They offer a sense of belonging, purpose, and understanding of one's place in the universe. As individuals search for answers beyond the mundane aspects of daily life, the intersection of science, mysticism, and cosmic forces could provide a meaningful framework for interpreting the complexities of existence. This intersection also creates an intriguing dynamic between two different methods of predicting and understanding the future: scientific and mystical. Both approaches offer valuable insights, but in fundamentally different ways. Science, grounded in empirical evidence, relies on observable data and repeatable experiments to make predictions about the future. Scientists seek to explain the world through natural laws, whether it's the motion of planets, the behavior of particles, or the mechanics of weather patterns. Meteorologists, for instance, use massive amounts of data to forecast weather, relying on well-established scientific principles to provide predictions that guide human behavior, even if they are not always perfectly accurate. Mysticism, on the other hand, is a more intuitive and spiritual approach. Practices like astrology, divination, and prophecy offer guidance not based on observable phenomena, but on personal insight and ancient traditions. These methods emphasize a holistic understanding of life and the universe, relying on the belief that unseen forces shape the future in ways that can be tapped into through intuition, spiritual connection, or rituals. For some individuals, these practices are deeply personal, offering a sense of comfort and direction, even if they cannot be empirically verified. In the modern world, these two approaches can coexist, each offering a distinct kind of value. While many might rely on scientific methods for practical reasons, they may also turn to mystical practices for deeper, more personal meaning. The duality between these two worldviews creates a fascinating space in which both science and mysticism can complement each other, providing a fuller picture of reality. However, conflict arises when mystical predictions claim to predict events that can be tested scientifically. For example, if an astrologer predicts a specific event based on celestial alignments, but scientific principles contradict that prediction, a clash of paradigms occurs, highlighting the tensions between empirical evidence and intuitive spiritual belief. This ongoing dialogue between science and mysticism, between the observable and the intangible, will continue to shape humanity's search for understanding as it navigates the uncertainties of a rapidly changing world. The relationship between science and mystical practices often hinges on the mutual understanding and openness of individuals who recognize the distinct yet complementary purposes each serves. Science, with its structured and methodical approach, seeks to uncover empirical truths about the universe, grounded in observation, experimentation, and logical reasoning. Mystical methods, on the other hand, pursue a more elusive form of knowledge, aiming to guide individuals towards spiritual understanding and transcendence. These two perspectives, though seemingly at odds, can offer profound insights into the mysteries of existence. Rather than viewing them as conflicting, a dialogue between the two approaches can lead to a richer, more nuanced view of reality. The convergence of science and mysticism can open up new ways of thinking, especially when considering the broader questions about the future and our place in the cosmos. In a hotter universe, the dynamics of interstellar alliances would be fundamentally altered by the escalating challenges posed by rising temperatures and the shifting environmental conditions that accompany them. As the universe's temperature increases, civilizations would find themselves facing more intense competition for increasingly scarce resources like water, energy, and habitable space. Under these conditions, the very survival of different societies would depend on their ability to adapt to the heat and collaborate in ways that were previously unimaginable. Early on, alliances could emerge between civilizations that recognize the necessity of pooling resources and sharing knowledge to tackle the shared threat of soaring temperatures. These partnerships could foster cooperation in technological advancements, such as the development of advanced cooling technologies, allowing civilizations to survive in increasingly hostile environments. For instance, two civilizations might combine their expertise to design and deploy energy-efficient systems capable of reducing the heat burden, benefiting both in their struggle to endure the ever-rising temperatures. However, as environmental stressors intensify and resources become even more constrained, the very alliances formed out of necessity might begin to unravel. Trust, so essential in any partnership, could erode as competition for dwindling resources increases. In this scenario, one civilization might hoard vital resources, stockpiling them in an effort to secure its future, while the other struggles to meet its commitments or provide adequate support. Desperation brought on by extreme heat could drive suspicion and fear, giving rise to rivalries between once cooperative groups. In response, new alliances could form as factions shift their focus to those they perceive as having more favorable prospects, whether in terms of resources, protection, or technological superiority. These shifting alliances could create a fluid and volatile political landscape, where relationships are constantly in flux. Smaller, more agile factions might thrive in this environment, adapting swiftly to changes and aligning with new partners as circumstances evolve. The need to continually reassess alliances based on immediate survival needs would dominate the social and political dynamics, leading to a complex web of cooperation, competition, and shifting allegiances. In the harsh conditions of a hotter universe, the very nature of interstellar relationships would be reshaped. The constant pressure of adapting to extreme temperatures and fluctuating resources would force civilizations to continuously reassess their survival strategies. This constant need for adaptation would foster a more dynamic and often unpredictable form of diplomacy, one in which trust and competition constantly intertwine. Alliances might form and dissolve in rapid succession, creating a system in which long-term stability becomes secondary to short-term survival. As we contemplate the vastness of space and the potential for cosmic warfare, it is essential to recognize how the unique environment of space itself would influence the tactics and strategies employed in such conflicts. Space is a harsh and unforgiving realm, vastly different from the familiar world of Earth. There is no atmosphere, which means sound cannot travel, and visibility is often hindered by cosmic dust, asteroids, and radiation from distant stars. These factors alone would radically alter how conflicts are waged beyond our planet. The immense distances between celestial bodies would make close-range combat impractical. Instead, spacefaring civilizations would rely on long-range tactics, with spacecraft equipped with advanced targeting systems capable of striking from vast distances. In this new arena, battles would unfold like a high-stakes game of chess, where each player must anticipate their opponent's moves far in advance rather than reacting to immediate threats. The ability to plan several steps ahead would be crucial, as the vastness of space would leave little room for error. Gravitational forces would also play a pivotal role in space warfare. Spacecraft could exploit the gravity wells of planets, moons, or even stars to gain speed, alter their trajectories, or change direction. By mastering the intricacies of gravitational manipulation, spacecraft could execute surprise maneuvers, making it extremely difficult for opponents to predict their movements. This ability to navigate the cosmos using the natural forces of the universe would be a game changer in any conflict. Moreover, the potential for new technologies would reshape the very nature of space warfare. Weapons utilizing solar power, directed energy beams, or even advanced particle accelerators could replace traditional projectiles, offering a new frontier for destructive technology. These futuristic armaments would need to account for the unique challenges of space, such as fluctuating energy levels, radiation shielding, and the absence of atmosphere for deflecting or absorbing attacks. The use of energy-based weapons could also introduce a new level of precision, where strikes are no longer limited by the constraints of physical ammunition. But warfare in space would not be limited to physical confrontations alone. The vast, isolated nature of space would also give rise to psychological strategies, such as the use of misinformation and deception. Just as in traditional warfare, the manipulation of communication could become a powerful tool. The vast distances between spacefaring civilizations would make it difficult to verify information, leaving room for manipulation. Spacefaring entities might engage in disinformation campaigns to mislead their enemies, masking their true intentions or locations, further complicating the already complex nature of interstellar conflict. As space exploration continues to advance and our technological capabilities evolve, the strategies and tactics employed in cosmic warfare would inevitably grow more sophisticated. The interplay between technology, strategy, and the harsh environment of space would shape the future of conflict in ways we can only begin to imagine. Given the increasing number of nations and private entities entering the realm of space exploration and utilization, the need for peacekeeping strategies to maintain harmony in the cosmos becomes more pressing. Space, once thought of as a vast, unclaimed frontier, is rapidly becoming a contested domain. The potential for conflict is growing as more stakeholders vie for control over space resources, such as satellite orbits, asteroid mining rights, and access to celestial bodies. One possible approach to preventing conflict in space would be the establishment of international treaties designed to govern activities in outer space. These treaties could set clear guidelines for the peaceful use of space, ensuring that all parties involved respect each other's rights and responsibilities. They could regulate key activities such as satellite launches, space exploration, and the exploitation of space resources, ensuring that no one nation or entity gains an unfair advantage over others. Another possible strategy would be the creation of a unified space governance body, much like the United Nations operates on Earth. This body could consist of representatives from a variety of nations and private organizations, tasked with mediating disputes, fostering cooperation, and ensuring that space remains a domain for peaceful exploration rather than competition. Such a body could provide a platform for dialogue, helping to resolve conflicts over space resources, debris management, and planetary defense. Technology would also play a critical role in maintaining peace in space. Transparent systems for tracking space activities, such as satellite positions and orbital paths, could help ensure that all parties involved are aware of each other's actions. These systems would allow for real-time monitoring of space activities, making it easier to avoid accidental collisions and reduce the risk of misunderstandings that might lead to conflict. By creating an environment of accountability and transparency, spacefaring civilizations could work together to address shared challenges, such as the growing problem of space debris, and mitigate the risks of potential conflict. In a rapidly advancing world where humanity is stretching its reach beyond the confines of our home planet, the importance of educational programs aimed at nurturing a culture of collaboration and a profound respect for the shared nature of outer space cannot be overstated. The cosmos is not a distant, isolated frontier. It is a collective domain where, if we are to thrive, stewardship must be the cornerstone of our exploration. By embedding these principles into the very fabric of education, both current and future generations will come to understand that space is not a realm to be seized, but rather a vast, interconnected expanse to be protected and shared. These programs are not simply tools for imparting knowledge. They are essential mechanisms for fostering the kind of unity that is necessary to ensure that humanity doesn't fall into the trap of competing for resources in the far reaches of space. At its heart, this collective stewardship is more than a matter of technical cooperation. It is about maintaining cosmic harmony. Preserving the integrity of our exploration requires a sophisticated blend of diplomacy, effective governance, cutting-edge technologies, and a shared commitment to peaceful discovery. In the absence of these elements, the very principles that drive us to explore the cosmos could become the cause of conflict. The space race, which in the past was marked by competition and rivalry, must evolve into a collaborative effort where the aim is not to conquer, but to explore in harmony. Through unified efforts, humanity can ensure that space remains a realm of discovery and opportunity, not a battleground of strife. This notion of collaboration extends into the heart of our very existence. Consider the origins of the universe, a concept that is rooted in both scientific discovery and philosophical pondering. The Big Bang, the monumental event that began everything we know, birthed not only time and space, but the very building blocks of existence itself. However, imagine if that explosive beginning had been even slightly different. If the heat generated in those early moments had been a fraction higher, the expansion of the universe would have unfolded differently, altering the very makeup of the matter that exists today. The particles that emerged, such as protons and neutrons, would have had greater energy, resulting in different forms of matter and potentially allowing heavier elements to form more readily in the earliest phases of the universe. These minute shifts could have profound consequences on the stars that would later emerge, on the elements they would produce, and ultimately on the kinds of planets that would develop. If the universe had been hotter in its early moments, stars might have burned hotter and brighter, yet with significantly shorter lifespans. These stars, in their fiery end, would have exploded in supernovae, scattering vast amounts of new elements into the cosmos. While this would lead to an abundance of diverse elements, it could also have dramatically altered the chemical pathways required to form the complex atoms that are fundamental to life as we know it. Moreover, such changes would not be confined solely to the stars. The very structure of galaxies themselves might have been different. The gravitational forces and interactions that govern their formation could have played out in entirely new ways, potentially resulting in galaxies with entirely different shapes, sizes, and compositions. Planets, too, might have developed under vastly different conditions, with environments that could be too hot to sustain liquid water, or even worlds with entirely unfamiliar atmospheric compositions. In a universe shaped by a hotter early state, the very fabric of reality would be different, and with it, the fundamental rules that govern life itself. This delicate balance that defines the nature of our existence underscores the fragility of the universe as we know it. Our understanding of reality hinges on the specific conditions that were set in motion during those early, formative moments of the cosmos. A slight change in the temperature of the universe's birth could have led to an entirely different reality, a reality where life as we know it might not have been possible, or might have taken forms we can barely imagine. These philosophical and scientific questions open the door to the intriguing notion of alternate universes, each with its own set of physical laws or versions of history. This concept, once confined to the realm of science fiction, has become a serious area of exploration, inviting us to reconsider the very nature of existence. If alternate universes truly exist, each with its own set of conditions, what does that mean for our understanding of reality? Could there be realms where the fundamental laws of physics are vastly different from our own, or where history unfolded in radically alternate ways? This possibility challenges the limitations of our current scientific models and expands the horizons of what we consider achievable. On a scientific level, the concept of parallel universes pushes the boundaries of quantum mechanics, suggesting the existence of multidimensional contexts where these universes coexist, side by side, each with its own version of reality. This idea invites researchers to explore the interactions between these realms, seeking new insights into the fundamental nature of the cosmos, existence, and perhaps even consciousness itself. It opens up new avenues of thought that could radically alter the way we perceive the universe. Philosophically, the implications of such a reality are profound. If every decision we make creates a new universe, what does that say about free will? The idea that each choice spawns an alternate reality raises complex questions about identity and agency. If each individual decision carries with it the weight of creating an entire new universe, how should we evaluate the choices we make? This philosophical exploration could lead to a re-examination of ethics, as individuals grapple not only with the immediate consequences of their actions, but with the vast web of outcomes that ripple outward through countless parallel worlds. Moreover, these questions might stir debates about the very nature of existence. Are these alternate universes as real as our own? Or are they merely hypothetical constructs, speculative ideas that challenge the limits of human imagination? This duality between what is real and what is possible creates fertile ground for existential inquiries. Could these alternate realities be as tangible as the one we experience? Or are they products of our minds, reflections of a universe yet to be understood? Such questions resonate with our cultural and spiritual beliefs, shaping our views on fate, destiny, and the overarching design of the cosmos. The idea of alternate universes not only challenges established scientific paradigms, but also sparks a profound philosophical introspection. It invites us to question our place in the universe and reconsider the very limits of what is possible. As our understanding of the cosmos expands, so too does our capacity for imagination. The human spirit has always sought to push the boundaries of what is known, to reach beyond the limitations imposed by the present moment, and explore the unknown. Throughout history, concepts once deemed impossible, such as flight, communication across vast distances, or space travel, have been transformed into tangible realities. Ideas that began as dreams in the minds of innovators and dreamers have become fundamental aspects of our everyday lives. Technologies like the internet, smartphones, and the very concept of space exploration were once thought to be the stuff of fantasy. Yet, through human creativity and ingenuity, these dreams have been realized, expanding the boundaries of possibility and showing that many of the limits we perceive are often self-imposed or based on the knowledge available at a given time. As we venture into space, we are faced with phenomena that challenge our understanding of the universe, urging us to reconsider what is achievable. Concepts such as colonizing other planets or harnessing energy from distant stars are no longer confined to the realm of science fiction. They are real, practical ideas that spark serious discussion. As we gain a deeper understanding of physics, biology, and the cosmos, we are simultaneously expanding our imaginative capacity, finding new ways to address challenges that once seemed insurmountable. Innovation thrives on collective curiosity. By sharing ideas and collaborating, humanity breaks down the barriers that once seemed insurmountable. This communal imagination fosters an environment in which what was once inconceivable gradually becomes plausible. The boundaries of possibility are not static. They evolve with our understanding. And as we continue to explore, both the frontiers of knowledge and the scope of imagination will expand, reshaping our perception of what is possible. Consider the role of heat in shaping the universe. Heat, in its many forms, plays a critical role in everything from planetary formation to the existence of life. It is a foundational force that drives much of the natural world as we know it. Now, imagine a universe where the origin of heat differs from our own. This shift could result in radical changes, altering the very conditions that sustain life. Such a change might lead to environments unlike anything we've ever encountered, influencing not only the physical characteristics of planets, but also the kind of life that could evolve on them. In such a universe, art and symbolism would likely be transformed as well. Artists draw their inspiration from the world around them, interpreting the colors, textures, and conditions that define their reality. In a world where heat influences everything from the atmosphere to the landscape, the very nature of artistic expression would shift. Landscapes dominated by unfamiliar heat patterns would inspire new color palettes, with artists turning to hues that are yet unknown to us, colors that might evoke feelings of strangeness or awe. These new visual languages would not only reflect the changes in the environment, but also offer a glimpse into the vast unknown possibilities that such a universe holds. In the complex interplay between art, nature, and science, symbolism has always been a tool to reflect our understanding of the world. However, as the conditions of the universe evolve, so too will the symbols we use to express our experiences, emotions, and perceptions. The universe we live in is not a static entity, but one that is constantly changing, shaped by forces that go beyond human comprehension. If the very source of heat that drives our planet's cycles of life were altered even slightly, it could trigger a cascade of events that would fundamentally reshape the relationship between beings and their environment. In such a scenario, the symbolism we see in art might undergo a radical transformation, evolving to reflect new relationships between life and the forces that govern it. This alteration, especially if it led to unusual natural rhythms or life cycles, could result in artistic expressions that focus on balance and disruption. In traditional art, motifs often symbolize fundamental ideas like growth and decay, life and death, and the cyclical nature of existence. Yet, in a universe where environmental conditions are unexpectedly altered, these symbols might merge, blur, or even flip, suggesting that life can flourish in ways previously unimaginable. Life may adapt to survive in a harsher, more unpredictable world, or conversely, it may thrive under entirely new conditions that defy traditional expectations. Such shifts would not only reshape the physical landscape, but would also bring about profound changes in human thought and cultural narratives. Through the lens of art, these transformations would be documented, not simply as visual representations of a new and altered universe, but as reflections of the shifting human experience itself. As humanity's understanding of life, existence, and our place within the cosmos changes, so too will the narratives told through art. We may witness the emergence of stories focused on resilience and adaptation, with characters and symbols representing the drive to find meaning within a universe that now feels vastly different. These artistic explorations would be not just reflections of the external universe, but of the internal human struggle to come to terms with a radically transformed reality. Art would therefore become more than just an expression of beauty or aesthetics in this altered world. It would stand as a testament to the deep shifts in thought, culture, and human identity that are driven by an evolving understanding of the universe. As humanity pushes further into the vastness of space, we can anticipate the rise of new artistic motifs and styles that are directly influenced by celestial phenomena. The mysteries of the cosmos, including the celestial bodies that lie beyond the boundaries of our planet, would become fertile ground for artistic inspiration. Space itself offers a treasure trove of possibilities for artists. The stunning hues of distant nebula, the swirling patterns of galaxies, and the strange beauty of black holes, all of these would present new ways for artists to convey an experience that transcends earthly perceptions. Artists might be drawn to the iridescent colors found in the cosmos, combining vibrant hues to create art that conveys an otherworldly experience, one that defies the conventional palettes of earthly materials. The very colors of space could inspire new forms of artistic expression, capturing the strange beauty and inherent mystery of the universe itself. At the same time, the concept of time and its relativity would likely give rise to an entirely new style of art focused on fluidity, movement, and change. Imagine an artwork that seems to stretch and contract, capturing the sensation of time warping under the influence of gravitational forces. Abstract forms could represent the bending of time, drawing upon the physical principles governing celestial bodies, creating a visual representation of time's fluidity. These artworks would not simply reflect the scientific understanding of time, but would also invite the viewer to experience the unpredictability of the universe in a visceral, almost tactile way. The integration of new technologies into art would further transform the way we experience the universe. Advances in virtual and augmented reality could offer immersive experiences that allow viewers to explore the very fabric of space itself, traveling through star fields, gliding past distant planets, or even navigating through wormholes that twist the fabric of space-time. In this new world of digital and virtual art, the boundaries between artist and audience would begin to blur, creating an interactive form of storytelling where viewers are no longer passive observers, but active participants in the journey through the cosmos. These technologies could also give birth to new genres of art, such as cosmic realism. In this genre, artists would explore the hypothetical but scientifically plausible landscapes of alien worlds, perhaps depicting strange flora, unfamiliar geological structures, or alien atmospheres that challenge our understanding of what is possible. These artistic representations would push the limits of our imagination, encouraging a deeper discussion about the existence of life beyond Earth and the nature of otherworldly environments. In doing so, these artworks would compel humanity to reflect on its own place within the universe, suggesting that the cosmic is not just vast and incomprehensible, but is a world of potential, mystery, and possibility. Moreover, themes of interconnectedness and unity would begin to emerge within artistic explorations of the cosmos. As humanity ventures further into space and uncovers the interconnected nature of the universe, artists might explore how all things in existence are linked in a complex web of relationships. This could take the form of collaborative works that blend different mediums, cultures, and perspectives, symbolizing humanity's shared quest to understand the vastness of the universe. The focus on collaboration within art would highlight the collective curiosity that drives human exploration and discovery, becoming a metaphor for the unity that binds humanity together in an endless pursuit of knowledge. Throughout history, cosmic events have served as powerful inspiration for artists. The birth and death of stars, the formation of galaxies, and the changing cosmic seasons have all been depicted in various forms, each providing a rich visual and conceptual representation of the universe's vastness and complexity. One striking way to represent these grand phenomena is by translating complex scientific ideas into imagery that is accessible and relatable to human experiences. For example, the explosive birth of a star might be captured through vibrant, swirling forms and colors, evoking the intense energy and transformation that characterizes this event. In doing so, artists convey not just the scientific reality of star formation, but also the emotional awe that such an event inspires. Through their use of scale, artists can also convey the profound vastness of the cosmos. A single canvas might depict an expansive night sky filled with swirling galaxies and nebulae, each painted with bold, careless strokes that evoke the endlessness of space. The visual scale of such a painting not only reflects the scale of the universe, but also forces the viewer to confront their own position within it. These artistic representations invite us to reflect on our own existence, suggesting that our lives, while fleeting, are part of something far grander and more timeless. This exploration of the cosmos within art is not limited to the visual. Modern technologies such as digital art and animation have allowed for dynamic, moving representations of celestial bodies. These pieces capture the movement of stars, the dance of particles, and the flow of time itself. By embodying the energy and transformation inherent in cosmic events, these works of art not only depict the grand beauty of the universe, but also provoke thought and emotion. They invite the viewer to experience the vastness of the universe in a way that is both intellectually stimulating and emotionally evocative. In this way, artistic expressions of cosmic phenomena serve a dual purpose. They offer a visual representation of the universe's grandeur, while also prompting a deeper contemplation of life itself. These works invite us to look both upward and inward, finding meaning in the contrast between the infinite cosmos and our fleeting existence within it. They ask us to question our place in the universe, our relationship with the natural world, and the very nature of existence itself. The evolution of a universe that began only slightly hotter than our own rests on the concepts of continuity and change. Continuity, in this context, refers to the unbroken chain of processes and events that shape the cosmos. From the formation of simple particles to the emergence of complex galaxies, the universe follows a predictable sequence of events, guided by the immutable laws of physics. Change, on the other hand, highlights the ways in which these processes evolve and transform over vast expanses of time. A slight increase in the universe's initial temperature, for instance, could alter the balance of matter and energy, leading to entirely new cosmic structures and phenomena. If the universe had begun even slightly hotter, it could have led to a more rapid fusion of particles, impacting the creation of stars, galaxies, and black holes. The altered balance between matter and antimatter might have had profound implications for the universe's development, including the way galaxies formed and evolved. Even the force of gravity, which plays such a crucial role in shaping the universe's structure, could have been different in such a scenario. The interplay between continuity and change is essential to understanding how the universe evolves over time, and how even the smallest variation in its initial conditions can lead to vastly different outcomes. Throughout the universe's history, we have witnessed cycles that repeat over vast stretches of time. These cyclical events, the birth and death of stars, the formation and collapse of galaxies, the shifting of cosmic seasons, give rhythm to the universe's story. Just as the seasons on Earth bring about changes in the natural world, the universe undergoes its own transformations, revealing new beginnings from the remnants of the old. This cycle of creation and destruction suggests that every ending may pave the way for a new beginning, which is essential to the ongoing evolution of the cosmos. At the same time, innovative breakthroughs in science and technology can have a profound impact on how we perceive and interact with the universe. Each new discovery brings us closer to understanding the universe's mysteries and opens new possibilities for exploration. Whether it is the discovery of new forms of energy, advancements in space travel, or a deeper understanding of dark matter, these breakthroughs not only expand our knowledge, but also redefine our place within the cosmos. As humanity continues to push the boundaries of exploration and knowledge, we find ourselves not just rewriting the narrative of our own destiny, but reimagining the very nature of the universe itself. Thus, the universe is not a static entity, but a dynamic, living force, constantly evolving, expanding, and changing. The interplay between continuity and change, along with the ongoing discoveries of science and art, reveals a universe that is ever unfolding. It is a universe of infinite possibilities, where every breakthrough brings us closer to understanding the mysteries of existence, and every question we answer opens the door to new questions. And in this ever-evolving cosmos, art remains a powerful tool for understanding our place within it, offering a mirror to both the infinite and the intimate aspects of life.